Okay, I know there was a lot to go to there, so we're going to start. Maybe I think just it's almost like 8:30. So okay, so we're going to talk about miRNA. So how many of you have heard about miRNA? You probably are familiar, right? So okay, so I don't have to, because we're kind of running behind time, right? You know, we are short times. I supposed to complete this yesterday, and then right, and cancer too, but we were not able to. So I tried to finish this quickly, and then we do the signal transaction today, right? So miRNA, everybody knows what is RNA, right? Start moving. Okay, so ribonucleic acid is, or simply RNA. We know that it has like a base here, right? Okay, linked with the ribose sugar, phosphate. So this is a nucleotide. It links to another nucleotide, and then another nucleotide. So it's make a chain, right? It's a like a single standard RNA. So this is simply the structure of ribonucleic acid. But ribonucleic acid, there are different kinds. Okay, they have all the same structure, but their secondary structure is a little bit different. Okay, so most of the time what we know is about mRNA, right? The coding RNA, because mRNA is a messenger. Okay, so DNA transcribed into mRNA, and the mRNA makes protein, right? And then we have, you know, the protein could be structured protein, could be enzyme, you know. But there are other RNA which are non-coding. Okay? These RNA do not make any protein. Okay, but they are still there. So these are actually a number of different types. Like last, maybe I think 30 or 25 years ago, we just know only few RNAs like mRNA, tRNA, ribosomal RNA. They are the major RNA, right? But recently we know that there are a lot of RNA which people in the beginning did not know what their function is, so they were ignored. But now, as we know, and technology is getting advanced, we are getting they are recognizing their function. So these non-coding RNA is like ribosomal RNA or rRNA, transfer RNA, small nuclear RNA or snRNA or small nucleolar RNA, SNO-RNA, interference RNA, short interfering RNA, or microRNA. So we're going to briefly touch all these to see what are differences between these RNA, and we're going to mostly talk about mRNA. We all know the I have a pointer here. Okay, so we know everything. This DNA got a replication, makes own copy, and DNA under the transcription make the mRNA. This when its transcription happens, it transcribes the whole sequence, right? But the whole sequence is not the mRNA. It has extron and introns. So what it happens that this is like a pre-mRNA. It gets under processing, and all this extron is removed, and then we get mRNA which comes out, right? So some of this extron, they are the non-coding RNA, right? Which then later contribute to different other forms of RNAs, right? On the other hand, we get RNA, which is actually in the nucleus. This ribosomal RNA, it goes in proteins like a small unit, big unit, comes out, and then it gets assembled with tRNA, make the whole complete ribosomal unit. And mRNA comes out from here, and it makes the complete, protein synthetic machinery. This, a very classical, protein synthesis and transcription and translation, right? We also know that RNA virus enter into the cell, and then it goes into nucleus, reverse transcribe, make DNA, right? And DNA virus directly go into the nucleus and then undergo into replication, right? So this is very basic structure, right? If you see the structure of mRNA, now the thing is that mRNA has a very long structure. Okay, the only coding sequence is very small. So this is the only coding region, right? So this is a 5' region and this is 3' region. It has like in 5', which is we call 5' untranslated. It has like 7-methyl G cap, right, at the end, and then it's bound by cap binding protein. And then we have translational region. So this is the 3' end. We have this region which undergo translation, and then 3' prime untranslated region, which is on the other side, is stability element, right? And then is subcellular localization with kind of zip code address, and then it's a poly address. This is a poly address, right? And then it's a some kind of sequencing, which is kind of determine where it's going to go, where it's going to localize. So this is just to show you that how RNA looks like, right? mRNA. So ribosomal RNA, you all probably know what it is, right? So just to show you, in eukaryotic cells, we have two ribosomal, we have ribosomes, which is two units, like 60S and 40S. 60S, 40S has 18S RNA, whereas 60S has like three different 5S, 5.8S, and 20S RNA. The S means it's the sedimentation constant, so it doesn't mean that the weight of the unit, rather how it, when you centrifuge it, how what is the sedimentation constant, right? Compared to prokaryotic, little it's very much similar, but it has like different sedimentation constant and different ribosomal RNA. Okay, transfer RNA, we all know about it. The transfer RNA is involved in protein synthesis. So there's each amino acid has a specific tRNA, but there are certain amino acids, they have more than one tRNA, right? So we have about 32 different kinds of tRNA, right? Maybe I'll just go to the structure to show you. So this is just how the tRNA looks like. So it has it's a linear chain, but what happens that it undergoes this what we call hairpin loop, right? It's just like a hairpin, because there are some complementary bases. We know that G can pair with C, A can pair with U. So whenever they see the complementary bases, they pair and make a hairpin loop. The important thing is this: the anticodon. Anticodon is complementary to the codon and mRNA, which can recognize which amino acid. So this tRNA carries the amino acid, and then it started making the peptide chain. So that's how it do the translation. Again, very basic concept, right? Small nuclear RNA, right, or sRNA. Now, this small nuclear RNA is a class of molecules that are found within the nucleus of eukaryotic cell, right? They are transcribed by RNA polymerase or RNA polymerase 2. Now, the function of it is involved in RNA splicing, right? Before it is known that RNA, they don't have any enzymatic activity, right? I found that RNA actually can have an enzymatic activity. They are catalytic agents, and then first of all discovered that Nobel Prize on this discovery. So it's kind of involving RNA splicing between, and then it's always associated with specific protein and the complexes that are referred to small nucleoribo, small nucleoprotein, or SNRNP. And this is like a terminology, SNRNP, or often like it's just pronounced SNRP. Okay, so and then we have a small nuclear ribonucleoproteins. So what it is just a complex SNRP, like a small nuclear RNA, and it has RNA and protein, and the whole complex is known as like a spliceosome, which is kind of several SNRP kind of joined together here and make a spliceosome, and they involve in actually in RNA processing. Like this is a RNA molecule, so it's going to cut from there, make a mRNA, and then this extron is removed out. So they're involved in some kind of catalytic splicing of RNA. Okay, and then we have a small nuclear ribosomal RNA, or snRNA. Or sorry, back. Okay, small nuclear RNA. As the name suggests, is present in the nucleus. Now we have a nucleus, and then a small portion within the nucleus is nucleolus, right? Very small, 6 to 300 nucleotide, right? And what it is they have like several functions, and they're classified into 3 groups. They participate in making ribosomes by helping to cut the large RNA precursor into small ribosomal RNA. Remember, we talked about ribosomal RNA has different RNA in there, so they come on one piece. But this small nuclear RNA cut into smaller pieces of 28S, 18S, and 5.8S molecule. The classification is it basically depends on their structure. So here it is like they have different these kind of boxes that present certain sequences. So that's how their structure look like. And again, there's a helping group where the bases are complementary and the bases are not complementary. They cannot base pair. And then is RNA interference or SI or small interfering RNA. Now these RNA is a like RNA interference of mechanism where is actually RNA bind to some complementary bases on mRNA, right? We know that mRNA is involved in protein synthesis. So what happens when they bind to the complementary one? It actually stops the transcription. And when it's bind, then RNA. So that's why it's called interfering RNA because it's actually interfere the function of RNA. Okay, and again is just to show you that we have long double stranded RNA. There's an enzyme which we call dicer, and then that other protein complex. I don't want to go into detail. I just want to just explain you that we have siRNA. So it's an enzyme cut a precursor into siRNA, and this get kind of loaded on this protein complex, and then protein complex is actually goes and recognize the sequence on target mRNA, and when it find the complementary bases, it make a pairing, and then it cuts the RNA. Right, so RNA is basically cleaved and lose the function. Okay. So there was just an introduction about, you can just save time. Okay, so we're going to mostly talk about miRNA or microRNA. So these are very short pieces of RNA, about only 19 to 24 nucleotides. So they are very short, right? They are known as like the master regulator of gene expression because they bind to the RNA and then they stop the RNA function. Okay. The post transcription gene silencing of target messenger RNA. Transcription, I mean the RNA is transcribed into RNA after synthesis, then they interfere, right? And they involve in a variety of biological function like cell proliferation, apoptosis, development, differentiation, metabolism, immunity, neural patterning, stress response, aging, and cell cycle. So a lot of biological processes they directly control. They are conserved among invertebrates, vertebrates, and plants. And this is all about like over 1,000 mRNA are identified, right? Right? More than 70% of miRNA are transcribed from individual mRNA genes. So there are certain miRNA genes. So these genes actually makes miRNA. So it's not that it's not the like, as I said that we have a precursor mRNA and the exon are removed, and then those exon are have different functions, right? So it's not the junk RNA. Rather, there are certain specific gene who makes miRNA. Okay, more than 50 of all protein coding genes are regulated by mRNA in mammal. So you can see it's now they are involved in regulating all the protein synthesis. Okay. Sorry. Yeah.
What's the difference between siRNA and microRNA?
Yeah, siRNA is just the RNA pieces which are coming out from the exon, right? So what it means that there's a DNA sequence, right? This is transcribed into mRNA, right? So which is kind of pre-mRNA. Okay. So we can get out this pre-mRNA region which is not required, right? So they are moved, right? So those small pieces which are they are intervening, right? But in miRNA there are specific genes. So the genes are actually makes like DNA sequences which make the MIR. So, but the function is similar, like the interference. Like one interferes whenever it finds a sequence, right? The other one is actually is regulated, like the gene, it makes the mRNA, and this mRNA is specific for certain mRNA, is going to block the activity, right? Now, so biogenesis of mRNA, instead of going this, I just go over the diagram and then. Okay, so basically what happens that we have DNA, right? So DNA has this by RNA polymerase, they actually make pri-mRNA. Okay, so their sense is very, very regulated. So pri-mRNA and then this enzyme called DROSHA, it's like a complex, there are several activity. It converts pri-mRNA into miRNA precursor. So still it's not a mRNA, right? It's just a precursor. Then it gets exported through, which is facilitated by certain proteins. It comes out from the nucleus into cytoplasm, right? So there's another kind of protein complex which is called dicer. They actually, what it does is make miRNA into miRNA duplex. So it still is double helix, right? And then there's another enzyme wave complex which is called RISC. And what it does is convert miRNA into mature miRNA. So if you see here, so basically this is pri-mRNA. So DNA is kind of DNA is transcribing the RNA, right? And it is does the base pairing whenever there is a complementary pair. So this is mRNA, separate mRNA. And what happens with this enzyme? So it's loaded on this enzyme, and it's, it get cut and make pre-mRNA, right? Now this pre-mRNA here, right, is then bound to this transport system. So these are the protein which helps to make them out from the nucleus into the cytoplasm. So they get out into the cytoplasm, right? So when they get out, they still not complete. They still, because you see the double hairpin loop, right? Okay, so they are double helix, right? They synthesize as one chain, but because of their complementary base pair, they make this kind of helix structure. So they get out, and then okay. So this is, as I talk about this, like certain enzyme like dicer. So dicer has like number of activities. It's like it says RNase activity, RNase 3A, 3B activity, double standard, RNA binding domain. It has helicase activity. So it's just a protein complex, right? So here it is. So that's what again, just to go over. Again, we have like a gene, mRNA gene making pre-mRNA, pri-mRNA, pre-mRNA, it get out, right? So again, when it get out, it has a double helix. So then there's another enzyme, this is TRB. Okay, and these are like very, very long name. You don't have to remember, just to understand what's happening. So it does this this circle here. Now when it cuts, it becomes like a double stranded RNA, right? So then it's loaded on the RISC assembly, and then the one of the chain is destroyed. Okay, so we just left with one chain, right? Now this is now ready to bind with a complementary pair. So this is, we have RNA like the 5' and 3' polyintel. So this is transcriptional region. So it binds there. Once it's bind to target, it start leaving the RNA, and then there's how interfere the RNA activity. Okay, so again, this is the same thing, like that we have pri-mRNA processing, making pre-mRNA, and then which is getting out, and then again the loop is remove double stranded RNA, and then double stranded RNA then converted into single stranded RNA. It recognizes the target and then leaves. Okay. Now, what happens that this is a very general structure of mRNA. So again, we have 5' and 3' and coding sequence. So its RNA is basically present in a circular form. It's not open form, in a circular form. Because what happens that there are certain proteins like they bind to different regions, and then they make a circle, right? So again, the mechanism, you can, just to save time, I just go there. So the thing is that, the mRNA interferes in different ways. So these are the proposed mechanism that we have mRNA. So this inhibition of translational elongation. So what happens that, the mRNA is kind of making protein, doing translation. So when it binds, it's basically it's not destroying the mRNA, but just inhibiting the translation. So mRNA does transcribe. Other mechanisms are proposed like co-translational protein degradation, completion of the gap structure. So the gap protein bind to this to the 3' end. So it interferes there, right? Inhibition of ribosomal subunit joining. We know that when protein RNA converts to protein, ribosomal unit goes there, right? So it interferes actually with the ribosomal binding to the RNA. So these are all again proposed mechanism. Inhibition of mRNA circularization. We know that for transcription, RNA is like circle, so it interferes. It binds some place where it cannot really interact, and then de-adenylation of capping. So we know there's a poly-A tail. So this RNA sometimes degrade the poly-A tail. So there are different mechanisms proposed. Okay, this is about some just brief introduction about mRNA, right? Now the nomenclature. So there's, as I said, there are about more than 1,000 mRNA, right? And they were discovered randomly, like some discovered one RNA, the other mRNA. So it's you can actually go to this site, and this database actually collects all the information about different RNA, mRNA. Whoever discovered, they put their sequence there, right? So they come up with some kind of nomenclature. So it's like a 3-letter prefix for species. So it's HSA, right? So HSA is like a human species, right? MIR, right? So it's a Homo sapien MI, and then assigned sequential number. So then there is a number like 1, 2, 3. And paralogous sequence differed by 1 or 2 position are letters like 10, A, 10, B. Like there are sequences which are very similar, right? So like MI, so this is mRNA, so it's just MI, it is miRNA. Then we have number 10, right? But these sequences are very similar. They give the number 10A and 10B. So that's how it's very simple. You don't have to remember anything. It's just basically it's a numbering system, right? Okay. Now, as miRNA is interfered with transcription. Translation, right? You have RNA, right? mRNA is going to bind, right? And it's going to bind is going to stop the function of protein synthesis, right? So if it's so these miRNA are divided into 2 classes, right? Oncogenic or anti-oncogenic, right? So the thing is that if miRNA is binding to a oncogenic, right? What is it? Is going to be oncogenic or anti-oncogenic? Anti-oncogenic, right? So it's just a reverse thing when it's binding to an oncogene, right? So it's like anti-oncogenic or tumor suppressor mRNA. But when it's bind to a tumor suppressor gene, it's an oncogenic RNA. So we all got it, right? So there's basically, they are divided into oncogenic or anti-oncogenic or tumor suppressor. It's just like little ones, So the 2 types of changes in mRNA are associated with cancer, right? You get changes in one kind, you get changes in oncogenic mRNA, it means it's going to stop the tumor suppressor, right? Or so it's just basically, cancer cell, progression is a balance between what you get. So basically you get to decrease in tumor suppressor mRNA, right? And then you get increase in oncogenic RNA, right? So it's like a balance between 2 different RNA. And I give you examples, how people know what we know about this mRNA, right? So like the onco mRNA, and again the nomenclature is just like we have mRNA, we just put onco or anti-onco, right? To distinguish, right? So there are a number of miRNA like Mi10B, Mi21, Mi70, So it's like a complex which has like all these different mRNA all together, right? So they are involved in a number of cancers, right? For example, MIR is involved in breast cancer, suppresses a specific mRNA, which is like OXD10. So this is the protein, right? So this is a tumor suppressor protein. So what it does, this MIR10B is going to suppress the formation of that particular protein. So that's how it performs. That means, remember we talked about P10 yesterday. This is a tumor suppressor gene which actually internalizes the function of PI3 kinase, right? And then so again, the MI21 is going to suppress the P10, right? It means then PI3 kinase have the activity. Right? So it's just some example. There's some anti-onco mRNA example, like okay. So it actually what it does, it keep oncogenes inactive, right? Because it's anti-onco, right? And then again, there's some example like MI148 or LET7. These are some early known, they're not giving the name like this, there's some, again, there's some deviation in classification, right? So what it does is target RAS oncogene. Remember we talked about RAS, that RAS is get activated with GTP, right? By the GTP, and GTP when has life command to GTP, then it's become inactive, right? And that's the oncoprotein. Remember we talk about that it's a normal protein, but it's got mutation only of a single nucleotide exchange. It becomes like oncogene, right? Same as PI3 kinase. We talk about PI3 kinase, right? It's an enzyme which involved in AKT activation, right? And we'll talk about more in the signal transcription later. So these are any kind of inhibitors, right? So this is all about mRNA, and I don't. So it's just to show you that this is a signaling pathway that can receptor bind by something, a growth factor bind to a receptor, activate the kinases, and then all these signaling molecules, basically involved in cell, survival and all that. And we have different kind of mRNA which act on different targets, right? And then involved in cancer inhibition. And then I'm sure you cannot read this, but these are just to show that all the different kind of cancers and what kind of mRNA involved, which are upregulated or downregulated, right? So upregulated means they are onco mRNA, and these are the anti-onco RNA. Okay. Basically, we want to, for the sake of time, because we have a lot more to cover today. So these slides are all there, but what it is that, the expression is regulated, right? The mRNA is just not that the gene is going to turn on all the time. There's a mechanism that which is regulating to their expression, like genetic abnormality is the same thing that we involve mutation. It's just a normal genetic mechanism, epigenetic regulation, transcription factor, post-transcription regulation. Let's see if I can go quickly some of these. Like it also, they also produce we talk about gene translocation, right? Point mutation, you get a mutation, and then it can have consequences on either decrease synthesis, right, or chromosomal translocation, and you can increase mRNA synthesis. So there's like a genetic, and then there's some kind of mutation, right? Mutation also lead to some kind of RNA which has either higher binding or lower binding, just like gene epigenetic regulation. And again, epigenetic regulation, the same thing. The promoter, we have gene for mRNA, they can be methylated, which can inhibit their transcription, right? So it's similar kind of mechanism we have. Transcriptional regulation, again, there are transcriptional factors. They can be, okay, I just want to, and then there's auto-regulatory feed, like sometimes one RNA actually stimulates the synthesis of the other mRNA. These are like a complex mechanism, like we have big here, and P53, big is oncogenic, right? P53 is anti-oncogenic. So they kind of express different mRNA, which has entire oncogenic effect, whereas Nick is trying to make RNA which has oncogenic effect, right? So again, there's sometimes, increase sensitivity of one or decrease sensitivity of one is stimulate the sensitivity of other. So it's kind of, they regulate each other. Again, P53, then I can just. So it's just some examples of different RNA which is involved in like activation, and you can, see is they are involved in like apoptosis process, they're involved in P53 activation, they're involved in like angiogenesis, all these, they are pro-angiogenic mRNA and they're anti, angiogenic mRNA. So just they're involved in like a metastasis. So all the information is there on the handouts. I copied here, so you can copy from here. So, so I just want to give you the basic concept of miRNA. So is that in question? Sorry. So what we can do, we can stop here and then we can go to the next topic. So that, because we have a lot more to cover on signal transduction area. Sorry?
The same concept of the siren. I missed the first part.
Yeah, the first part.
Same concept.
Yeah, the first part we just describe different kind of RNAs because we have like RNA, like coding RNA, non-coding. Coding RNA we know is mRNA, right? Non-coding we have things like transfer RNA, ribosomal RNA, nuclear RNA. Okay, so it will be different. Yeah, you didn't miss very much. Okay, so what we're going to do here is go to next topic, and I'm gonna. Yes. So it's still opening. Okay, so we'll move on diet, cancer, and genes, right? So this is again the part of how the genes are involved in cancer, right? So far we have, like we talk about one basic concept of cancer, different classification. We talk about oncogene, tumor suppressor gene, and we talk about epigenetic regulation, right?
Excuse me, sir. Dr. Rafar, excuse me.
Methylation, histone modification, acetylation, and mRNA. So these are the three basic, which are they constitute the epigenetic regulations. But these does not involve in any change in sequencing, but involve in regulation of gene expression, right? And after that, so we're going to talk about diet, cancer, and genes. So this is the same lecture I gave, like in the chemistry workshop. I modified a little bit, but not very much, right? So we're going to see how diet is actually a very influential agent in regulating certain genes, especially in cancer gene. So we're going to talk
can
about.
You please share your slide? Excuse
Sorry?
me, sir. Can you please share your slide?
Oh, okay. Sorry, I think I forgot to share. Is it? Okay, can you see now?
Yes, sir.
Okay, thank you. Sorry for. Okay, all right. So again, I'm going to start with this saying that Hippocrates, like long time ago, actually said that let food be the medicine and medicine be their food. Right? So if you eat food like a medicine, let's have the food as a medicine and medicine be a food. So if you need a drug, instead of eating a drug, just have some kind of proper food. So it just shows you that the importance of food has been recognized early on. So people know that food is very important, right? And there's an Indian proverb saying when diet is wrong, right, medicine is no use. When diet is correct, medicine is of no need, right? So if you have proper nutrition, you really don't need medication. And if you know that most of the medication, they have origin from some kind of plant source, right? They, in ancient way, now we have like in very modern medicine, where we have all these like tablets and chemicals to treat certain diseases. For all time, people still get sick, right? And they get treated. And how they get treated is that they use some extract, some plant extract or something. So there was some information. What the modern science has done is that actually isolated the active principle and take in the tablet and sell, right? But the thing is, sometimes when they make the pure compound, then you also get the side effect. In the extract, there are things which actually decreases this toxicity, okay? Or there are some things which prevent some toxic effect and give you some benefits, right? So food has like both, can be good or bad, right? Now, the thing is that we talk about that the cancer, which are like we mentioned this yesterday, that only 5 to 20% cancer has some kind of genetic basis, like hereditary basis, can go from one generation to other generation, or people which has problem with their gene, like family clusters, people marrying into same family, they have certain genes which are clustered there, they have more risk. Other than that, like more than 80% of cancer are linked to the non-hereditary causes. And if you can see, like diet contributes about 35% of cancer development. And along with diet, tobacco use is about like 30%. So it's just controlling two things, tobacco use and diet, you can actually prevent somewhere between like 65 to 70% cancer. So it is a very preventable disease. And this is a very, like lethal disease. Once people get it, it can be cured. So it depends, if you can catch it early on. If not, then it can be, is a high risk, right? So just having, and I see a lot of really young people is smoking, or when I was smoking today, I was just saying that while they're smoking, there's no benefit to this. If they quit, they don't know. And smoking is, I explained yesterday, it's not only lung cancer, but it causes cancer of other tissue. Your lungs may be normal, you're feeling that, okay, I can smoke because nothing happens to my lungs, but you never know if, some other place, you're getting some kind of, process is started early on. Okay, now nutrition cancer. So when we study nutrition cancer, so it's basically we do the epidemiological study, right? What it is, there are certain kinds of things like we have to do either case control, cohort, or cross-section studies, right? They provide some kind of clue whether a nutrient compound or nutrition particular food is beneficial or is not beneficial, right? So I explain you what is the different kind of epidemiological study, right? So 1/3 of cancer deaths each year in US can be attributed to nutrition and other lifestyle factors. Now, in addition to, as I said, 30% of cancer is just linked to the food only, right? And we talk about this, the carcinogenesis occurs over here, right? So the thing is that you can basically prevent it at any stage of cancer progression. You can stop it, you can reverse it just by having the proper diet. Okay, so what are those epidemiological steps? Right? So one, people do case control step, right? So what happens in the case control? The diet of individuals with cancer are compared with those of cancer-free controls matched for age, sex, and other key factors. So we have a population, right? So we have a population here and a population here, right? So in this one, we have some people exposed and they're not exposed, right? Same as we have exposed and non-exposed people. But in this case, we take the one who would have the cancer, right? Okay, and then we get in the second group, we try to get controls, right? So the same age group, same, and we try to make as like sex, yes, the same number of male, same number of female, the same number of age and all that. So that like time matching, right? And then we can compare, right? So what are these people eating and what is these people eating, right? And then we say, is there any difference? Is there any agent in the food which actually affecting these people, right? So that's how they figure out that okay, that particular diet may be involved in maybe protecting, or so maybe they are eating something and that that particular food may be preventing them not to have cancer, right? Or these people may be doing something or eating some kind of diet which are, maybe pro cancer. Now, the other kind of studies they do is like a cohort, right? Now, this cohort can be two different kinds. It could be like prospective or retrospective, right? Prospective is forward, right? So what happens that they have, for example, there's an example like heart disease, but you can have the same thing that these people have some kind of that they have, for example, cancer, right? Okay, then you follow that how they are progressing over a period of time, right? And see what are how their diets are, right? So people who in not all these people, some are going to like die and some are not going to die, right? So then you compare that, what factors are leading, to causing the adverse, what kind of diet was, right? Okay. Other kind of like a retrospective, right? Retrospective is that you are currently has the data, right? That these people, for example, all in red, they have cancer, right? So you go back and then you see that what they ate, which led to this cancer formation. So it's like a retrospective, right? So they're going back and then figure it out what happened to them. Where in this one, they just have, they found these people, like in a group, there's some people have like maybe have cancer, some don't have cancer, and they're following both group over a period of time, saying that, how this is progressing in two particular, group, right? Okay, and the other one is a study they use is like cross-sectional study, right? In cross-sectional study, the diets of different groups of subjects are compared using the same area at a single point. So it's like a one point, they go out and then they just measure the diet of different groups, right? And then looking, what are the incidences in different groups, right? So then they're not matching age, sex, and all that. They're just going different groups. So it's like one shot, right? And what they can do is that they can follow the same group over time, right? After 1 year, after 10 years, some of these studies are done like for 25 years, right? So some of the studies for, especially done on cardiovascular, this is number one excellent, that they follow the diet, and then they follow those people, or some of the genetic studies, they follow generation to generation, right? So it's like, they call longitudinal study, right? So these are some of the epidemiological studies they use, right? No, the relationship between diet and cancer is, it is, complex. Okay, the diet actually can have carcinogen. So it's not that all the diet is safe. Whatever you eat is not really, can be, is harmful to you. Okay, sometimes they have agent which can enhance carcinogenicity, right? Sometimes they take between a latency period between initiation and promotion. Right? Like the cancer is started, right? And then some diet, once the cancer is started, some diet can actually promote this progression, right? Some diet actually can inhibit this progression. So they can increase the latency period, right? And sometimes, sorry? Oh, because okay, I'm sorry. Okay, okay, yeah. So I was just saying that the diet play a different role. So once cancer is initiated, a diet can actually decrease or increase the period from its initiation into progression, right? Slow down, right? Or diet can also promote it, like initiation, and they use it as a wrong diet, and then the period is actually decreased. Now, there are certain factors which are again comes from these studies like epidemiological studies, and what they've shown is that the energy intake in physical activity, right? So total energy intake is strongly associated with breast cancer in post-menopausal women, right? And what it means is associated when if you're taking more energy, like if you're taking food, providing more energy, and you're not doing physical activity, then it's a risk factor, right? So physical activity may have a protective effect, right? Women who spend an average of 3.8 hours per week in physical activity have lower risk of colon and reproductive cancer, right? So little bit physical activity, not very much, like about 4 hours every week, can be preventable, right? So what happens if you're taking a lot of calories, a lot of energy, so you run into risk of obesity, right? And obesity is not only that people have diabetes risk, right? Obese people often have diabetes too, but they also obesity is also a risk factor for cancer too. So a number of cancer like breast, colon, endometrium, esophagus, gallbladder, pancreas, kidney, they all kind of are linked to this cancer, right? Not only that, if a person suppose has a cancer and not controlling the diet, so and the person is cured, then the obesity can actually help reoccurring the cancer. So obesity is so maintaining a physical kind of weight or maintaining like a physiological weight is probably very helpful, right? Now, carbohydrate and glycemic index, right? So high glycemic index diet associated with increased risk of cancers, including ovarian, endometrial, breast, colorectal, pancreas, and lungs, right? Limit processed food and refined sugar, emphasize whole grain and low GI food. But high glycemic index carbohydrate means that when we eat something, right? So some of these carbohydrates, they are metabolized very quickly, and it gives you blood, a spike in blood glucose. So they are very high glycemic, right? But some fruits and vegetables, although they are high in carbohydrates, but they are slowly metabolized. So when blood glucose increases, it increases over time. So it does not really affect. And there's some example of right, high glycemic and non-glycemic foods, right? So fruits and vegetables found to associate with lower risk of about 128 of 156 studies. So a lot of studies are done, and most of these studies found that having the eating fruits and vegetables is actually helpful. Increased consumption of fruit and vegetables is associated with lower risk of cancer of oral cavity, esophagus, stomach, colon, rectum, and bladder cancer, right? Evidence is so these are the cancer, but then we have the hormone dependent cancer too. So the evidence is weak about those hormone dependent cancer because they involve a different kind of pathway. Okay, and all the fruits here is like they have agents like the phytochemical which are known to have anti-cancer activity. For example, fruits which have red color, they usually have lycopene in there, which is examples are tomatoes and tomato product, pink fruit, watermelon. Red purple color, they have anthocyanin. You guys probably know more than I do. Orange, beta carotene. And then again, so these are some example showing that we have all these phytochemicals present in different kind of food, which gives fruit a color, and that are found in that kind of fruits. Okay, and here's some example of high glycemic index. So if you can see their food, so usually the fruits and vegetables which are less than 50 glycemic index, right? They are considered as low glycemic. But if they are more than 70 or higher, they are high glycemic. So the example are when you can see here, for example, jelly beans, is 80. White bread is 80, so it's high glycemic. As soon as you take white bread, you're gonna get spike in blood glucose, right? Rice is very dangerous. Like the rice is very high glycemic. If you very spike quickly, I don't know where rice is somewhere. White rice, yeah, white rice. Actually showing low glycemic. Yeah, sorry, I'm wrong. So glycemic, but yeah, I can figure rice is actually the thing is that it's not high glycemic, but rice is 30% sugar, right? So basically, if you're eating like one plate full of rice, 1/3 is actually 30% sugar. We don't realize. So you take a lot of sugar, but it's a slow glycemic. So so you can select your food like try to get the fruit which is low in we have low glycemic index. Okay. The study have shown that people who develop cancer they tend to have low intake of raw and fresh vegetables. They don't, no, usually, then again, these are come from those studies, epidemiological studies. So it's just the data they collected, like they don't eat very leafy green vegetables. Lettuce, carrot, raw and fresh fruits are missing from their diet. Often they don't take things like cabbage family vegetables, and then there are low intake with flavonoids and lignins, since like grains, soy, and vegetables. So again, the thing is that it just shows that it just proves that people who develop cancer, they often lack all of these, right? So basically, include these in your diet, you may have some kind of protective effect. Okay. Fruits and vegetables, they are low in energy, good source of fiber, vitamins, and minerals. They have good source of antioxidants like vitamin C, E, selenium, phytochemicals such as carotenoids, flavonoids, cholesterol, helium compound, indoles, phenols, and the oil chutneys, right? So they are all antioxidation activity, right? And antioxidant activity, why we emphasize on antioxidation activity so much, right? Because the thing is that, we eat things, right? We metabolize, right? We generate a lot of reactive oxygen species, right? We have a defense mechanism where these reactive oxygen species are neutralized, right? But what happens when there is excessive generation of reactive oxidants, right? So if they're not utilized, they're very, very reactive. So they bind with DNA, they bind with protein, they bind with lipid, and then destroy the cellular structure, right? So, and then often when they react, they lead to some kind of cancer initiation, right? Because if they bind with DNA, then the mutation and all that, right? So that's why it is important to have antioxidants, right? Because you like your defense can just maintain antioxidant or activity to a certain level, right? But since we eat a lot of food and generate a lot of oxidants, right? In order to utilize, we have to have a regular intake of fruits and vegetables to prevent the accumulation of oxidants, right? Okay, so plant-based food may prevent cancers by inhibiting hormone-dependent steps in tumor formation and protecting genetic materials from carcinogenic agents, suppressing, as I said, free radical production, serving as bulking agent to dilute carcinogen, decrease gastrointestinal transcriptase, right? Stimulator of physiological active and anti-cancer enzyme. So it's all like what happens, when we eat plant diet. As I explained earlier, that there is a lot of fibers, right? You go into the stomach, okay, and then so it make you go bathroom more often. So when you go to bathroom more often, it means you are removing all the toxins, because if they stay in your gut, you have this of working from cancer, but they can be absorbed, and then they make do some changes, maybe delete DNA or something, right? So the thing is that you're limiting the exposure, right? So right, and the other thing is that they dilute in the carcinogen. Okay, so you have some food which has some carcinogen, but you have a lot of fibers. Fibers preventing the absorption. Now some of them they're going to bind the fiber and going to be removed, right? And the other thing I mentioned is the fibers are very good because what happening about bacteria, we cannot digest some of the fiber, right? But our bacteria do. So bacteria acts on the fiber and they produce this thing with small chain fatty acid, like butyric acid, right? And the butyric acid is a very strong histone deacetylation inhibitor. We talked about yesterday the histone deacetylation. They are activated during cancer, right? So they are like several advantages, right? Now preserved meat and cancer risk, like some studies link eating large amount of preserved meat increase risk of colorectal and stomach cancer, right? Preserved food like sausages, right? Bacon, they are processed, right? They are treated to stay longer, so they are not really good. The other thing is that often they are treated with some kind of compound which is nitrate in it, right, to prevent the bacterial degradation. So the nitrates is actually shown that that can be converted into carcinogen because they can the nitrate can be used to nitrosylize various proteins, and then that can be carcinogen. But it's not, they may or may not be related, but studies suggest they may be, right? Fruits and vegetables retard the conversion of nitrate into nitrosamine, right? Again, the fibers they bind in nitrate, and then it prevents their formation of nitrosamine with binding with protein, right? So cooked meat and cancer, it's like frying, broiling, grilling meat at high temperature creates chemical that might increase cancer rates, right? Cause cancer in egg. It's been proven that they cause animal cancer in animals, right? So using some other method, having a low temperature or microwaving, like for short period of time, actually is better than actually grilling. Some people really love like a barbecue, right? Barbecues is good test and all that. Anything you eat, the blackishness, right? They is really, really toxic, right? Yeah, either move it or don't eat or don't eat the grilled food. I've done an experiment where you use this sort of black stuff, right? So these are basically what they have like a lot of aryl compound, like carbon aromatic compound. They polymerize and all that. They are very, very carcinogenic. If the animals really develop it. So yeah, it just we have a defense mechanism. Some are neutralized, some are metabolized, some are get rid of it. But the thing is that if you have a again it depends. If you eat too much of it, then you're increasing the dose, right? Or you are weak, then defense mechanism weak, then you are probably is not good thing. Okay. And then food safety now, there are certain naturally occurring carcinogens like aflatoxin in peanuts, saffron in plant oils, tannin in grains and grapes, like benzopyrene formed by smoking meat and fish. Like so, there's certain food they already have carcinogen in there, like eating. So if you're eating peanuts, right? Usually they check for this peanuts. Aflatoxin is not a thing which is present in peanut, but it actually comes from the contamination from fungus, right? The fungus thing. So you have old peanuts, right? Sometimes fungus is not visible, you cannot see, but if you eat it, then the aflatoxin is a carcinogen. Right? So naturally found in plant food like celery, parsley, fig, mustard, pepper, and castor oil, right? And then again, the pesticides is one other risk factor because a lot of pesticides are used in order to save the fruits and vegetables. So that's why people are now shifting to organic farming, right? Organic, so because organic agriculture does not use pesticides. So that way, you're avoiding the pesticide. So the best thing is that whenever you have fruits, vegetable, wash it thoroughly, wash it really, scrub it to get the pesticides out. But the problem is pesticides can actually leach into the food, right? From the skin, they can go inside. You don't test it, but it's a small amount gets into there. So again, there's an advantage. If you don't use pesticide, the farmer cannot make money because half of their produce is going to be rotted. So that's how the pesticides was discovered, right? Okay, so that's about some introduction about various food. Excuse me, how actually food is can be beneficial, right, for preventing cancer, right? I showed this yesterday again that cancer is a multi-stage process, right, and it takes long time to develop. The thing is that it can be stopped at any stage. It's not that if you use cancer, it has to go all the way. Not it's just, it can be stopped, it can be slowed down. So just by changing the lifestyle, changing the diet, and the proper diet, it can be you just have a benign tumor and then it won't progress, right? But if you continue on a bad diet or bad lifestyle, for example, if you don't quit smoking, if you continue or rather increase like you one pack a day, you start having 2 pack a day, then you're just promoting some of these, speeding up some of this process, right? Oh, it's stuck again. Oops, sorry. Sharing has stopped as the share window is closed. Let me share again. Why stop?
We should really open the PowerPoint.
Hmm?
The PowerPoint, yes. We should be open the PowerPoint from here.
Oh, it's closed. Okay.
Yes.
Yeah. Then I now I open two copies.
Yeah.
Now just the mRNA one. Okay. Yeah. And then I share it.
Which we have.
Oops.
Can I just-
Oh, here it is. Yeah, thank you. Okay, thank you. Okay, sorry about that. I think somehow we lost the. Again, it's stuck. Hmm,
Knowledge?
it's not moving. I think it's maybe loading. Oh, no, it's moving.
Which slide?
I don't know. Yeah, yeah, yeah. Okay.
So.
Okay, so we were here, right? So and again, I showed you this one that it takes long time for cancer to develop. Okay, now we're going to talk about genes for cancer growth, right? So we know that we talk about oncogenes and tumor suppressor genes, right? So I don't have to repeat, right? So I'm gonna go over certain, how basically the specific mechanism, how these, the signaling mechanisms involved in carcinogenesis, and how diet can prevent it, right? So the molecular pathways for cancer prevention. Okay, so what it is, so dietary agent can suppress the transformation, hyperproliferation, invasion, angiogenesis, and metastasis of various cancers. So any process, all these processes can be inhibited by diet, right? The precise molecular mechanism of action of these compounds have not been fully elucidated, but we have data which actually suggests, that they have anti-cancer activity. And now some of these is not true, but some of the mechanism we already know that how they work. So the most common compounds and the fruits and vegetables, which is anti-cancer activity, are there has been linked to have anti-cancer activity, such as like curcumin, which is present in turmeric. Everybody knows it, right? Okay. Resveratrol present like red grapes, peanuts, and berries. Genistein is often present in soybean. Silymarin, like milk thistle, there's a plant, there's a flower. And then diallyl sulfide or SL cytosine is like indium. Allicin in garlic, lycopene, like in tomatoes. Capsaicin, red chilies, diosgenin, fenugreek, 6-gingerol in ginger, also known allergic acid in pomegranate, uracolic acid like in apples, pears, and prunes, anethol, like anise, camphor, and fennel, catechins, green tea is very effective. Has a lot of ECGC has a lot of activity, and I'll show you some of these examples. Eugenol in cloves, indole 3-carbinol in cruciferous vegetables like cabbage, limonene, like citrus fruit, beta carotene, and fibers, right? So there's all this list which has actually been shown that they have anti-cancer activity, right? Now, what happens that that all these they not only have anti-cancer activity, but they can also act on cancer stem cell at very beginning, right? So there's a big potential to include fruits and vegetables on regular basis in your diet. Okay, so how they actually work? So what is this? The diet actually regulates the intracellular signaling pathways, right? So we will go over some of these. Like they can regulate nuclear factor kappa B, right? Activator protein AP, threonine protein kinase, STATs, EGF, thyroid EGF receptors, cyclooxygenase, cyclin D, histone deacetylases, chemokine, proteasome, the BCL protein we talk about involved in hyperphosphatemia and cancer, right? So I'll go some of these examples and see to show you that how they work, right? So for example, NF-kappa B, right? The way NF-kappa B works is that NF-kappa B actually is a complex, right? So that it has two units, like 55 and 65 subunits for REL A and 50. So these two units actually they are inhibited by this protein, which is called inhibitory kappa B, right? So it's present in this cytosol, but it's an inhibitor, right? It's not active. So what happens when a growth signal comes? Right? So the growth signal activates this enzyme I-kappa B kinase, right? What it does, kinase, is phosphorylate I-kappa B. When I-kappa B is phosphorylated, it gets removed. So these two units are free now. As soon as they are free, they are active. They go into the nucleus and they have responsive element. They are region in the DNA where this NF-kappa B sits, right? So NF-kappa B are transcription factor, right? And it sit there, and when it sit there, it start promoting the gene, right? Now, NF-kappa B is one of the very, very inflammatory molecule, right? It's involved in all kind of inflammation. But inflammation can be good or can be bad, right? But if the inflammation is good in the beginning, because it's trying to get rid of infection or whatever, right? But if it's not controlled, it's continued for a long time, then actually inflammation is the cause of cancer. Okay, so and in most of the inflammation, we get activation of NF-kappa, right? So what happens to fruits and vegetables, right? So is this NF-kappa B is involved in all this process, right? It's in immortality. Like we talked about telomerase yesterday. So it's actually it activates the telomerase enzyme, and then so that become like a cell-dividing inflammation, angiogenesis, making the blood vessel metastasis, tumor promotion, proliferation, or the pathway which are anti-apoptosis. So it's still at the kind of survival path. So NF-kappa B is really a key mediator in inflammation. And whenever, I don't know how many people are involved in doing research, if you're looking for inflammation, very first thing we check is the effects of NF-kappa B, right? So basically what you do, you know that NF-kappa B is present in the cytoplasm, right? So you make the extract and you see if it is present in the nucleus. It's present in the nucleus, it means it's activated, right? Or the other way you check is you look for phosphorylation of I-kappa B. I-kappa B is present, it means NF-kappa B is removed and is active, right? So this NF-kappa B, again, we have here we have just an example I put down of curcumin. But all these, curcumin, genistein, capsaicin, resveratrol, green tea, polyphenol, they all have been shown to have some effect from NF-kappa B, right? So here is like, curcumin is inhibiting the NF-kappa B transportation in the nucleus, right? Curcumin is also, inhibiting this binding to the response element. Same as the other compounds, they do the kind of similar kind of things. All right. So now the other molecule, signaling molecule we have is AP1. Okay. Now AP1 is also a transcription factor, right? It has kind of similar mechanism. AP1 has again two units, phos and G. Okay, so these are two proteins combined together, right? And again, they are kind of present in the cytoplasm as inactive by binding to this inhibitory protein 1. Right, so inhibitory protein 1 is there, so this 3 complex is present sitting in the cytoplasm is not active, right? So then when we get a signal like the phosphoester is a very potent carcinogen. You put on your skin and the mice develop cancer very easily. So again, the mechanism is that the phosphoester protein kinase C, which phosphorylate, these proteins, right? So basically, what happens then? There's other signal, the phosphorylate the IP1, and then it gets dissociated, and then it also requires the phosphorylation of phos and Jun2. So all these enzymes can actually phosphorylate all these, and once it's phosphorylated, they go into nucleus. So AP is a complex, right? It's called AP, but it has 2, like phos and Jun, right? And it can be phos and phos, Jun and Jun, or phos and Jun. So it's like always a dimer. So it binds to the responding element. When it binds, then it's transcribed all different kind of genes, which is basically involved in cancer. Right. So that's how this AP1 works. And okay, so AP1 has been shown really in different kind of cancer. So it's all different, like it's involved in differentiation, right? In cell progression as well as in apoptosis, and it causes all kind of fibrosarcoma, squamous cell carcinoma, hepatocarcinoma, like chronic myeloid leukemia, Hodgkin lymphoma, rhabdomyosarcoma, osteosarcoma, and all that. So in proving that activation of AP1 is involved in all these kind of cancers. So again, we have food like curcumin. Again, curcumin has been shown that it directly interferes AP1 DNA binding. So here it is like I showed the example of resveratrol. So this is like AP1 binding. Like this is a DNA piece. Like it's a binding of different transcriptional factor. So what resveratrol or curcumin does is interfere with the AP binding, right? Suppress activity, resveratrol inhibit TPA, induce AP1 activation. So there's diet has shown that if you have regular use of some of these fruits kind of vegetable containing these chemicals, there is a chance that you inhibit the activity of this, right? No. And the pathway is involved is AKT or protein kinase, also known as protein kinase, right? And the way it works, and I think explained yesterday that we have growth factor, we bind to the receptor, right? And this receptor activates PI3 kinase. PI3 kinase has two subunits, like P83 and P85 and P110, right? What it does when it binds to the receptor, it converts PIP3, which is PIP2 into PIP3, right? Okay, and then when you get generation of PIP3, it actually binds with AKT. And this enzyme phosphorylate AKT, and AKT downstream is involved in cell proliferation and injuries, right? So PI3 kinase is actually on AKT is known as like oncogene. They are involved in a lot of tumors, right? Just to give you an example, that a lot of chemicals or a lot of drugs actually developed by various pharmaceutical companies just to inhibit either PI3 kinase or AKT or downstream effect of AKT through mTOR, right? So the activation of PI3 kinase is heavily involved with carcinogenesis, right? But we have number of compounds, right? For example, curcumin, ECGC, and green tea polyphenols, they have shown to inhibit PI3 kinase, either PI3 kinase or AKT activation, or both, right? For example, here I get the example of ECGC is actually inhibiting the phosphorylation of AKT, right? And ECGC also inhibiting the activation of mTOR. Whereas ECGC also what it's doing is activating P10, which actually are antagonizing the effect, right? So all these, so they are pretty effective in inhibiting PI3 kinase. So same as like the other drugs are developed. Those fruits and vegetables containing these can be used, and you can always see repetition like curcumin is pretty effective in blocking most of these pathways. Same as ECGC. So just regular using curcumin or ECGCs or green tea on regular basis can be very helpful, right? So in the pathway we have MEP kinase, right? Now the way MEP kinase work is a similar kind of mechanism but little different, right? In this case, again, we have the same thing, growth factor binding to the receptor, it activates RAS, it goes through the pathway. So RAF is also known as MEP kinase, activate. Once this gets activated, it activates MEP kinase then goes into the nucleus, bind to its responding element, and then transcribe the gene, which comes under control of MEP kinase, right? So these are all kinases involved, and there are interest again to develop inhibitor for either RAF kinase or MEP kinase or MEP kinase or MEP kinase, right? So okay, so here's this example that all these companies, pharmaceutical companies, they actually have drugs to inhibit the MEP kinase activity, right? Either upstream RAS level or kinase level, or downstream just inhibiting the enzyme activity. So there's a lot of drugs there, right? But things like curcumin, which inhibits MEP kinase, right? Indole 3 carbinol, which is present in cruciferous vegetables like like cabbage, broccoli, cabbage, that kind of stuff, right? Inhibits all different isozymes of MEP kinase, like MEP kinase 2, K3, K4, K3, like all this, right? Resveratrol is also shown to reduce the MEP kinase activity. ECGC again present in tea, inhibit the MAP kinase phosphorylation, right? Okay. And the signaling molecule we have is called STAT, right? So what STAT works is actually is used, this pathway is used by interferon, right? So when interferon binds, it activates the receptor, activate these kinase phosphorylated state. When state it gets phosphorylated, it activates the dimer, and it goes into the nucleus, again binding to interferon responding element and transcribe genes, right? So most of the mechanism is the same, it's just different molecules are involved, right? And we have again curcumin, resveratrol. Curcumin inhibit STAT3 phosphorylation, resveratrol inhibit the SRC-mediated S3 activation. Butene, which is present in cashew, suppress S3 phosphorylation, capsaicin suppress STAT3 phosphorylation, and again it's shown that some of these chemicals can be effective in blocking this pathway. Okay. Now we have growth factors like EGF. EGF is a normal protein, but when it's kind of overexpressed after mutation, it's called like HER2, or there's another name is like mu. So it can be resveratrol can actually inhibit their expression. IGF-1 insulin like growth factor 1 again is a growth factor, is involved in carcinogenesis, can be inhibited by green tea polyphenols. VEGF, we talk about vascular endothelial growth factor, which is the key factor in angiogenesis, right? It promotes the blood vessel formation. So green tea polyphenols again can inhibit the EGC expression, or EGF, which is endothelial endothelial growth factor, right? Can be inhibited by curcumin, genistein, resveratrol, and catechism. Right? So all these growth factors, they involve at some stage of carcinogenesis, and their expression can be inhibited, right? Now, one important thing is chemokine. How many people know what are chemokine? It's kind of cytokine, but it has a specific function, right? This specific function is the involvement metastasis. Yeah. So what is this chemokine? Is like you heard the name chemotaxis, right? They think that if you have attract like a chemical, it can attract the cells, right? Cell, exactly. Yeah, cell migrate towards that, that attraction. So what happens? There's certain chemokines, and they have chemokine receptor. So the chemokines receptors are, for example, expressed in cancer cell, and a tissue is making chemokine, so it means the cancer cell is going to migrate there, right? Okay, in their size, right? So that's how the metastasis happen. There's some tissues, they have ligand and all that, right? Receptor expression. So what happens then again? The thing is that you get cancer from one place. For example, you have stomach cancer. It can spread like lungs, brain, liver, bones, because of different places, right? Now the important thing is that we have like CXCL, 12. L, when it says L, it means a ligand, right? So it's a chemical which is kind of produced by tissue, right? When is R is a receptor, right? So what happens that we have the CXCR4, right? So CXCR4 is the receptor, and this for CXC is like because they have certain sequences, that's why they are giving them CXC. So this like a ligand CXCL12 bind to CXCR4, right? When it is bind to the ligand, it induce all kind of signal, right? All these pathways basically, they involve in chemotaxis. So they induce proteins which make cells to move, right? And then cell move towards where the ligand is, where the ligand either receptor is or the ligand is, right? So either cell is expressing the receptor, so it's going to move towards the ligand. If it's produce a ligand, it's going to go towards the receptor, right? So that's how chemotaxis happens, right? So again, curcumin has shown to inhibit the ligand mediated invasion and migration, right? Also reduce the CXCR4 expression. So it also reduces the expression of the receptor as well as the ligand, right? Zeromone, I think as a ginger is also again inhibit both CXCR4 and CXCL12, right? So they interfere in the metastasis process. Okay. Now, other pathway which is really involved in carcinogenesis is the cyclooxygenesis, right? you probably heard about this cyclooxygenase 2 before, because a lot of, like, you take aspirin. Aspirin indicates, ibuprofen, right? All these, they inhibit cyclooxygenase, right? Because they inhibit inflammation, right? And inflammation is involving a lot of things, like, your pain is basically mediated through inflammation, right? Swelling, redness is basically an inflammatory process. So what happens? All this happens because we have this molecule in membrane, which is arachidonic acid, right? Arachidonic acid is a fatty acid, right? But what happens? The arachidonic is the substrate of this enzyme, which we call COX-1 or COX-2. COX-1 is cyclooxygenase 1, COX-2 is cyclooxygenase 2, right? So COX-1 is always present there, right? So it's, basic is involved in, right? But what happens when there's an infection or something? Then we get activation of COX-2. So COX-2 activity is really controlled by infection or like some kind of mechanism, right? Some kind of signal, right? So when that happens, then you get generation of prostaglandin substrate like PGH2, right? And this can be actually by different kind of enzymes like leukotrienes, like they make lipoxygenase, cyclooxygenase, and hydroxygenase, right? So what it does is actually change and make sort of what, like thromboxane, prostaglandin I2, prostaglandin E2, prostaglandin T2, prostaglandin F2, and they have different kind of mechanism. Like some are involved like platelet activation, some are involved in dilating the blood vessels, so the swelling is increased. Some are actually just cause inflammation and involved in tumor formation. So basically, they're not good. They're very bad. Okay, so all the prostaglandins, they're involved in inflammation, right? So there's been a lot of attempts to block the cyclooxygenase 2, right? And once you block this, it means you're not going to generate any of this, right? And we have chemicals or compounds in diet like resveratrol, inhibit TPA-induced COX-2 expression in skin. And nitrosomethyl benzamine also died. I'm not sure which food contains this, but it uses COX-2 and esophageal cancer, right? And ECGC actually inhibits COX-2 expression. Actually, this is a chemical which causes a carcinogen, right? It's involved in esophageal cancer, which can be inhibited by basically resveratrol or ECGC. Okay. The other process, or angiogenesis. Angiogenesis again. So we talk about the cancer activation, metastasis, angiogenesis. So during what happens in angiogenesis, that we have a primary tumor, right? This primary tumor, when it becomes metastatic, it starts digesting the basal membrane, digesting the tissue, enter into the blood vessel, and it circulates everywhere, right? Some way it find a favorable condition to grow, so it goes there, right? And it starts multiplying, right? But in order to grow and survive, it has to have the nutrients, right? In order to grow. So what it does is develops a mechanism that it sends signals and grow the blood vessel, right? So it started like hooking up, like the same as that. Now, if the water is flowing and if you want water in your farm, what you do another branch to bring the water to your farm, right? Exactly the same thing. This tumor actually dig a kind of trench or a vessel, which actually draw a line and then start getting the blood to tumor, right? And getting the nutrients, right? But on this process, the most important factor is VEGF, right? It's vascular endothelial growth factor, right? It's involved in endothelial cell proliferation, right? Because the endothelial cell, these are the blood lining, with only one monolayer, right? Only one lining of endothelial cells. So they start proliferating, so they start dividing because you need the, those cells to make the channel. So these factors here, tumor usually makes VEGF, right? So it's making the growth factor, and this growth factor is going to divide the endothelial cells, and they're going to line up and make a blood vessel, right? So there are a lot of attempts to block the activity of VEGF, right? So we have, like, again, curcumin inhibits VEGF expression, ovarian and pancreatic cancer, ECGC, which is present in catechins, which is present again, green tea inhibits VEGF receptor phosphorylation, resveratrol inhibits angiogenesis, right? So all these have been, again, act through a certain mechanism. Cell cycle, we talk about cell cycle, how the cell cycle goes on, that we have this retinoblastoma protein. Once it's phosphorylated, then you get cell cycle regulation, right? So again, their products like fruits and vegetables which can inhibit this process, right? So like curcumin, resveratrol, thiocyanine, thiamoquinone, genistein inhibit cyclin D expression, right? And what happens once you inhibit cyclin D? Remember cell cycle, what happens? Kinase, yeah. So what happens, that in order for retinoblastoma protein to phosphorylate, you use cyclin and cyclin dependent kinase, right? So the thing is that in order to have cyclin dependent kinase, they actively bind to cyclin, right? So if you inhibit cyclin expression, it means the cyclin dependent kinase will not be active, right? So it won't be able to phosphorylate what? Retinoblastoma protein, right? So, and you need to have retinoblastoma protein phosphorylated in order to do the cell cycle, right? So if the retinoblastoma protein is not phosphorylated, it means retinoblastoma protein will stop cell cycle, right? So, and then again we have GSC, that's grape seed extract, reduces the expression of cyclin D1 in lung cancer, right? So that's how they control the cell cycle. Okay, apoptosis, right? So again, this apoptosis, some people call apoptosis, right? This again, depends on the part of it, what you live in. So apoptosis or apoptosis, what it is also known as programmed cell death, right? So when, for example, you're using a chemical or you're using a chemotherapy, a drug or something, right? So they send signal. This is a normal cell, right? When you get a signal that, okay, it's time to die. So what happens that it actually stimulates on some kind of pathway. So it's a program cell. It's not just that it's going to have a heart attack and die. It's just, it kind of goes through a pathway, and then, it starts, disintegrating itself, right? And then it becomes like, disintegrate, stabilize, right? So the whole this process is called apoptosis, right? But there is a mechanism, right? So what happens that we have this called like a death receptor. Okay, so the chemical comes bind to the death receptor. It induces all kind of mechanism. So one thing you can see is here called caspase, right? They are all caspase 3, caspase 9. And so what happens that these caspases are actually present in the cell, but they are present in as a procaspase form, like it's a procaspase 8, procaspase 3, procaspase 9. So when the signal comes, the caspase pro convert into the active caspase, right? And they are the proteolytic enzyme. They start cutting the proteins, right? So they're one mechanism, and the other mechanism is that when there's a DNA damage, we talk about P53, that is a sensor. So P53, what it does is make some proteins, right? Like Bex protein. Bex protein, what it does is makes holes in the mitochondria. And as we know, the mitochondria is the powerhouse of the cell, like generates energy, ATP formation. If the cell has no ATP, it's not going to function, right? Metabolically inert, right? So it makes holes in the mitochondria, so destroy the mitochondria. So all these processes actually lead to cell death, right? So again, and I'm not going to go through this, like we have curcumin, resveratrol, ECGC, they have shown to inhibit specific pathways, right, which involve in apoptosis, right? So like, for example, they downregulate the expression of apoptosis suppression protein, right? So they are like in the cell, there's an apoptotic mechanism and there's a mechanism which actually block the apoptosis happening, right? So most of the cancer cell, they produce these protein in excessive amount because they don't want to, make the cell die, right? So the cell, they want, this is called survival proteins, right? But what happens that, some of the diet, they actually reduces the expression of the survival proteins, right? Curcumin protein, it actually, causes like activation of caspase 3. Resveratrol, again, is involved in the induction of this protein, which involved in inhibition of cyclin-dependent kinase activity, right? Again, when it's inhibited, it means the cell cycle will stop, right? ECGC downregulate the NF-kappa B activity, right? And again, is also involved in expression of P21, which is again the inhibitor of cyclin-dependent kinases, right? So all these compounds can have direct effect on cell cycle, right? Diet and epigenetics, right? So that's all about how they block the signaling pathway, but actually that can directly affect the epigenetic processes too, right? And we talked about yesterday, the epigenetic processes like histone modification, DNA methylation, and microRNA. Right, so a normal cell actually can be converted into a cancer cell through these epigenetic processes, right? But diet and environment can modify this and actually prevent the conversion of normal cell into cancer cell. Right? And briefly, what happens that we have now DNA methylation we talk about, right? We have histone modification that you get histone acetylated, it opens, and you get gene which is transcribed, and these are mostly the genes which are oncogenes, right? Which involve in cancer formation. The DNA which is methylated is actually block the expression, right? And these most of the methylation happens to the tumor suppressor genes, so they do not express. That's how it's involved. And again, we have we have mRNA. So miRNA bind to mRNA and affect the transcription of protein. So all these processes they can be regulated. And I'm just going briefly again. We talk about how the DNA methylation happens. That we have cytosine, we have DNA methyltransferase, the methyl, then the cytosine on 5th position, right? So in a normal cell, what happens that these are like, for example, these are oncogenes, right? So they are methylated, so they are inactive, right? But the tumor suppressor gene, they are not methylated, so they are active, right? They are expressing, right? In cancer cell, what happens that the methylation of the oncogenes is gone, so they are active, but this tumor suppressor genes, they are methylated, so they are inactive, right? So the thing which blocking the tumor progression is not there, right? But the thing which is stimulating tumor progression is expressed. So that's how what happens between these tumor suppressor tumor oncogenes. And again, what we have in histone modification, we have histone acetyltransferases, right? Which acetylate the histones, and then we have deacetylases, right? So the acetylation is linked to the basically opening of chromatin and expression of gene, and some of genes are oncogenes, whereas deacetylation means like removing the acetyl group and DNA get condensed, right? So that's like blocking the expression, and most of the time it is block all the genes which involve with metastatic reduction, DNA repair, or tumor suppressor genes, right? And we have foods which are actually both involved in DNA methylation and inhibiting the histone modification. And there are fruits and vegetables which actually does the both, right? For tomatoes, apples, and citrus, they can actually inhibit, specifically the DNA methylation, whereas cashew, grapes, and garlic can modify the, they can act on histone modification. And then we have things like, we talk about ECGC all the time. So ECGC actually can also inhibit the process of both histone modification and DNA methylation. Okay. Just to show you, we just showed you that we have process of methyltransferases, histone acetyltransferases, deacetylases, and dietary polyphenols can act on all any of these pathways. Okay. Now, one of the important thing is that as we talk about the DNA methylation is really important, right? What happens that we have cytosine, right? It gets methylated, right? Once it's methylated, it basically most of the methylation happens as a tumor suppressor gene, right? So they're not expressed, and the mechanism is that we have this mtDNA methyltransferase. What it does is uses S-adenosyl methionine as a substrate, as a methyl donor. So methyl group from methionine moves, and then this S-adenosyl methionine is converted to S-adenosyl homocysteine, right? So methyl group is gone, it's transferred over there, right? So that's the reaction. But what happens that we have like green tea, right? And compounds which are known as catechols, right? So these the structure of catechols, and they also can go into methylation. So what happens that the catecholamine is like catecholamine methyltransferase, right? It gets also methylated, right? Uses the same mechanism. So when you have a lot of catecholamine, so it competes between DNA methyltransferases and catecholamine, right? So the problem is we have limited supplies of S-adenosyl methionine. If you have a lot of these, it means that it will be utilized for this, right? Okay, so this reaction will be inhibited, right? And not only that, we get a lot of generation of S-adenosyl homocysteine, And homocysteine is also found as strong potent inhibitor of DNA methyltransferase, right? So it means you get less methylation of tumor suppressor genes, right? That you get more expression of tumor suppressor gene. So that's how these catecholamines work. Okay. And then just briefly that diet and miRNA is actually involved in regulating all the organs, right? And then again we have mRNA, tumor suppressor RNA. We just talk about this briefly, right? Then so again, just to show you that we have a lot of all these different dietary components which actually modify both, like this is like a concluding diagram that you can modify the histone methylation, histone acetylation, DNA methylation, and they are also involved in regulating the release of miRNA, right? All this compound like vitamin D, anthocyanin, catecholamine, curcumin, choline, and all that. And I have some example too, like curcumin is shown to change the expression of 29 miRNA, right, in the pancreatic cancer, right? ECGC modulates the expression of MI16, right? ECGs also induced is upregulated by ECGC and dysregulate the anti-apoptotic protein BCL2, right? So, okay, soybean isoflavine has also has shown to regulate the expression of some miRNA. Okay, genistein is also, and then so basically we just coming towards the end. So there are certain recommendations which are recommended by different societies. This is American Institute of Cancer Research. So their guidelines is that to choose a diet rich in variety of plant-based and foods, right? And you know that how different components specifically inhibit different pathways involved in some transcription mechanism which are involved in oncogenesis, right? Eat plenty of vegetables and fruits, maintain a healthy weight, and be physically active. Drink alcohol only in moderation. That's not a problem here, I hope. Select food in low in fat, which are low in fat and salt, right? Prepare and store food safely. Okay, guidelines from American Cancer Society are almost like similar kind of guidelines. Choose foods that help maintain a healthy weight, right? When you eat away from home, choose food low in fat, calories, and sugar, and avoid large portion, right? So what happens is, just happens, of course, when you go out to a conference, you get a buffet, and then you start eating more than what you usually eat. So, I'm saying that, but I'm actually guilty of that. That when you go, you see all different kind of food, you start eating more. So again, when you stay away from home, take low, fat, calories food. Eat a smaller portion of high calorie food, and again make sure be aware that low fat or fat free does not mean low calories. It can be non-density rich, right? Substitute vegetable fruits. So if you want to have some kind of French fries, cheeseburger, pizza, ice cream, or something instead of that, maybe eat a fruit. There's a desert, right?
Can I ask?
Sure.
What do you think about the artificial sweeteners?
Oh, okay.
Do you agree, or do you have an idea about the risk of cancer?
Yeah, with artificial sweeteners, they actually there's some reports that they are actually poses threat. They're harmful. Yeah, it's only because they well, I'm trying to remember the mechanism. I read somewhere, like aspartame and all that. They interfere some of the biochemical reaction. There's an inhibitor and all that. Yeah. So the thing is that if we can avoid sugar, the thing is, sugar is now we take sweet, right? We feel happy when we take sugar and we eat, right? But honestly, it's a poison. Your body really do not need sugar, right? Who needs sugar? Because it's only taste, right? And after 5 minutes test, your body has to get rid of that sugar, right? You never heard anybody heard disease like sugar deficiency, right? Nobody gets sugar deficiency, right? Your body is capable of making sugar. You eat fat can be converted into sugar, right? You eat a lot of sugar is converted into fat. So what happens when you take sugar, like for example, if you're taking a cup of coffee or tea and you're adding 2 teaspoons of sugar, you adding 3 or 4 drops a day, then what happens? You're taking all the sugar, which you don't need only for taste, right? But your body has to get rid of it. So what it does, there are only 2 things your body can do. Take the sugar out, it goes in the liver, right? Either, the liver makes it to triglyceride, or it can go into muscle and it oxidize, right? It only goes into muscle when you are working. If you're not physically active, it's not going to go into muscle, it's going to go into the liver. And it converts into fats, right? And fat, liver does not store fat, so it goes into the adipose tissue, it's fats, and then what you get with increases, adipose tissue, and you get fatter and fatter and fatter, right? So sugar is really, and slowly, you get diabetes, obesity is a risk factor for cancer and all that. So basically, it's a slow poison, right? And if you like, if you don't, somebody have coffee, I hope you're not having sugar in it.
No, it's not sugar.
So perfect, right? I mean, I stopped taking sugar in my tea a long time ago, and actually tea tastes a lot better because you're not taking, and especially the most dangerous thing is the Cokes and Pepsi, because, in one glass, if you take the sugar out, you cannot drink Coke or Pepsi because it's a very, very bitter taste. So to mask the taste, they put sugar in. You know what? In one can, they have 9 spoons of sugar. There is a lot of sugar in there, right? So, okay, so we can stop here and we can take a break now, right? And then we can start signal transaction, right?
Good morning.
Good morning.
How are you?
Good.
Yesterday I sent you an email, but I don't know if you received it.
I don't think so.
I sent you an email. Okay, this is good.
You want me to bring it?
All of it. One second.
Iva.
Eva?
HIVA.
Okay.
Yeah.
Yeah, okay. I mean, it's just check it.
Okay, that's it.
I will check it. Okay.
Okay, I sent you all the files, almost all the files, and only
Oh.
study I didn't attach.
Okay.
لا but المفروض عندنا slide. All are asking about slides. They need the presentation.
Yeah, it's copied here, the handouts. If you have your disk or something, or they're going to email it to everybody actually.
Yes.
Yeah. So I don't have, but they will email. Yeah, they will
I
email.
want to ask you, in the previous slides, you presented as microwaving is safe procedure.
Yeah.
Is it safe? Really?
Well, there's some people really think that it's not safe. What happens that basically microwave is based on increasing the energy of water molecules, right? So water molecule excite, okay, and then it makes food hot, right? So what people think that they still, when you eat food is hot, then it's still exciting.
Yes.
So say it may not be safe because maybe interfering. So, but it's usually is regarded safer than grilling.
Yes.
Yeah. Grilling.
One more thing. Do you think that gamma radiation sterilization is carcinogenic?
Well,
By the same concept.
sterilization is not, because it kills the bacteria, and all that, right? But if you expose yourself to gamma radiation, then it's going to be dangerous, right?
But sterilization is not.
Sterilization is not, because everything is already dead. Like if you eat meat, it's sterilizing the radiation, so it's already dead.
And the radiation will not be there for a long time.
Yeah, and again, if you have excess of everything, if you excess radiation, then it might, change the structure of, some of the lipid and protein in there. Yeah. Yeah.
About the free radical.
Uh-huh.
I understood that we would some degree of free radicals to fight cancer.
Yeah.
Over excessive of antioxidant, okay, may have an antagonist effect rather than a beneficial effect.
Yeah. Well, there's the thing, free radical can cause the cancer, and you need free radicals to kill the cancer cells. Yeah. Cancer cells too. But most of the time, I think the free radicals will involve inflammation and cause the cancer, right? And then
The risk of the cancer
Yeah.
may overweigh
Yeah.
the beneficial.
and then sometime, when the cancer is there, then you need free radicals to kill the cancer. So there's some drugs which actually stimulate free radicals in the cancer cells, and then kill the cancer from free radical formation. Yeah. So yeah. But the thing is that, usually when you are healthy, then there's risk of free radical to develop cancer, right? Yeah.
Yes, generally,
Yeah.
the risk of cancer outweigh the beneficial effect of
Yes. Yeah. But that's good too. That's why unless cancer does have side effects. Yeah. Yeah, that's what the other cancer has side effects. Right? Yeah. So that's why food life is very important.
Yeah, I think the natural
Sure, sure. Yes. Sometimes the chemotherapy just have some quick and driver. My neighbor, she got leukemia, and she used to walk outside very healthy, and then nothing to the doctor. In 6 months, she got so big that she cannot get out, and then she died in 6 months. No, she was like normal, but she has some small problems. And then after 2 years later, when she died, finally her husband developed prostate cancer, right? And then the doctor said, oh, it's very aggressive, you have a very enlarged prostate, and then if you not treat it, you have only 6 months to live. And he said, no, I'm not going to take it. I'm die, right? And he survived 6 years. So your body is dependent to
Yeah.
the cancer patient prevent or stop taking the
Yeah, this is will help sometimes.
stop taking.
Sugar, social media, a way of treating.
Yeah, we depends now. I mean, teamwork is actually
Like starving cells.
yeah, starting sense. Use energy to sugar, but it also uses vitamin to make energy. So I'm just wondering if you take sugar out and start placing the protein because people is aggressive. It's very selfish. They want to steal everything from horse. So I'm not sure, if sugar is high, protein, vitamin, how because these are two things that use it, and sugar will put on it. Yeah.
So it's well boost immunity in those patients. Well boost the
Boost the immunity.
I will spend so much time.
I don't want to be around. But yes, yeah.
how we can take one of this soft coffee.
Yeah, they're going to evaluate everybody.
Yes.
Yeah.
Okay.
Yeah. Yeah, I think we can start now. All right, I think we can start now, just to save time, right? So this, like, to conclude the cancer genetics portion, right? So we're gonna switch on the new topic. The next workshop is on about signal transactions. No, you know that what signal transaction means is that and there's a okay. So signal transaction is a process by which a chemical or physical signal is transmitted through a cell as a series of molecular changes that ultimately results in a cellular response. So we have a cell, right? So cell senses something, either it senses a chemical or it senses some kind of physical stimulus or something, right? So once it's cell, so we have, that we have a cell membrane, right? We have a nucleus, right? Nucleus has of the gene, and nucleus control all the genes, control all the activity, right? So somehow the signal has to go from outside to inside, right? So that's why it's called signal transaction, because the message is transducing from outside into inside, and then cell response, depending on what kind of signal it is, right? So there are, like, various mechanism is involved. Like the first thing is that we have to have a certain receptor, right, to receive this signal, right? Once the signal is received, then there's all different kind of different pathways, right? Like, for example, if I say something to you, and I'm only one, but there's like 50 people like your class, and then 50 people are going to tell something to somebody else, it means signal is multiplied, right? It's just transducing. So that's what happened, and then different people can take a different route to explain, right? So it's the same thing. So message is going, but it can take different path, right? And ultimately lead to nucleus, right? And depending on what kind of signal it is, there's some kind of information, some kind of message that, okay, this gene needs to be transcribed, right? Or this gene needs to be not transcribed, right? So we get a flow of signal, right? So this is the whole process called signal transaction, right? So we will try to cover all that, right? So basically, I'm not sure if you see all these not, but this is, it's a very brief summary to see that what happens that, we have a ligand. So there's something which binds, right? Before, so ligand does not really, well, not in most of the cases, but in some cases, like, can enter the cell, but most of the ligand, they have their receptor, right? So there's a receptor, and there are different kind of receptor, like G protein, and we go all in detail. Ion channels like tyrosine kinase receptor, which has activity, kinase activity, and then the receptor which actually recruit a kinase, right? So there are different kind of receptor, and there's kind of signaling mechanism like GTP activation we get. So it transduce. Then we have some kind of enzyme activities like phospholipase, adenylate cyclase, guanylate cyclase, phospholipase, all there, and they generate the second messengers, small molecule. This a small molecule then activates certain enzyme, and then these enzymes lead to direct activation of like enzymes, phosphorylation, dephosphorylation, and then ultimately we get response, right? So there's all in the similar mechanism is there with tyrosine kinase that we again get activation of various enzyme, generate second, second messenger, activation of enzyme, right? That's how it's right. And some molecules which are like hydrophobic, right? Lipophilic, right? Like steroids. Okay, they can actually directly enter into the cell because they are cell permeable. So what happens that they have a receptor which is present inside. Okay, so still they have to bind the receptor, but they can enter into the cell bind to the receptor, and then both receptor and the ligand complex enter into the cell, bind to the genes, and then transcribe the gene, right? So mechanism is same, it's just a different way of doing it, because most of the ligands, they cannot enter into the cell, right? But the steroids, they can. Okay, so when we talk about, you have to have a receptor, right? To receive the signal, right? Cell membrane has a lot of protein, right? Not all protein act as a receptor, right? So in order to have a receptor, it has to have certain criteria, right? So the receptor, first thing is protein in nature, right? Not any other stuff cannot be receptor, right? It's protein in nature because they have a binding site, right? It must have a binding site for a natural life, right? Without binding, it's not going to do anything, right? Must interact with one or several effector molecules, right? So like the thing is that there's a ligand into the receptor, but it should have some binding site to the effector, so they can transduce the signal from outside to inside, right? So there's effector molecule, right? Specific substrate binding lead to function, like once you have effector molecule, you need 3 components, right? And then it induce some kind of response. It does not induce a response, there's no point, right? So why somebody's system is binding all that? So it induces a response, right? And it just follow the characteristic of substrate binding, like always time dependent, right? Okay, like binds and then it removes, not just bind and bind all the time, right? It binds and then get detached, right? Because the when it's bind, the conformation changes, and the conformation rechanges, resets, reduces the binding activity, right? Always dose dependent, right? They have like a dissociation constant. There's a concentration involved, right? You have to have certain concentration in order to have the effect, right? Usually temperature dependent. Again, is the binding characteristics, right? Usually reversible, right? It's not that it bind and then it's done all the time, right? Sometimes associated with substrate hydrolysis, right? Often regulated by cellular enzymes, right? Like the enzyme, they change the conformation of the receptors, right? Okay. Now there are different kind of receptors. They are classified, as I explained before, a receptor which are coupled with G protein, right? So most of the hormone and neurotransmitters, they use this mechanism, right? So these are known as G protein. And we're explaining what is a G protein, right? You already probably know all about it, right? Okay. Receptor with intrinsic tyrosine kinase activity, right? What it is, there's a receptor. So it's an extracellular domain, acts as a binding site, right? But the intracellular domain is a kinase activity. So this enzyme is within the receptor, right? But then there's a receptor with associated kinase activity, right? The receptor binds the ligand, but actually recruit a kinase from cytoplasm, right? On binding, right? Before that, the kinase is not there. It's present close by, but so it's kind of similar kind of mechanism, but it has like a slightly different mode of action, right? And then we have intracellular receptor, right? So there are 4 major categories of receptors. Okay, now G protein coupled receptor, we call that like the GPCRs, right? In short, right? Our largest family of cell surface receptor, right? A GPCR is a plasma membrane receptor that works with the help of G protein, right? That's why we call G protein receptor, because it always requires a G protein as an effector molecule, right? Now, G protein acts as on and off switch, right? If GTP is bound to G protein, the G protein is active, right? So what happens in order to activate GDP get displaced and GTP binds, right? Then it's become, so there's the basic characteristic, right? And this is an example of a G protein receptor. So one of the characteristics of G protein receptor is passes through the membrane 7 times, right? 1, 2, 3, 4, 5, 6, 7. Okay, so span the membrane 7 times, right? So that's how they look like, right? Okay, and then they have these loops, right? There's 1 loop, 2 loops, and there are 3 loops here. Okay, so what happens is that all G protein receptor have 7 membrane spanning region, which results in the formation of 3 loops, right? C1, C2, C3, right? Okay, the end terminal is always the extracellular side, right? And the carboxyl terminal is the intracellular, right? Okay, G protein interaction with receptor occur within the cytoplasm domain, right? So what happens is that these 2 regions, they are very conservative, so their sequence is same, right? Most of the time. Now this region is very variable, right? And because of this variability, different G protein bind. Because if it is same all the time, it means it has to bind the same G protein, right? So because of this variation, so this is the region where the G protein interacts, right? Okay, in this loop. So this loop 1 and 2, right? 1 and 2, and then in our loop 3 and 4, they are conserved, right? But they loop between 4 and 5, right? Sorry, yeah, 5 and 6, right? This is the most variable region. Okay, so this is just a simplified mechanism. Is that you have a receptor, right? And there's a G protein present, and then the enzyme. So these things has to be there in the membrane, right? Present in the membrane, but they are not interacting with each other, right? So there's no signaling, right? Signaling starts when a molecule binds to the receptor. What it does is attract the G protein. G protein binds to the receptor, and what happens is GTP is displaced by GTP. Now it is active, right? When it is active, right, it then binds to the enzyme, right? It binds to the enzyme, and this enzyme induces a cellular response. Right? So this is very simplified mechanism, right? So these G proteins, right? They look simple, but they are more complicated, right? Because they are not one molecule; they are three molecules. So the three proteins they are like alpha unit, beta, and gamma unit, right? Now, the alpha unit has a guanine binding site. So this alpha unit bind with GDP or GTP, depending on if it's inactive, bound to GDP, right? When it's active, it's bound to GTP, right? Okay. In non-activated states, occupy GTP, right? The presence of appropriate agonist hormone receptor G protein inducing a conformation change, and GTP exchanges GTP, right? Binding of GTP to alpha subunit causes dissociation of beta gamma unit complex, right? So they are present as three, the trimer, right? But once it's bound to GTP, the beta gamma dissociate, right? Okay. And then G alpha has an intrinsic GTPase activity that slowly hydrolyzes GTP into GTP. When it's hydrolyzed, then it changes the conformation again and become inactive, right? When it changes the conformation, there is exposes the binding site and the beta gamma unit bind that, and that is again an inactive complex, right? Okay, so there's again it's the same thing is explained again. We have a receptor, the G protein, and then inactive effector. What happens? The hormone is bound to the receptor, right? And then this G protein basically, once it's bound, then it is, attached to the receptor. Then GDP get released, right? And then GTP is bound, right? And then what happens? Then this GTP goes like GTP exchanges. GTP is down here, right? Beta gamma unit is released, right? These are then bind to the effector molecule, right? And then it hydrolyzes slowly, and then GTP bound again, right? So it's kind of a cycle itself. Okay, now G protein are bound to plasma membranes. Right? Now the gamma unit is regulated, whereas alpha unit is meristol related, right? So what it means is that as I said, it's bound to the membrane. So there is some kind of anchor to hold in the membrane, right? And lipid membranes, lipid bilayer, all that, right? So you need something to anchor, right? So what it uses fatty acid, right? Fatty acid hydrogen reaction, right? So the prenylate is like I don't know how many people know about cholesterol biosynthesis. Like cholesterol biosynthesis, what happens? The acetyl group join with N-acetyl group, and then N-acetyl group, and and make a chain, and then finally it gets cyclized, right? So before it gets cyclized, there's a long chain of fatty acid, right? Not fatty acid, but like a acetyl group joined together. It's very, very hydrophobic, right? So this is called a prenyl group, right? Okay, so this group is actually attached, the G protein is actually prenylated, right? So it is here, right? And same as gamma unit, right? This is meristic acid. Meristic acid again is a fatty acid, just 12 carbon atom, right? So again, they are acetylated. Okay, so they serve as an anchor, and then just the beta unit is bound to the alpha and gamma unit, right? So that's how they are hauled up in the membrane, right? Okay. So what happens? The lipid modification serve to anchor the unit to the membrane as cDNA that encode 21 distinct G protein has been grown, right? They are divided into actually 4 big families, right? We have GS, GI, GQ, G12, and 13, right? GQ, there are other members like GQ, G11 and 15, and G11 and 14 and 15 and 16, right? So they are like number of G proteins, right? And because some of these, why they are classified into different groups, right? So here is just an example that there are a number of 4 enzymes. They are associated with G protein, like GS adenylate cyclase, right? GI also adenylate cyclase, G alpha, and then the GF alpha Q with mediated with phospholipase, and G alpha T uses GLP phosphodiesterase, right? Because it's just to show you what the effector molecule, but we'll go more in detail, right? Okay. Now the beta gamma unit is a dimer, right, composed of 2 polypeptides. However, it acts functionally as a monomer, right? So they are very tightly associated, right? They don't dissociate each other. So beta gamma unit, they are together. They bound to G protein, right? When it's bound to GDP, right? But when G protein bound to GTP, they dissociate, right? But they stay together, right? So molecular cloning has identified 4 different genes for beta unit, right? So it's beta 1, beta 2, beta 3, right? So they are variable units, right? Same as the gamma units, right? There are a number of different kind of gamma subunits, which is kind of shows the specificity towards different kind of organs. Okay, so in addition to G protein itself, right, beta gamma units has now shown that they also involve in some kind of similarity, right? So their inhibition of, like they involve in inhibition of adenylate cyclase, inhibition of muscarine receptor, activation of cardiac muscarine potassium channel, inhibition of aluminum fluoride activated G alpha and PLC. These are, you probably don't know more about it because it's very old. What happened before? Like there was a mechanism they used aluminum fluoride to activate G protein. All days in the 80s and 90s. So when we use aluminum fluoride and then you get binding of GTP with the G protein, that's how it was initially started. But now nobody uses this, right? Required by pertussis toxin catalyzed by, and we talk about this activation of phospholipase A2. I mean, some maybe this name may be strange to you, but I will explain in a few minutes, right? So what happened? So we have G protein, right? Okay. Now G protein is actually ADP ribosylated by bacterial toxin. Okay, that's how different kind of G proteins were identified, right? Okay. The alpha subunit of G protein can be ADP ribosylated by bacterial toxin, right? These proteins are either insensitive or sensitive to cholera toxin or pertussis toxin. Okay. And thus can be classified cholera toxin sensitive or pertussis toxin sensitive or cholera or pertussis toxin insensitive, right? And this is very important, right? Because that's how the initially the G proteins were classified, right? So what happens that it's just an example that we have a kind of receptor, right? There's a G protein here. Okay, it's called G stimulatory, GS, right? S means stimulatory, right? Okay, so it's G alpha, but G alpha S, right? So when a ligand bind, right? So they stimulate. What it does is that they activate the adenylate cyclase. Okay, adenylate cyclase is an enzyme which makes cyclic AMP, right? So you get more production of cyclic AMP. On the other hand, your receptors, like which bind to prostaglandin E1 or adenosine, and what they do is actually the same mechanism that the G protein get activated to bind, but their activation actually leads to inhibition of adenylate cyclase, right? So this is called G alpha I, like inhibitory G protein. So, and then what it does is actually decreases cyclic AMP, right? So one signal is activating both going from G protein, but one is inhibiting cyclic AMP production, and one signal is stimulating cyclic AMP production, right? So it's G always S means stimulatory, is easy to remember, right? Now, what happens with the cholera toxin, right? So the chondrotoxin actually is adiporibosylate. Ribosylate, you know the ribose, right? That's why it's called sugar is a ribose, right? Where it is present? It's present in nucleotides, right? Ribose, right? So it's like we have ATP energy molecule which serve as a phosphate donor, right? So ADP ribosylate. So here what we have a ATP molecule, right? So this is actually like adenosine, right? Ribose, and then we have 3-phosphate. Sorry, 2-phosphate. This is ADP, right? Okay, 2-phosphate, and then we have adenosine. Sorry, this is nicotine, adenosine diphosphate, right? So this is actually NAD molecule, right? And nicotine adenine dinucleotide, right? So what happens? And this is a GS alpha, right? So the ADP ribosylation causes inhibition of GTPase activity, resulting in a persistent active G protein, right? So what happens that this is a protein, right? So the pertussis chondrotoxin, what it does is, it breaks the bond here, right? And the whole this is a ribose is transferred to the protein here, right? Ribose and 2-phosphate, right? So ADP ribose, that's why it's called ADP ribosylation, right? So now it is ribosylated, right? Once it's ribosylated, this protein is what? Permanently active, right? So that's how the chondrotoxin works, right? Because once it's active, then it's very dangerous. Nothing can stop it, right? Signal is on and on all the time. So that's why it's called GS is chondrotoxin sensitive, right? So that's how it works. And then similarly we have pertussis toxin, right? Okay, these are like the bacteria which make pertussis toxin. And then what is this is also ADP ribosylate, GI, G0, and GT, like with cysteine residue, right? Or on carboxy terminal, right? The adipocylation of carboxy terminal functionally uncoupled G protein activation catalyzed by receptor, resulting in inhibition of hormone activated pathway, right? So it's a reverse mechanism. Chondrotoxin is all activating, right? But it's the same thing, like same mechanism. We have NAD molecule, right? So this is nicotine, right? This is the adenosine diphosphate ribose, right? And then again, this is G alpha I, okay? And this is the cysteine residue, right? So again, this bond is breaking down. The nicotine is out here, right? And this adenosine diphosphate ribose is actually transferred here, right? Ribose, 2-phosphate, and adenosine, right? Adenosine. So this is ADP ribosylation. Now, when that happens, it's actually the G protein get uncoupled from the receptor. So even the receptor, the ligands bind to the receptor, right? G protein is not going to go there, right? So it's make it all permanently inactive, right? So that's how in all days that's how it decided whether the G protein are chondrotoxin sensitive or pertussis toxin sensitive. Both signals are dangerous, right? One negative protein active all the time, the other is stops signal completely.
Because it's inhibition of inhibition, so it results in
Activation of well, the thing is that now it's not going to automatically activate cyclic MP. You need GS to stimulate cyclic MP, right?
I mean
Yeah.
the GI.
Yeah,
But
GI.
It's direct to GI.
Yeah, if
GI is inhibited.
Yeah.
So then the result is from the activation.
no, the thing is inhibited is just not going to decrease the cyclic MP because in some hormones, right, require
Yeah.
decrease in cyclic MP, right? So it's not going to decrease cyclic MP, right? But if you want to have cyclic MP production, then you have to activate the adenine cyclase, right? Through GS mechanism. Yeah. It's not like reciprocal. It's just two different mechanisms. One is involved in inhibition, other inhibition. Yes, of course. Yeah. Okay. So now here's so you understand GS and GI, right? Now the end G protein is GQ, right? It does not use adenine cyclase. Both GI and GS use adenine cyclase like cyclic acid, right? Okay, it uses another protein which we call phospholipase C, right? Where it is. Okay, phospholipase C. Okay, so it's the same mechanism, ligand bind to the receptor. Okay, G protein get activated, right? This G protein comes with the receptor. GDP is displaced by GTP, right? And then what happens is then recruit phospholipase C. Okay. Now, what phospholipase C does is act on phospholipid. Okay, and then it's X on specific phospholipid, which is called PIP2, right? It's phosphatidylinositol bisphosphate, right? So the structure is like I don't know how many of you know about structure of phospholipid. A phospholipid has a glycerol backbone, right? It has two fatty acids, right? And a phosphate group and a nitrogen base, right? And nitrogen base could be choline, ethanolamine, serine, and all that, right? Okay. So, and in this case, it is inositol, right? Inositol containing 2-phosphate, right? That's why it's called bisphosphate, right? Okay. So again, this is called, glycerol backbone, 1 fatty acid, 2 fatty acids, phosphate. Okay, inositol with 2-phosphate, right? So what phospholipase C does is cut it, glycerol where the phosphate goes with inositol. So what will happen? We have glycerol, right? With 2 fatty acids, right? So we get release of diacylglycerol, right? 2 fatty acid with glycerol, diacylglycerol. The other molecule is like inositol with 2-phosphate. The phosphate which was there with glycerol comes with there, right? So it becomes like IP3, right? Inositol 3-phosphate, right? It's not a phospholipid anymore, right? It's just a inositol, which is a sugar, right? With 3-phosphate group. And diacylglycerol is okay. Now these are very important second messages, because what happens that IP3 is actually directly act on endoplasmic reticulum. There's a ranitidine receptor. There's the IP3 receptor, sorry. And then what happens that it binds to the receptor and actually moves calcium from endoplasmic reticulum into cytoplasm, right? So endoplasmic reticulum is a source where all the calcium is stored. Okay, and then it's just stored there, but it just cannot get out. There's a channel, and it goes to this channel, right? The channel only activates when IP3 binds, right? And we know that calcium is involved in a lot of protein activation, right? A lot of enzymes, they depend on calcium concentration, right? So this calcium can activate those enzymes. Now, one of the enzymes is protein kinase C, right? Now, the protein kinase C is actually require both calcium and diacylglycerol. So diacylglycerol bind to protein kinase C, right? And the calcium here, right? And get activated, right? Okay. Now protein kinase C, as the name suggests, right? Is the kinase, right? What is going to do? Phosphorylation. So it's going to phosphorylate protein, right? Now one of the things protein kinase does is it phosphorylate protein only on serine or threonine residues, right? So it's a serine threonine dependent kinase, right? Okay. So now we know that in this case, like phospholipase C is activated both by calcium and diacylglycerol, right? But now we know that there are other kind of phospholipase C too, which actually either dependent only on diacylglycerol. They do not require calcium, and there are protein kinase C which do not require diacylglycerol. They get activated by protein kinase, calcium, right? So they are all different kind of isozyme protein kinase C. But this is a very classical mechanism, right? Now those G protein which uses phospholipase C, they are termed as GQ, alpha beta G alpha. So this is alpha basically is G alpha Q, right? They're discovered specifically for phospholipase C. Okay. So anything not clear about G protein? It's pretty, simply okay. Now the second kind of receptor, we have receptor with tyrosine kinase, right? Okay, now receptor especially for growth factor, right? Differentiation factor in some hormones, like and again, most of the hormones they use this G coupled protein, right? G coupled receptor, G protein coupled receptor, right? But the growth factors, right? And the difference between the hormone and the growth factor, right? The hormone is an endocrine product, right? You know what is endocrine? Without any drugs, right? Okay. So what happens? We have in our body we have glands, right? Okay. Now some glands actually has a duct, right? So these glands, their function is to make some secretion, right? Like pancreas, right? So pancreas make pancreatic juice, right? But pancreas is a pancreatic duct, and it goes into intestine, right? So this kind of gland called exocrine, right? So they have their own duct, right? But their pancreas also make insulin and glucagon, right? Now, those insulin and glucagon actually does not come through the pancreatic, right? Rather, it diffuses out from this side, right? So they are like coming out from the gas mechanism, right? same as all other, like organs like thyroid, thyroid hormones, right? It's just diffused in the blood, right? It doesn't have a duct, right? So all the secretion which comes out from that like mechanism without any like the diffusion, they are hormones, right? Okay. Now the growth factors are a little different, right? Growth factors are basically is small than hormones, and they are just actually can produce at the local site by the cell and for the cell local cells, right? So it doesn't have to travel through blood. The hormone has to travel through blood to go like insulin, comes from pancreas, goes into the blood and actually acts on liver and muscle cell in order to transport the glucose, right? So growth factor is mostly associated with somehow growth, right? For example, IGF-1, insulin like growth factor 1, is not insulin, but its properties are same as insulin, right? Our PDGF, EGF, FGF, right? These are all growth factors, right? These growth factors, they bind to receptors, right? Those receptors have intrinsic tyrosine kinase activity, right? As they bind, they somehow activate their kinase activity, right? So what happens? The common molecular topology receptors are large glycosylated extracellular ligand binding. So they have like a big, glycosylated domain. So a lot of glucoses are, a lot of carbohydrates are present, right? Single hydrophobic transmembrane region, cytoplasmic domain that contain a tyrosine kinase activity, right? So again, transmembrane region, which is the region which goes through the membrane, and then they have a tyrosine kinase activity, right? Okay, the way it works is that when ligand bind, okay, so one ligand bind to the receptor actually is what we call cooperate mechanism that actually induces the binding of the other ligand. So this binding maybe takes little longer to bind, but once it's bind, the other ligand bind rapidly to the receptor. So it's like a cooperative binding, right? Like you probably learn about hemoglobin. Hemoglobin can bind for oxygen, but once binding is difficult, but then the second binding is quicker, and the third is more quicker, and the fourth is even more quicker, right? So they actually help induce the binding, right? So same as that. So what happens when they bind? They make a diamond. Okay, so now this is kinase domain, they get activated. So this kinase domain actually phosphorylate this, or this one phosphorylate. So they are cross phosphorylate each other, right? So they become like phosphorylated. Okay, so again, the receptor with tyrosine kinase activity can be grouped into actually or into a base class, right? Okay, on the basis of sequence similarity in distinct structure features, right? Okay, what it is the show it. Okay, so they are like classified, like some of the extracellular domain, they have two cysteine repeated regions. So this is like a cysteine rich region, one, and then the same region is repeated again, right? So a lot of receptor, like example is like EGF receptor has that kind of receptors, right? Okay, so they classify on this basis, or they have like is the cysteine region that actually linked with disulfide only, right? So this is not a part of this is the whole thing is receptor, but these chains and the chains, and then these are like what the cysteine regions linked to the disulfide bond, right? And then we have receptor group receptor, which is immunoglobulin molecule, right? This like immunoglobulin, like antibodies, like they have this specific structure, so they have like immunoglobulin like domains, right? And then we have fibronectin type structure, where the cysteine rich region, and then this also immunoglobulin, right? And then they have like all this tyrosine kinase activity in the receptor, right? So the thing is that they have like two cysteine rich repeat, right? Disulfide link tetrameric, similar to class 1, right? So heterotetrameric, remember there are 2 units and then they bind like to the 4 subunits there, right? And immunoglobulin like domain, 5 immunoglobulin or 2 immunoglobulin, but they are now we know that they are receptor with 1 immunoglobulin domain and more than 5 immunoglobulin domains, right? Okay, so this is how it looks like. So we have like ecto domain. This is the extracellular domain, right? We have transmembrane region, and then we have a cytoplasmic domain, right? And then we have the homology, which is kind of basically just where they have the kinase activity. Okay, so again, what happens? The receptor tyrosine kinase activity on activation catalyzes phosphorylation of tyrosine residues of their own cytoplasmic domain and of every oligomerized receptor as well as others, cellular proteins. So as I mentioned, right, that sometimes they share the ligand, right, and it's different way of people present. Like sometimes they one ligand is actually shared by both, like chains, right, two receptors, or they are binding to, two ligands binding to the two different receptors, and then they, come close to each other, right, and they make a dimer, or sometimes there are three receptors come together, they make a trimer or oligomer. So they kind of, they aggregate each other, right? When they aggregate, because they have tyrosine kinase activity, right? So they transphosphorylate, right? And they can transfer phosphorylate not only first phosphorylate, but one place, but they can do multiple phosphorylation. And I'll show you, this multiple phosphorylation is important because the place it is phosphorylated is dictate what next is going to bind to the place, right? It's phosphorylated to a different place, it's going to. So again, in receptor, something binds, and then that phosphorylate is like, depends on the response on a different phosphate region. Okay, so again, it just shows you like we have, the ligand is binding, right? They make a dimer, right? Dimer is going to use ATP, going to phosphorylation, right? And then this phosphorylation is going to recruit other protein, which is going to, so these like proteins are inactive, but when they bind to the, the phosphate residues, the phosphotyrosine, then they become active and they induce the cellular response. And again, depends on where they are binding. If they bind on this side, there could be one kind of cellular response. If they bind to a different region, then it could be a different kind of cellular response. Okay, so now how it works, right? Why the way it works is that tyrosine phosphorylation region of cytoplasmic domain of receptor bind to other cellular protein in SH2 domain, like domain homologous to non-catalytic region of C-SAR proton genes, and activate them by tyrosine phosphorylation, right? So what happens actually? We have a certain proteins. And there, this protein has a specific region, what we call them SH2, right? And this we call this SH2 domain because their sequence are homologous to SAR. Remember we talked about SAR, it's like oncoprotein, right? So this is SAR, is the oncoprotein, they have certain sequence, right? So those similar kind of sequences present in this protein, right? So this we call SAR homologous, domain, right? 2 and 3, right? So this SAR homologous domain, right? They have a very, very specific affinity to phosphotyrosine residues. But whenever they find the phosphotyrosine residue, the SAR2 is going to go and attach. So these are like local kind of mechanisms. They have like a specific binding site, and then when they found the phosphotyrosine, they go and they attach there, right? So then they go there, and then what happens that this protein, for example, this protein GRB, right? This is nothing. It has only 3 domains, right? SH2 domain and SH3 domain, right? So now the SH3 domain is again the SAR homologous domain, type 3. Certain proteins bind to SH3 domain, right? So it's like an putting the adapters. This bind to these SH2 domain bind to this SOS protein, right? So SOS protein actually has affinity for RAS, right? And we know that RAS is a GTP binding protein. It's a small GTP binding protein. Okay. We talk about GTP binding protein, but this small GTP binding protein is small because it has only alpha units, so it doesn't have any beta and gamma, right? And it's smaller than the alpha units is only 21 kg, right? Whereas the big protein is 42 kg, right? It's almost like half of this size, right? But the function is same because it's bound to GTP is inactive, right? And then the GTP get exchanged by GDP, it become like active, right? But it does not happen by itself, right? In the first case, in the large GTP heterotrimeric protein, only conformational change, attract GTP, right? And conformational change attract GTP, right? But in this case, they require an exchange factor. which actually induces the exchange of GTP through GTP, right? So they'll use the exchange factor. So GTP gets exchanged by GTP, right? And then, so and then what they have a hydrolyzing gap protein, right? So gap protein, so we have GEF, right? GTP exchange factor, right? And then we have gap, right? So in the first case, like the G protein has intrinsic, GTP has hydrolyzing activity, so GTP converts to GTP becoming active. Whereas in this case, G gap hydrolyzes GTP, right? And become, GTP become like GDP and it's become active. Okay, so it's a slightly different mechanism, but again the same, that GTP bound is active and GTP bound is inactive, right? Now in this case, right, like this, just giving the example, like PDGF receptor, right? When it get activated, again it's going to activate the similar mechanism that is going to be dimerized, and then kinase activity is going to phosphorylate, and you can see it's going to phosphorylate on different regions, right? Okay, like phosphorate at like tyrosine residue 579 or 581 and all that, right? Depending when it phosphorylated, it recruit a different kind of enzyme or a adapter protein. Like if it's phosphorylated, these two, this phosphate is called PI3 kinase. It's one for NCK, right? This is for GAP, NCKP, S SHIP2, phospholipase C gamma, binds here, right? Now we talk about phospholipase C, right? Remember that phospholipase C is activated by G, which one? GQ, right? Okay. All right. Okay. There's another isozyme of phospholipase, which is phospholipase gamma. Actually, it does not get activated by G protein, but is activated by tyrosine phosphorylation, right? So it's bind to the phosphor and then it get activated. Same mechanism. Once activated, is going to act on PIP2 and then make IP3 and then exactly so. That's same mechanism, right? Now here in this case, EGF receptor bind and it's going to phosphorylate tyrosine on different places, right? In this phosphorylation, I can recruit different kind of second messengers, right? Adapter proteins which will, induce the response. All right. Okay. So now, what happens during cancer, or that sometimes there's a mutation in binding site, right? So remember here the mutation, this growth factor is binding, right? Dimerize is going to that have kinase activation, right? Phosphorylate going to recruit, right? Now, so this is a normal receptor. That's what happened with ligand binding, right? But what happens is sometimes there's a mutation in the receptor, right? And it does not require ligand. It just gets activated by itself, right? So now there's a mutation and it's activated and it's like an independent firing, right? And that happens during cancer. Like, for example, HER2, like it's get mutated and then receptor is, is active, right? Okay. Now, the other thing is that we talk about, like, that the growth factor, actually difference between hormone and growth factor. Hormone is released into the blood, travels, and like the thyroid hormone has so many places to act, right? It goes to blood, goes everywhere. Insulin has lot of size to act, right? In the blood. But growth factors, it can be actually travel in the blood and goes other side, but it can actually that's on signaling, right? So what happens? The growth factor is released from the cell, bind to the receptor, and actually stimulating the cell, right? Doing some, whatever response, right? So the mechanism, what we call it, autocrine, right? So and then remember we talk about the hormones, like they are the product of endocrine glands, right? So there's an endocrine mechanism, right? So hormones act through endocrine, and endocrine is a mechanism where the product is secreted in the blood, right? And travel, right? So this is endocrine, right? Autocrine means the same cell is making and then stimulating them. So this is autocrine, right? Okay. There's another terminology which is called paracrine. Yeah, between the paracrine, just can just act locally, right? In the same tissue, right? Paracrine, outcrine, and so on, right? There's another terminology which is called gestacrine. Anybody know that gestacrine? Okay. Gestacrine is that cell actually is nothing can release out, right? If one cell has antigen, right, on surface, it bound to the other, other cell has the receptor, right? So it involves cell to cell recognition, right? Okay, so it's like, for example, antigen presenting cell and T cell, right? So macrophages present antigens, some immunology, right? So that's how what happens. Then we get infected, or macrophages process the antigen, it shows, display the antigen, and then the T cells comes and recognize, right? So the T cell has T cell receptor, and then macrophages like have antigen presenting, like the CD4 molecule and like the receptor. So they bind to each other, right? So there's interaction is called gestacrine, right? Okay. I think we already talked about, that receptor phosphorylation to RAS. So a little bit about RAS. So RAS is really a key oncogenic protein. Like we talk about it, how many, like in some cases, 90% of the cancer and pancreatic cancer, RAS activation, and RAS can be activated really just by one single amino acid, was not amino acid, one single nucleotide exchange, right? One mutation, bind mutation, right? So RAS is basically involved in activation of RAF, which is also known as MEP kinase, or MEG, which is MEP kinase, and then ERK, which is MEP kinase, and then MEP kinase is involved in a lot of activation of transcriptional factor, regulating protein synthesis and all that, right? RAS is also involved in activation of PI3 kinase, which makes PIP3. We talk about which recruit AKB, which is also known as protein kinase B. Remember we talk about protein kinase C, right? Okay. All right, and then this downstream they have already actually induce a signal which involves in cell proliferation and cell survival, right? So basically it inhibits apoptosis, right? And then RAS is also involved in the other small G proteins, and then it's involved in cell movement. Like this, so this is like Logpodia or Lamidopodia. These are the like cells. So the cell membrane, what happens is it make this finger kind of structure, and then you start moving, right? So you can actually look in the internet and see how cell moves, really crawls, right? So RAS is actually a very powerful oncogene. Okay, and then again, I already mentioned that how it is activated. The RAS, when is bound to GDP, is inactive, right? Then we have this, G protein exchange factor, which actually exchanges, displaces GDP and GTP bound, right? So this enzyme does it. Whereas in other G protein, is the conformational change makes, right? And then what happens? The GTP is actually hydrolyzed by GAP, right? Remove the phosphate, and then become like GTP is become like inactive, right? Whereas in the regular G protein, what happens? It has intrinsic GTPase activity, which hydrolyzes like GTP, right? So that's how RAS is active, right? Now, so that's all clear about the receptor with tyrosine kinase activity, right? Similar mechanism we have, but the only difference is the receptor actually provide the binding site, right? But when it binds, change the conformation, and then there's tyrosine kinase present in the cell, they come and then they attach to the receptor. Then they make a full functional receptor, right? So that's like the receptor with associated tyrosine kinase activity, right? And these are basically mechanism used by cytokine receptor. You know what are cytokines?
That cells used to communicate with each other.
Yeah, inflammatory mediator. So cytokines are mostly produced by immune cells. They are also known as interleukins, right? But they can be produced by other cells too. But they were given the names because they were produced by immune cells, right? So they're a little different. They also have growth, properties, but they have like the thing is that with the cytokines, the different cytokines can have same properties, right? Like multiple cytokines do the same thing, All right. So now, okay, there's this 6 feet of cytokine receptor, right? They have large extracellular ligand binding domain, very rich cytoplasm there, right? That's why they don't have tyrosine kinase activity. There's not much cytoplasmic there present there, right? Whereas in the growth factor receptor, we have receptor binding site which is glycosylated, but in this case, they have very large extracellular domain, right? And then the cytoplasmic tail is really very little, and then they have certain region which is like common to these receptors, but they are, they don't have tyrosine kinase, right? Okay. Now again, the many cytokine receptor consists of subunits. So as we know that they have not very long tyrosine kinase activity, so they are just receptor they bind. So what happens? They use a co-receptor. So some other protein comes and attach with them, and they are called co-receptor, right? Now the funny thing is that different receptor can use same co-receptor. Like for example, the single chain we have a protein called GP130, right? The GP130 can be used by interleukin 6 receptor, leukemia inhibitory factors, OSM, interleukin 11, interleukin 12, tropic nucleating factor, CT1, right? So all these cytokines, right? Their receptor, when they bind, they recruit GP130, right? Same as in case of IL-3, interleukin 3, interleukin 5, GA, this granulocyte, monocyte, colony stimulating factor, they share this protein which called GP140, right? So again, this is the core receptor is shared by different. That's why they have similar function, because the thing is that all these have probably similar kind of activity, right? Because they're sharing the core receptor. Same as we have share gamma subunit ligand specific, alpha, the alpha unit is specific, alpha beta is specific, but they're sharing the gamma, right? And then these are the one, and then we have the interferon receptor. They actually, they have from alpha and beta and gamma, so these chains can be, shared with each other, right? So that's how they are classified based on the sugar. And the classification is they are like type 1 and 2 cytokine receptor family, TNF receptor family, interleukin 1 receptor family, receptor tyrosine kinase family, and TGF receptor family, right? I think they don't have the tyrosine kinase activity there, but they have some other mechanism. Okay. Now the thing is that the hematopoietic cytokine family, they use this WXWS, right? So W means tyrosine, serine, and then any other amino acid, and sorry, tyrosine is and then and serine, right? So they have this particular sequence repeated all the time. So all these receptors, right, with ligands, right, they have these conserved the region, right? So in this, what happens that that the cytosine residue, right? The receptor in this family have approximately 1200 amino acid homologous region, which is characterized by 4 conserved cytosine residue, right? So these are 4 conserved cytosine residue, right? And then they have this specific particular amino acid sequence. Okay, then we have interferon receptor family. Interferon group into 2 classes, type 1 and type 2. Type 1 is actually similar like alpha and beta interferon. Type 2 is interferon gamma. Type 1 interferon binds to common receptor, the interferon receptor is interferon beta receptor. Okay, the characteristic receptor, the 2 repeated domain, each consists of approximately 200 amino acids, same as the other receptor. And 2 cysteine residues separated by 7 amino acids in the amino terminal, 2 cysteine residues separated by 20 amino acids, right? So these, they are 2 amino acid residues. The first domain are separated by 7 amino acids, and these residues they are separated by about 20 amino acids, right? Okay. So these are actually, you know, they just show you the like different. I cannot read what is. Okay, receptor family with cytosine-rich region in TNF and NGF receptors, right? So the receptor in this family have variable degrees of cytosine residue domain, each containing 6 conserved cytosine residues, right? So these are like, you know, these are the domains which repeat, right? And each has like, you know, 6 conserved cytosine. TNF receptor or alpha or beta share structure similarities and exert similar biological function. It's 2 distinct TNF receptor are input by different gene. So we have 2 different kind of receptor, like one is 55 kilodalton, other is 75 kilodalton. And there are some of the antigens, you know, they actually bind to these receptor. What happens is text. It looks like after a while you get tired and okay. So we can actually just skip some of these, you know, expressions. It's just to show that now we have, you know, a receptor which is immunoglobulin superfamily, and the structure look like this. So these have the immunoglobulins, right? On the structure, and again, you know, they have a small cytoplasmic domain. Okay, cytokine family with serine, with cytoplasmic serine threonine kinase, right? And this one is actually, instead of tyrosine kinase, they actually has the phosphatase activity, right? So, like, you know, this is the TGF receptor, and again, it's just diaperizes. It uses the chain. Like co-receptors. Okay, and then we have other big family, like they use as like GP130, the common receptor. It's just like, you know, just to show you that they are distinct family. There's nothing much into really most of them, right? Now, interestingly, the certain cytokine they use a receptor which is actually G protein, right? So you use this similar kind of G protein receptor, and the receptor is like interleukin 8, right? And it's, again, you know, is a cytokine. It's not a hormone, but is actually uses this G protein receptor in a similar way. Then we have interleukin 2, alpha beta chain, and then so these are just the receptor, right? So basically they are works very much similar, like I showed with the tyrosine kinase receptor. The only thing is that they recruit, you know, tyrosine kinase from the cytoplasm, right? And they have like a co-receptor which is shared by different, right? Now the other kind of receptor we have is ion channels, right? Okay, so what happens that when certain, you know, hormones or neurotransmitter binds, they actually open a gate, right? And the ions actually goes in, right? You can calcium ion, potassium ion, sodium ion, all that, there's specific channels. And these ions is basically with the cellular response. And after that, it kind of changes the conformation again and become closed. So it's pretty simple. These receptors they are receptor, but they are channels too, right? Okay, so they are actually different kind of ion channels, right? The ion channels, they are ligand gated, right? So, for example, a neurotransmitter bind, right? So when neurotransmitter bind, what it does is actually allows the entry of potassium ions, right? And then we have mechanical gate, right? So this again, the mechanically, you know, there's a pressure, you know, can actually can lead to the opening of ion channel, right? Some specific ion can get in, or when the pressure is gone, then it closes, right? We have channels which are always open, right? Like potassium and sodium. It depends on the gradient. So it recognizes with the that how much when sodium potassium comes in, then sodium gets out. When the sodium comes in, potassium comes out, so that they maintain the electrochemical gradient, right? And then we have voltage gated channel. Voltage gated channel is the flowing of sodium across the membrane. Is create the membrane potential, right? And then just make some kind of electric current. So these are different kind of channels, and these are different kind of receptor which are actually ion channels itself, right? Okay, and so basically just some mechanism that how the neurotransmitter works. It bind to the GABA receptors, right? And then it's the receptors get open. So what happens that the chloride comes in, sodium gets out, and then this leads to the the neurotransmission, right? Okay, it just show the how the different units acts. There's nothing really much into this. So now the voltage, at a channel again, then they are basically maintain the voltage difference, right? So that voltage difference lead to the opening and closing of the channel. So that's why leads to the movement of the sodium ions. Okay, so now the other receptors are the receptor which is present in the intracellular, right? Okay, so we talk about how the receptor bind, how the ligand bind to the receptor, right? Outside like steroids, right? Especially the enzyme, like we have the molecule which are lipophilic, like estrogens, right? Testosterone and thyroxine, right? Because the feral group says lipophilic, so they can actually enter into the cells, right? And their receptor is not present on the surface, but they are present in the cytoplasm, right? So what they happen that they ligand enter and they bind to the, once they bind to the receptor, then they transmit to the nucleus, right? And when they transmit to the nucleus, then they transcribe the genes. So they become very simple. So, for example, here is a so what is the ligand here? Glucocorticoids, right? Okay, so these are the steroids, right? So the steroids actually glucocorticoid is the glucocorticoid receptor is present in the cytoplasm, right? But it's present, it's like a receptor, right? It's not free. There's like heat shock protein 90, they bind to this one and actually make it inactive, so that it cannot enter into the nucleus, right? But what happens that when the glucocorticoids comes and bind to the receptor, right? These are released, and then the whole complex actually goes into the nucleus and start transcribing the gene, right? So this is very, kind of very efficient mechanism because it doesn't need any signaling molecule. In the other case, you need G protein activation, recruitment of another molecule, generation of second messengers, and all that, right? In this case, it just binds, goes into directly to the nucleus. That's why you heard that the steroids, people try to avoid these steroids because it's a very quick potent effect. It doesn't need very much signaling, just bind to the receptor and goes into the nucleus, right? Okay, why is stuck? Okay. Similarly, we have this receptor thyroxine, right? The hormone which are present from thyroid gland like T3, T3 bind. There's a transport system. T3 goes into the nucleus, and again, instead of the T3 receptor bind with the T3 receptors. Okay, and then this receptor actually have some other co-receptors. The protein be found, and then it goes into the nucleus, and then bound the thyroxine response element, and then start making the mRNA, right? So these are some of the intracellular receptors, and then we have what we have here is that vitamin D, Okay, so the same as vitamin D is also, water insoluble, very hydrophobic, right? So again, vitamin C can go into, then we have vitamin D receptor. So it binds to a receptor and then it recruit as the molecule RXR. It makes a transcriptional complex which goes into the nucleus and then again, start transcribing the gene, right? And then we have estrogen. So estrogen has is the similar mechanism that goes to the nucleus, bind to the estrogen receptor, right? And there are different kind of estrogen receptors, and then go to the nucleus, right? Now the interesting thing is that actually there is a intercellular and the kind of receptor which can be bound to estrogen. And then people also found that there's maybe a cellular receptor present in the membrane which can bound to the estrogen too, right? But there's all these lipid soluble compounds, they look like this. I think that's maybe the last slide. It should move. Yeah, that's the last slide. Okay. So that's all about receptors, right? What time is it? Okay. We can now. So any question so far about receptors?
But lipophilic hormones or chemicals, they also have the capability of binding to certain receptors.
Binding.
The
Sorry.
lipophilic
Mhm.
hormones also they have the capability of binding to certain receptors. Right?
To
Plasma receptors.
no.
Sometimes
Well,
they bind to.
there's like for estrogen, I heard that there's, but I did not know about other type of.
Okay.
Yeah,
Just
the estrogen, I think, yeah.
Yeah.
They found that other estrogen receptors,
I
yeah.
don't know why
Mhm.
your surface receptors for different.
Yeah,
Yeah.
that's interesting. Yeah, yeah. Um, share screen. Okay. Which one? Okay, sorry. It's time to share. Okay, so receptor. So next thing after receptor is the second messengers, right? Um, no, this no, we learned that okay, the ligand binds to the receptors, right? Okay, now and there are different other receptors, right? And that how they recruit the other molecule to actually make the signal move from extracellular to intracellular, right? Now information go to intracellular. Okay. Now it has to go all the way to the nucleus, right? In case of steroid receptor, it's easy. They can directly, once they bind, they go to the nucleus, right? But for a lot of hormones and growth factors, they need to still, get transfer the information from receptor to inside the nucleus, right? So they need some kind of messengers, right? Same as like, if you want to give a message to somebody, get somebody, and then that somebody is going to go there and then deliver the message, right? That's how the messages work, right? So there are a number of mechanisms that, they generate second messenger, right? If we talk about adenylate cyclase, right? So adenylate cyclase, it generates actually cyclic adenosine monophosphate, or we call cyclic AMP. Sorry, C is missing, right? Cyclic AMP, right? And then we have similar enzyme which we call guanylate cyclase, right? Okay, and it generates second messenger, cyclic GMP, right? So cyclic GMP is actually specifically activate protein kinase A, right? So it's different. Like we have protein kinase C we talk about, right? Activated by diacylglycerol, what other calcium, right? Okay. We talk about phospholipid, protein kinase B, right? Which is actually AKT, right? Okay, so it is protein kinase A is activated by cyclic GMP, right? Protein kinase G is activated by cyclic GMP, right? And then, we talk out briefly, but we'll go more in detail. We have like second messenger, which are derived from phospholipid, right? And then we have like calcium is also active as a second messenger, right? When I was doing, like when I was a graduate student, we only knew cyclic MP, cyclic GMP, and calcium. These are the three messengers, right? So this discovery of lipid as a second messenger is a particular new development. It came out like late 80s, early 90s, right? When they discovered phospholipid C, like G protein, they discovered that phospholipid C, it activates, it releases diacylglycerol and calcium, which activate protein kinase C. Then the people started looking for other phospholipase derived second messengers, right? So they found that okay, phospholipase A2 actually, releases arachidonic acid, right? And then phospholipase C, we already know that is produced inositol 1,4,5 trisphosphate, right? Also known as inositol trisphosphate or IP3, and diacylglycerol, right, which activate protein kinase C, right? Then phospholipase D actually make phosphatidic acid. And we go, what's the structure difference between phospholipase C and phospholipase D and A. And then we have the sphingomyelinases, right, which actually produces leucine and ceramide, which also second messenger, right? So we briefly go and see how these messengers are produced and what is their function, right? Okay, so adenylate cyclase, cyclic MP protein kinase A, right? So this is the signaling mechanism, right? So receptor mediated CMP formation, right? Membrane of 7 transmembrane domain receptor family, right? Adrenergic receptor which transduce signal through geoprotein interact with adenylate cyclase, right? And consequently modulate the intercellular cyclic NP levels, right? Okay, elevation of cyclic NP is mediated by G-alpha S. When we talk about, right, stimulator subunit of G protein, while 3 types of G-alpha subunit like G-alpha I, I2, and I are responsible for the inhibition of cyclic AMP level. When we talk about GS stimulatory, GI is inhibitory, right? Okay, so what happens? It's pretty simple mechanism. Okay, the receptor, especially like adrenergic receptor, right? Epinephrine, norepinephrine, they are very, very strong stimulant, right? Right, you know that there's a you probably heard this that people carry EpiPen, like epinephrine pen, because some people are very highly allergic, right? So they inject, as soon as they have injection, they can inject the epinephrine. So epinephrine is very fast acting. The way it acts is that bind to the receptor, again activate the G protein, get activated, right? You get cyclic MP generation, and the cyclic MP activates protein kinase A, and that which is stimulate the cellular response, right? So this is a very simplified version. I also shown you this before, that things like epinephrine, glucagon, or ACTH, acetylcholine, trophic hormone, adrenal cortex trophic hormones, right? Okay, they bind to their receptor, right? And again, they stimulate the G protein, right? They increase the cyclic AMP level. GI decreases the cyclic AMP level. Okay, now what happens? How the cyclic AMP is produced? It's produced from ATP, right? So this is the ATP molecule, adenosine, ribose, and triphosphate, ATP, right? So adenylate cyclase, the name suggests, what happens that if you go the pyrophosphate, like 2 phosphates are removed, right? So we have adenosine monophosphate, right? But this actually cyclized. So what happens? That is actually cyclized, right? So it make a bond here. So that's why it's called cyclic AMP. Okay. And then this cyclic AMP actually can be converted into AMP by this enzyme phosphodiesterase, right? So what they do is just hydrolyze this bond and it generate AMP, right? Very simple chemistry, right? Okay. So what happens? The enzyme. We're not talking about the receptor now. We're talking about the enzyme, right? So igniter cyclase, right, is a bound enzyme. So it's membrane, right, which composed of two sets of 6 transmembrane segment altering with 2 large cytoplasmic, right? So the thing is that it's just, it's a big enzyme. So it's a 6 transmembrane, and then there's a loop, and then there's a membrane, right? So this is it's not a receptor, right? It is enzyme present in the membrane, right? Okay, AC activity is regulated by specific G protein or ligand interaction with the receptor. We already know that, like 2 different isozyme of AC adenylate cyclase are known. And what happens, the cyclic AMP specifically bind to cellular kinase, which are termed as protein kinase A, right? All cyclic AMP responsive events require activation of protein kinase A. So all the reaction from cyclic AMP is going to go through protein kinase A, right? Now, protein kinase A exists as type 1 and type 2 isozyme depending on the presence of the regulatory unit. So specifically regulatory unit, R1 and R2, right? The relative amount of PK1 or PK2 is varied among tissues in other animals and also in the same tissue among different animals, right? So they function same, they both make cyclic AMP, right? Now, the structure of protein kinase. So we understand G protein, understand the adenylate cyclase is present in membrane, right? And then it interact, it produce cyclic AMP. Cyclic AMP activates protein kinase A. So how it activates protein kinase A? Now, protein kinase is a tetrameric homodimer, right? Homodimer means like it's a tetrameric, there's 4 unit, right? And so they have 2 catalytic unit and 2 regulatory unit, right? So what have we composed separate regulatory and catalytic? Catalytic units are identical in substance specificity and kind, right? Regulatory units are functionally diverse, exhibit different affinities to cyclic AMP and diversely distributed in several locations, right? So these can be similar but can be different, because there are some isozymes, right? But they are identical, right? So what happens that the regulatory units are actually bound to the catalytic units, right? And this protein kinase A is inactive, right? When cyclic AMP comes, right? So cyclic AMP actually binds to the regulatory units, right? And then when it binds, the catalytic unit get detached. Once it detaches, it has kinase activity is ready to phosphorylate the proteins. Okay, so here it is. So this again, the signal comes in. Okay, now we get cyclic AMP production, right? Cyclic AMP now receptor bind, ligand bind to the receptor, and then what have been changing, enter with the adenylate cyclase, right? Next cyclic AMP bound to the receptor with the catalytic unit. This catalytic unit, is now active in the phosphorylate a lot of proteins. Like some of the proteins are like CRAB protein, which are transcription factor, right? Okay, and then this CRAB protein recruit another binding protein, binding protein, and make a transcription factor, which is actually bound to cyclic AMP response element. And then the genes specifically depend on cyclic AMP activation there, the transcript, right? Okay, that's how it works, right? And it's just there's a similar other representation just showing that how it binds, right? Okay. It's actually the same kind of thing that this is okay. Now the only thing it's showing is that we have active protein kinase A and then active protein kinase A. Now, active protein kinase A actually is an autoinhibitor. It actually inhibits the adenylate cyclase, right? So if you have more kind of excessive general cyclic AMP, you need a signal to stop the production, right? Because there's enough cyclic AMP already produced, and there's a need more cyclic AMP. The protein kinase A goes and then stop the adenylate cyclase activity. Okay. Okay. Now, one of the mechanisms which is very, very well studied, cyclic AMP is their effects on release of blood, glucose, right? So what happens? that epinephrine receptor bind to the epinephrine bind to the receptor, activates GS, right? Generate activates nitrous cyclase. ATP is used to make cyclic AMP, right? So what happens that is just to give you that how the signal is actually amplified, that you get approximately about 20 molecules of 89-less cyclase is activated by only one molecule of epinephrine to the receptor, right? Now these 20 molecules, what they do, they convert inactive protein kinase A, right? Remember, cyclic AMP is going to bind to the regulatory unit and dissociative catalytic, right? So now you have active protein kinase, right? So what happens that one molecule is actually can activate 10 molecules of cyclic and protein kinase, right? Now this kinase, what it does is that we have phosphorylase B kinase. It's present as an inactive, and you probably heard this long time ago in carbohydrate metabolism, how the glycogen degrade, right? This phosphorylase kinase B is actually get phosphorylated by protein kinase A and is now active, right? This is like active phosphorylase B kinase, right? What is a kinase? What is going to do? There is a glycogen, inactive glycogen phosphorylase B, right? So it's going to phosphorylate this, making active glycogen phosphorylase, right? Now this going to do what is going to do is going to actually phosphorylase is going to break the glycogen and release the glucose 1-phosphate, right? Glucose 1-phosphate then actually get dephosphatase and actually get out in the blood, right? So that's how it works. So what happens that one molecule actually amplifies the signal. See how 10 molecules stimulating 100 molecules of these, 1,000 molecules of these, 10,000 molecules of this, and then you get 10,000 molecules of glucose release, right? So one classical, there's a first pathway that was studied for cyclic AMP activation, how epinephrine actually. So that's why the epinephrine is this produces a lot of glucose which is utilized to help rescue from allergic reaction, that kind of things. Okay. Now, cyclic AMP is also involved in lipolysis, right? So what happens is that again, the same mechanism, the epinephrine bind or glucagon bind to the receptor, right? Activate 89-less cyclase, make cyclic AMP, activate protein kinase A. Now, this protein kinase A actually phosphorylates this hormone-sensitive lipase, right? Because this lipase is only active when the ligand binds, right? So when it is active, it actually converts monodiacylglycerol into monoglycerides, right? Like we have triglycerides, right? So triglycerides actually hydrolyzed by ender lipase, right? And it converts to diglyceride. And diglyceride is converted to monoglyceride, right? And then we have monoglyceride lipase is converted to glycerol and fatty acid, right? So this enzyme, is also, is involved in the lipolysis and is regulated by cyclic AMP. Okay. Now, so cyclic AMP has been shown to induce all kind of processes. I just showed the example of glycolysis and lipolysis, like chemotaxis, gene expression. We already know lysozyme activation, GC activation, PLC activation, sodium potassium efflux, calcium efflux, alteration cytoskeletal components, phosphorylation of myosin light chain, right? So all these processes are mediated through cyclic AMP activation, right? Now, there are now reports that they are actually receptor for cyclic AMP. Like cyclic AMP as second messenger, but actually it can get out from the cell and bind to a cellular receptor, which they identify as like a 40 kilodalton protein. It also uses G protein and consists of various members like cyclic AMP receptor 2, receptor 3. Sorry, this is receptor 1 like 40 kD, 2 is 36 kD, receptor 3 is 64 kD, right? And receptor undergo phosphorylation leading to leading to cyclase activation, right? Signal transaction mechanism is not known, right? So cyclic AMP is generated through G protein activity, right? And again, it also acts as a ligand. Okay, any question about cyclic AMP protein kinase mediated signal mechanism? It's one of the oldest, mechanism. As I said, when I was doing graduation, We only know cyclic AMP, cyclic GMP, and calcium, right? Okay. Now, guanylate cyclase, cyclic GMP, and protein kinase G, right? So it has like very similar mechanism as what cyclic, cyclic AMP, right? Its only thing is that it makes cyclic GMP, right? And activate protein kinase G, the cyclic AMP activate protein kinase A, right? But the mechanism is a little different, but it's essentially not very different, right? So again, the same thing. We have instead of ATP, we have here is GTP. That's why it's called guanylate cyclase. The same thing that the pyrophosphate is released with guanylate cyclase. So we left with this phosphate. This phosphate, bind with this hydroxyl group like a circle, right? So this is now cyclic AMP, right? Okay, similar mechanism that this cyclic AMP can be broken down into cyclic GMP simple by hydrolyzing this bond by phosphodiesterase, right? So we have number of phosphodiesterase. There are too many, like phosphodiesterase 1, 2, 3. That then they are involved. Some acts on cyclic MP, some acts on cyclic GMP, right? Okay. Now, again is the same mechanism that we have GTP, right? Guanylate cyclase, cyclic MP, phosphodiesterase hydrolyzing like cyclic GMP dependent kinase, right? And there's cyclic GMP dependent ion channels too, right? Involved, right? You get the signaling cascade and you get some kind of response. Okay. We'll talk about this. Okay. Now, the thing is that we talk about adenylate cyclase, right? It's present in the cell membrane, right? But in case of cyclic guanylate cyclase, there are two different kind of guanylate cyclase, right? The one are localized in the cytoplasm and the other one are present in the membrane, right? So some guanylate cyclase just like a adenylate cyclase present in the membrane, but then we have other guanylate, the guanylate cyclase which is present in the cell membrane. So these are just some of the example that these has this transmembrane domain, right? And then so these are some of the hormones they bind, and then and these are like it's like the enzyme activity present in the cytoplasmic domain, and then making GTP, right? In this case, they don't have the transmembrane, right? They are present in the cytoplasm, but essentially they do the same thing. They make cyclic GMP, right? It just showed how the cyclic the cytoplasmic guanylate cyclic works. Okay, now cytosolic GC is activated by free radicals and nitro-vasodilators, right? Now membrane bound GC is activated by peptide hormones, right? Like like atrial nephrotic factor, right? Each GC is regulated by different effectors and promote accumulation of cyclic GMP in different cellular compartments, right? So here it is, right? So what happens is that we have two different, we have membrane bound guanylate cyclase. So all these hormones going to bind to the receptor, activate this membrane bound guanylate cyclase. Again, the same thing, ATP is converted into cyclic GMP, right? The other one is nitric oxide, right? Nitric oxide diffuses in this cell, right? And bound to this soluble guanylate cyclase, right? But it does the same thing, make this GMP, right? And that was really very important, right? Because there was an important the person who discovered this mechanism and actually discovered first time that a gas can be a ligand. Before that, it was hormones, peptide hormones, and growth factors, and all that was supposed to be a ligand. Now this nitric oxide is a ligand which activates in cyclic GMP, right? We get GMP production, right? And then we get a downstream mechanism. Okay. What you talk about cyclic Gs exists in two major forms: soluble, type 1 membrane by type 2. PKG is okay. Sorry, before we talk about guanylate cyclase, right? So guanylate cyclase is going to activate protein kinase G. Now, the protein kinase G is also has two different forms. One is present in the membrane because it's going to associate with the cyclic, granulate cyclic is present in the membrane. The other one is, which present in the cytosol, right? So PKG is relatively low in most tissue with the exception of lungs, cerebellum, smooth muscle, and platelet, right? Protein kinase G is negligible in liver, adipose, cardiac, skeletal muscle, neutrophil, and macrophages. Okay. PKG is relatively low in most tissue. Okay. Okay. Now, the thing is that there can be an overlap between their functions. Like cyclic GMP is produced both by nitric oxide and nucleotic peptides, like hormones, right? You get activation of cyclic soluble cytosolic cyclic protein kinase G, right? And then the function is actually involved in smooth muscle contractility. They increase the calcium, decrease phosphorylation, right? Causes smooth muscle relaxation and regulate the decrease in blood pressure, right? Okay. Whereas the other function is the activation of MEP kinase, gene expression, vascular proliferation, atherogenosis, and angiogenesis, right? So there can be different functions. One is involved in regulating blood pressure, other is in cell proliferation. They just show you the structure. Like we talk about the activation of protein kinase is a tetramer, right? And then cyclic MP bind to the regulatory unit, is the catalytic unit. Their mechanism little different, right? Protein kinase G is actually a single peptide. It's not, doesn't have, right? Single peptide chain of approximately 140 kilodalton containing both the regulatory subunit and the catalytic unit. So they're present in both, right? In most tissue, protein kinase G type 1 is present, which exists as homodimer, right? Like what homodimers means, like two single peptide, they actually attach with each other, so they are same, but they are make a dimer, right? The structure organization of PKC is similar but not identical to PKE. Contains segments and strong homology to both catalytic. Okay, the regulatory unit is like the N terminal is the regulatory unit, C terminal is the catalytic unit, and then they have a place which is called site of dimerization, right? So this site is used to recognize the other, PKG, and then dimerizes, right? Intermolecular inhibitory site of catalytic. Okay, this is very simple. Okay, so how that is regulated, right? So the thing is that, as I said, they are the dimerized, right? So this is actually is one molecule of PKG, and there's the other molecule, right? So the thing is that, like, this is blocking the catalytic site, right? So it's the molecule actually folded. Okay, so when cyclic GMP binds, it changes the configuration. So they are not dissociated, right? Because they are dimerizing. These are dimerizing, on top, and then they have the GMP binding unit, and then we have the catalytic unit, right? So what happens when GMP bind, it changes the configuration, and the catalytic sites are open, right? So the substrate can enter. Okay, when substrate can enter, then it can phosphorylate the substrate, right? So it's a little different than cyclic MP, right? Cyclic MP always simple. Let's say cyclic MP bind to the catalytic details, right? In this case, cyclic GMP bind, it changes the configuration and exposes the catalytic unit, right? And then once the catalytic units are exposed, then the substrate can enter and get phosphorylated. But they are in this configuration, it's blocking the catalytic sites. Substrate actually cannot enter. So it's just a different mechanism, but actually essentially is the same, that it generates the cyclic GMP. Just for the sake of time, I'm just skipping some slides, right? Now, mechanism of cyclic GMP action. So what cyclic GMP does is involved with like platelet aggregation, right? Cyclic GMP actually inhibits platelet aggregation. So what happens, again, the nitric oxide is generated, right? And the E nose is basically we know that it involved in muscle relaxation, right? And it also inhibits the platelet aggregation. Okay, one role of cyclic GMP is in regulating the hypertension, blood pressure, because again it has a site of action in in the smooth muscle cell. Okay, so ANP causes kidney to release. So again, instead of explaining what happens, then again this NO bind to the guanylate cyclase, make cyclic GMP, and cyclic GMP is actually involved in a number of processes like net blood flow, renin, and glomerular filtration rate, regulated blood function, and take natural the US like it's basically has to do how much water it can retain and excrete it out. So all this actually lead to and we know that kidneys are really they regulate the blood pressure, right? So that's how cyclic GMP is involved, and then and as mentioned, the cyclic GMP is also involved in ion movement, right? So for example, here, what happens cyclic GMP kinase is the phosphorylating this involved in this calcium store, which is present in the endoplasmic reticulum. Calcium gets out, right? And then this is actually coming out through the effects in from phospholipase C, right? Like I mentioned before, calcium gets out, and then what happens? This actually stimulates the movement of potassium outside, right? And so when it moves out, then more calcium gets in. So it's kind of hyperpolarizes. So it's just the role of cyclic MP in ion movement, right? So I can just skip this. Okay, now the cyclic MP is actually came into more kind of in light of Viagra's story, right? Because what happens that when they were making this drug, like it's actually giving generic name Viagra, but it's like is sildenafil is the actual compound. So what happens when they were doing clinical trials, right? That they use placebo and they use the drug, right? They get the patient, and actually the drug was designed to protect heart, right? To relax the muscles, the heart muscles, so they to prevent the heart attack, right? So what they found is that when they do a clinical trial, after the clinical trials, whatever drug you did not choose, you have to return, right? So they can count the compliance, how many people use drug and how many not use, so they can calculate it. They were surprised that all the people, and then they have done all these studies. They know that how many people are going to compliance and how many people are going to compliance. But they were surprised that a lot of people actually compliance, right? Use the drug, and a lot of placebo was returned. So they were kind of surprised that why so many people actually compliance to their drugs. So then they started interviewing, right? And then they found that the drugs actually has other functions. It relaxes the large arteries, which actually prolongs the erection. So that's how they discovered, and then it was actually designed for cardioprotective effect, but then it's sold for some other purpose, right? And the purpose is that what happens that it actually it inhibits the phosphodiesterase, right? So we talk about it with cyclic MP generated by guanylate cyclase, right? But the guanylate cyclase, cyclic GMP get hydrolyzed into GMP, right? By phosphodiesterase, right? So what Viagra does actually is a very potent inhibitor of phosphodiesterase. So what happens? The once cyclic GMP is generated, right? Is the state in cyclic GMP, right? There's a signal, off signal is off, right? Is off signal. So you have a lot of cyclic GMP generated, and you know that what cyclic GMP does is produces nitric oxide, right? The nitric oxide, nitric oxide produces a lot of cyclic GMP, right? and then cyclic GMP is involved in muscle relaxation, right? So that's how this is the signal prolongs for longer period because of the inhibition, right? Okay, so the other kind of signaling we have is calcium comodulin, like okay. Now, what happens that so we talk about protein, cyclic MP, protein kinase, right? Cyclic GMP, and the other one is the calcium, right? So what calcium does is that we know that calcium is involved in a lot of enzymatic activity, right? So how calcium works is that we generate IP3, right? Remember how IP3 is generated by phospholipase C activation, right? Phospholipase C exon PIP2 direct down into IP3 and diacylglycerol. This IP3 actually they have a specific receptor on endoplasm, sorry, on the ER, endoplasmic reticulum, right? Which is stored in calcium. So it's bind to its receptor, and then what happens that it for binding to the receptor, then it recruit this molecule which is called CAM, right? Now this CAM is actually is bind a lot of calcium, and it is actually recruit this CAM kinase, right? So this makes this complex with calcium, a lot of calcium, calcium comodulin, and calcium comodulin kinase, right? That's how it gets activated, right? Once it's activated, then it is phosphorylate glycoprotein. So here is the CAM kinase, this is phosphorylate kinase, and then sort of calcium bind, get activated, right? So that's how the calcium works. Okay, so what happens is that CAM kinase has several kinase domains. Okay, so this protein here is that's the comodulin, and then this is like the okay. So this protein is actually already phosphorylated, right? So it's the binding of comodulin alters the conformation of the inhibitory subunit that releases and activates the kinase domain, right? So it is like this inhibitory domain. So this kinase activity is kind of present in inactive form, right? So what happens then the comodulin when bind to the calcium, right? Then this is actually has the affinity and it binds to the calcium comodulin, right? And it binds the site opens, right? When it opens, then is become like is activated, is ATP to phosphorylate the other substrate, right? So that's how calcium comodulin works. And we know that how the calcium comes out. Calcium comes out from again phospholipase C activation, right? So that's the mechanism of how the calcium works. So like X is a second messenger basically. It's just a summary that the phospholipase C like PIP3 kinase IP3 release, right? And then the calcium comodulin get recruited, then activate protein CAM kinase. There are various different kind of CAM kinases which are specific substrates, right? So like CAM kinase 1 is like phosphorylate, synapsin, CAM2 multiple substrate, CAM3, EF2, CAM4 function is not known, and CAM MLC, which is myosin light chain kinase, which actually a CAM kinase is phosphorylate myosin light chain, right? So I think it is coming towards the end. Okay. It just shows you that the structure of CAM kinase is actually has several units, alpha, beta, gamma, and this is like a hexagonal, and then binding of calcium actually stimulate the binding of other calcium. So it gets that there is like a cooperative binding. Again, as I explained, and then when it binds, so what happens that it gets autophosphorylated. Okay, so when it's autophosphorylated, this how it's open is it make that structure change or conformation change is open its catalytic sites, right? And then it is able to phosphorylate the other proteins. Okay, just some kind of regulation. Now here is this so So this is like how this CAM kinase is present. So basically, it's present as a multiple protein complex, right? So it's a regulatory unit and catalytic unit, right? So it's present in the folded form. So all these are like joined together and they're present in the folded form, right? So these are not active, right? So what happens when the calcium collagen complex bind, the conformation changes, right? Now this is open, right? So all the catalytic sites are open, right? So and it's like it's can then able to catalyze the other proteins, right? So it says like it's like it's multiple subunits. There's more than I think it's like how many present? I think there's a fixed number like 1, 2, 3, 4, 5, 6, 7, 8, about like 10 or 12 subunits present. And we know the physiological effect, release of calcium inside the cell causes initiation, closure of Cormolia guard cells, inhibition of red light dependent wheat leaf plasma. Is some of the effects in plasma, and then okay. Okay, we already talked about nitric oxide and then oxide synthesis, like so. Actually, nitric oxide is also a second messenger, right? Nitric oxide is a noxious, stable, free radical gas, right? It is a major messenger molecule regulating immune function, blood vessel dilation, and serving as the neurotransmitter in the brain and peripheral nervous system. Nitric oxide activates guanylate cyclase to generate cyclic GMP, which stimulates GMP-dependent protein kinase, resulting in muscle relaxation. So, okay, how this NO2 is produced, right? So basically, we have a nitric oxide synthase enzyme, right? Mostly it comes out from arginine. So what happens that this we have this arginine molecule, right? This nitrogen is actually used to generate nitric oxide. Okay, so this oxygen is used in NADPH is actually oxidized and then donate the hydrogen to arginine. So arginine become like citrulline, right? So this is like become like two double bond and then the oxygen gets here and this nitrogen gets to the other oxygen. So one molecule of oxygen there, the other one goes to nitrogen, and we get the nitric oxide formation, right? So it's basically produced from arginine and nitric oxide synthesis is involved, right? Okay. The way it works is that again we have the arginine, peroxidine, we get citrulline, nitric oxide. This nitric oxide till it goes into the especially acts on the muscle, and then there are specific receptors. They make cyclic GMP, right? Stimulate protein kinase, and protein kinase that induces the relaxation, right? And the enzyme nitric synthase is actually activated through a signaling mechanism. Like acetylcholine is a GPC receptor, activates phospholipase C, phospholipase C IP3, which uses calcium commissioning, which involved in the activation of nitric oxide synthase, make more nitric oxide, and then causes the muscle relaxation, right? So nitric oxide is also a signaling molecule, right? So nitric oxide synthase, right, is a very labile and direct measurement. I mean, NO is a gas, right? So it's very just decomposes quickly. So it's very hard to measure the NO, right? So what happens? The generation of nitric oxide is basically measured by the nitric oxide synthase activity, right? If the activity is high, it means it's going to make more nitrogen, right? So they are like different kind of synthase, right? We have neuronal NOS or NOS, we have endothelial or ENOS, or we have macrophage like IONS, right? In brain, NOS occurs in the discrete neuronal population in cerebral cortex, hippocampus, and corpus luteum. It occurs in the neurons, right? In cerebellum, all granular cells and basket cell content and NOS. The NOS is absent, it's just some details or the mechanism. Okay, so again, it just shows, we already talked about it, how the, it's regulated through the receptor mechanism. Okay, So it's just like, how the neuronal nitric oxide works, right? So neuronal nitric oxide works, again, we have like, we have neurotransmitter like glutamate. When bind to the receptor, we get activation of kinase, right? Which actually activate N1os, right? N1s that, convert, arginine as a substrate, come to citrulline and make the, right? So this is the mechanism for NOs. We have slightly different mechanism of E, like which is present in the epithelial cell, it's actually endothelial cell, nitric oxide synthase, right? ENOs, right? Now, in this case, we have like, acetylcholine receptor, again, phospholipase C, calcium, comedulline, and then we getting where is enos here? Okay, so this actually activity enos, which is like close to the membrane, and it actually releases nitric oxide outside, right? So it's not acting inside, rather it's it's releasing the nitric oxide outside. And then we have inos, right, which is intracellular. Okay, and then again it's the same kind of thing that the receptor bind, activate the transcription factor step for transcribe the gene for inos, and then inos, this intracellular inos, which make NO, and then NOs is released out on the other tissues. So different, like we have three different kind of nitric oxide synthase, and neuronal, and then we have endothelial and intracellular, right? So they have like slightly different way of generating. Well, they generate similar way from arginine, but slightly different way of regulating it, right? And I think basically it's involved in smooth muscle relaxation. I'm trying to just prepare. Okay, so you probably know about the use of nitroglycerin. Is very effective in preventing the heart attacks, right? And the function was the same, that is basically what it does is supplies a very rapid supply of NO, right? And when the NO is come, so now when the heart, the vessels are constricting, because of the rapid generation of NO, these get relaxed, right? So you get more blood flow. Here the blood flow is restricted, but when it's relaxed, you get more blood flow coming to the heart, and there is, they can, it was able to prevent the heart attacks, right? So when people feel chest pain, that's what happens, that the arteries are constricting, and people take just nitroglycerin and then immediately get relief. Okay, there are a lot of function about enos, and then okay, we can skip all these. I think it's just okay. Now we go on different set of second messengers, right? Okay, now phospholipase drive second messenger. Now the thing is that, as I said, some of these second messengers early on we know that protein kinase A, protein kinase B, calcium, they are very classical, right? The breakthrough came when we found the phospholipase C can generate diacylglycerol, right? And then diacylglycerol is a lipid molecule. So then the whole field started, how the lipid molecule we get lipid drive second messenger, right? So the phospholipase we have phospholipase A1, A2, C, and D, right? So this is the structure of a phospholipid, right? So what phospholipid has is the glycerol. So basically CH2OH, CH2OH, and CH2OH, right? So glycerol, right?
Yes.
What happens that the first position of glycerol is attached with the fatty acid, right? Second position is attached with the fatty acid, right? Third position we have phosphate group in a base,
Yes.
right? Now, this base can be different. It can be choline, ethanolamine, serine, inositol, or glycerol, right? And based on the base, we name the phospholipid. For example, if it has choline, we call it phosphatidylcholine, right? If it has ethanolamine, is phosphatidyl-ethanolamine. If it has serine, is phosphatidyl-serine. If inositol is phosphatidyl-inositol. If glycerol is phosphatidyl-glycerol. So it's called phosphatidyl is this portion, and then the name of the base, right? Now, the interesting thing is that most of the phospholipids, they are present in membrane, right? Cell membrane. Why? Because it has a phosphate group which is polar, right? So So this is the fatty acid hanging there. This is the phosphate, and then this is the head group, right? Phospho, it can be choline, serine, whatever, right? So these are the head group. So head group can interact with water, right? And this lipid interacts with each other. So that's why the membranes are lipid bilayer, right? So the cytoplasmic region and the extracellular region, they can interact with water, and then this is this is like make a protective boundary, because these are very, very lipophilic. Nothing can enter because it will not go through the membrane, right? Unless it's lipid soluble, right? Like estrogen, we talk about estrogen receptor, lipid soluble, it can go there, right? Now, the thing is that this phospholipid is subject to action by various phospholipases, right? Now, the different phospholipases act on different places, right? Like phospholipase A1 acts here, right? Okay, so when it does act here, it's going to release this fatty acid, right? And then the rest of the structure we call phospholipid, right? For example, if it's choline, is going to be lysophosphatidyl-choline. Ethanolamine is lysophosphatidyl-ethylamine. Lyso means it has one less fatty acid, right? Okay, so we get lyso, and we get, so A1 is we're going to get free fatty acid, and we get lysophospholipid, right? Okay, now this phospholipase A2, right? Now what it does is actually remove the fatty acid on the second position, right? So still we have one, so it's still the structure called lyso, right? The only difference is phospholipase, we get fatty acid remove first position, A2 remove fatty acid on second position. So A1 and 2 generates free fatty acid, right? But they generate the other structure what we call lysophospholipid. Both fatty acid and lysophospholipid, they are second messengers, right? Now, things are a little different, and we already talked about with phospholipase C. What phospholipase C does is X here. Okay, so we have glycerol, right? And one fatty acid and two fatty acids. So it's diacyl, then diacyl glycerol, right? And then we have phosphobase, right? So basically what happens, we get a diacyl glycerol release, and then we get phosphobase, right? It can be phosphocholine, phosphatolamine, phosphoserine, or phosphoinositol, right? And specifically phospholipase C can hydrolyze any phospholipid, right? But when it hydrolyzes inositol, remember inositol present with 2-phosphate, inositol 2-phosphate, right? This phosphate, and then it's hydrolyzed here, so inositol 2-phosphate, and this one like become like 3-phosphate. This become like IP3, right? So IP3 is the second messenger, right? Okay. Now this another phospholipid is phospholipase D, right? Now phospholipase D is here, right? So what it does is just remove the free base, right? So what happens? We remove the free base. So what we have a glycerol, one fatty acid, two fatty acid, and a phosphate group acid, right? So the whole structure is called phosphatidic acid, right? Okay, so it produces phosphatidic acid, right? So phosphatidic acid is also a second messenger. Okay, so here is again shown in the structure wise. Okay, so we have the phospholipase. So this is actually this 1, 2, and 3, right? So one is fatty acid, second is fatty acid, and third is a phosphate group. And R is could be any choline, ethanolamine, or the phospholipase A2 is mostly involved in releasing the fatty acid from second position, right? Phospholipase A1 is not that important, but phospholipase A2, right? Why? Because in most of the time, the second position of the phospholipase is occupied by arachidonic acid, right? So it releases arachidonic acid, and we know that arachidonic acid is a substrate for cyclooxygenase, right? Which generates a lot of prostaglandins, right? Which is all kind of physiological activity, right? So that's why phospholipase A2 is important, and the rest of the structure for phospholipase C is basically releasing inositol 1,4,5 cis-phosphate. Again, the thing is going to act here is phosphate, and then inositol is R group is inositol. Phospholipase D is phosphatidic acid. Okay, and this is 2, and then this phosphate group here, right? This phosphatidic acid. Okay, other kind of signal molecules we get is from sphingomyelinase. Okay, now sphingomyelinase has a kind of similar structure as a phospholipid. The only thing is that it does not have a glycerol backbone, but it's a similar kind of backbone like we have this this one carbon, it is a hydroxy fatty acid, right? And the second carbon is actually it is a amino is a fatty acid. It's kind of amino group, right? It's the amino fatty acid. This is actually alcohol. So it's like CH3, CH2, 2, and OH, right? So there's alcohol group here, and then we have phosphate, and then we have most of the time we have choline there, right? So this is the sphingomyelin, right? What sphingomyelin is the same thing like phospholipase, right? So it's actually remove the phosphocholine, right? So rest of the structure, what we left is this one, right? Which is called ceramide. And ceramide is itself is a signaling molecule, is a very potent agent inducing the apoptosis. At ceramide, cell will die because it binds to the death receptor and induces the apoptotic process, right? This is ceramide, right? Now we have another enzyme which is called ceramidase. What ceramidase does is actually releases this fatty acid here, right? So we have this amino or hydroxylated kind of alcohol, which we call sphingosine, right? Sphingosine, and what happens is sphingosine is by sphingosine kinase and actually phosphorylate here, right? So you get phosphorylated, right? Now the thing is that this structure, right? Ceramide is pretty much similar like diacylglycerol because this is like huge SL chain and this is like 3 carbon, right? 1, 2, 3, right? Okay, so it's pretty much mimic the diacyl structure, right? And we get sphingosine, and remember this fatty acid phosphate. We will put a phosphate here, and this is very much similar like phosphatidic acid, right? So they're not phosphatidic acid, but they structurally they look like phosphatidic acid, and these are all signaling molecules, right? Okay, now phospholipase A1 it catalyzes the fatty acid. This is an arachidonic acid position, right? We have different kind of phospholipase, like we have secretory phospholipase and we have cytosolic phospholipase. Like the phospholipase is actually secreted out in the outside, and then we have cytosolic, right? And then these phospholipase A2 are defined in many ways. Secretory phospholipase is small protein per reactor, whereas the one which is cytosolic is a long, it's 85 kilodalton, right? Secretory is activated by calcium concentration in millimolar range, right? It's cytosolic activated by micromolar range. So it's very, very calcium sensitive inside cytoplasm, right? Secretory has no fatty acid preference in SN2 position, right? So, but the cytosolic which is present inside the cell is used as phospholipid with arachidonic acid. That's how it's the second messenger, arachidonic acid. Okay. Secretory phospholipase are mostly secreted and composed of approximately 120 amino acids containing 14 to 14 cysteine, all in disulfide pair. It's just a structure, it's not that important. I think I can skip just to save time. Okay. So activation of CL, cytosolic Pla2, it's actually activated by, for example, liposaccharides from bacteria. Okay. Platelet activating factor, bradykinin, thrombin, EGF receptor, all are implicated in the activation of phospholipase A2. And you know that all these agents they are vasodilators. They process like prostaglandin E2 synthesis. Activation of CPLA2 has been shown through G protein coupled mechanism in adrenal receptor and rhodopsin, right? Activation of CPLA2 is also regulated by protein kinase C, right? And CPLA2 activity is also stimulated by calcium. So all these, they are the mechanism. CPLA2 can be activated through a G protein mechanism, right? Or it can be activated through like protein kinase. Protein kinase phosphorylate CPLA2 will make it active, or the calcium can make it active, right? Recently, activation of MEP kinase is linked to CPLA2, and we know that MEP kinase is activated through non-receptor tyrosine kinase receptor activity, right? So that's how it can also activate CPLA2, and they all do the same thing, release the arachidonic acid, right? Now, once the arachidonic acid is released, right? So, and this is like cyclooxygenase make all kind of prostaglandins, right? Whereas lipoxygenase make all kind of leukotrienes, right? And then we have other hydroxylation and the phospholipid, right? This can actually makes a platelet activating factor, right? So both arachidonic acid and lysophospholipid, the remaining portion, right? The fatty acid here, the second fatty acid is removed. It's actually used by different enzymes to convert into platelet activating factor, right? So they both are, arachidonic acid or the leukotrienes or prostaglandins. They all have biological activity, right? Okay. Now, what happens that now we have snake venom. The snake venom is actually very rich source of phospholipase A2, right? So that's what happens that snake bite and people die because all their lipids are gone, the membrane so quickly, and then it's going to remove the arachidonic acid and then lysopia, right? Now, the arachidonic acid, we know that trombin, prostaglandin, and leukotriene get massive inflammation, and it can actually destroy the organs, right? So that's how the venom works. That it makes, it's going this massive phospholipase A2 activity. It makes all this inflammatory mediator, massive inflammation, and then organ failure, right? And it also has pharmacological effects called muscle toxicity, body toxicity, edema, and I can read. Okay, have anticoagulant effects, so blood is not going to coagulate, and platelet aggregation. So it's all this, that's how the venom works, because it makes massive inflammation. Okay. Then again, we have the other enzyme, phospholipase C. We already talked about phospholipase C. What happens that okay, so phospholipase C, what it does again, we have this glycerol molecule, right? It's one fatty acid, other fatty acid, which is anchored to kind of then plasma membrane. We have phosphate group, and then we have inositol, right? Now, this is phosphatidyl inositol. What happens that this inositol is actually phosphorylated sequentially with PI4 kinase and PIP5 kinase. So we get one phosphate group here and the other phosphate group here. So basically, this is structure of phosphatidyl inositol 4,5 bisphosphate, right? So we are simply in a PIP2, right? Now, PIP2 is actually a subset for phospholipase C, right? So what happens that it breaks down the bone from here, right? So it's cut from here. So what we left is two fatty acids with the glycerol, right? So the bone will hydrolyze here, and then phosphate is linked with there, right? So we have 1, 4, 5 tris phosphate inositol, right? Or we call it just a mouthful like inositol 1,4,5 triphosphate. So we call it one simply IP3, right? So that's what phospholipase C does. Okay. Now the thing is that then when the phospholipase C is activated, we get IP3 generation, and we know that IP3 binds to the IP3 receptor, releases calcium, right? And then we get the IP3 also involved in the release of calcium, like vibration produce side, and then other molecule is generated as and glycerol, which activate protein kinase, right? I think by now you probably all know about too much phospholipase C activated, right? Okay, this is escape. Okay. Now there are several isozymes of phospholipase C, right? We have phospholipase C, alpha, beta, gamma, and delta, right? And it just depends, where these isolated from different tissue. The only thing, to remember is here that phospholipase B is the classical one which acts with the G protein, right? Whereas phospholipase gamma is actually, it has SH2, SH3 domain. So it binds to the tyrosine kinase receptor, right? We showed before, right? And then it gets activated. Okay. And you can basically, from the slides, you can read just too much details here, there, right? Now, protein kinase C, right? So, protein kinase C is a family of, calcium phospholipid stimulated serine kinase, right? Protein kinase C is activated by diacylglycerol. We all know about this, which is generated from receptor-mediated hydrolysis of, PIP2, right? Now PKC is activated by tumor promoter, right? PMA, or we call it promoter assistant, is also known as TPA, right? These are very effective tumor promoter, and that's how the function of basically phospholipase C is discovered, because the structure of this is very much similar like diacylglycerol. So diacylglycerol, we know that diacylglycerol activate protein kinase C. So this actually also, that's how it activate protein kinase, massively activate protein kinase C, which phosphorylate out of protein, and then those involved in tumor promotion.
Are those compounds representing some of the poison?
These are they are not present. They are the synthetic compound. Yeah, they are synthetic compound. They were made for inducing the tumor. Yeah, and then they found that actually the mechanism is that they mimic the diacylglycerol structure, and that's how they work, right? Okay. Again, we have different kind of PKC, classical PKC, which is calcium and phospholipid dependent. We have new PKC, which is calcium independent, but dependent on phospholipids, or diacylglycerol. Basically, all we have atypical, which is neither dependent on calcium or phospholipid, right? So it's they have different mechanism, and then we can skip these structures. That it just shows different phospholipid structure. There's nothing really much to it. Okay. Now the thing is that the protein kinase C, we know that is activated by SARC kinases, activated by diacylglycerol, activated by calcium, right? Once it's activated, and these are different kind of isozymes, right? To protein kinase C, and they're specifically known that protein kinase A is involved in growth arrest, inflammation. B is involved in melanogenesis. Epsilon is in the hyperplasia. So different protein kinase has a different specific cellular response. Now, phospholipase D, right? So we talk about A, talk about C, and the other one is phospholipase D. Now, the phospholipase D is actually generate phosphatidic acid, right? So the interesting thing is that receptor bind, agonist, activate phospholipase D, and what happens that they generate phosphatidic acid, right? Okay. Now the thing is that we have this similar kind of mechanism that we get at diacylglycerol, right? The only difference between diacylglycerol and phosphatidic acid is only a phosphate group, right? So we have phosphatidic acid phosphatase, which actually can convert into PA into diacylglycerol, and then can activate protein kinase C, right? And then through this mechanism, right? And then there's some specific, P-phosphatidic acid itself is a signaling molecule. So we have an enzyme which called DAC kinase. So DAC kinase, what it does is phosphorylate DAC into phosphatidic acid. So these are two interconnected, right? So it's very difficult to say, because sometimes this agonist can induce the effects which can be induced by phospholipase C, right? Or this receptor can induce the effect which can induced by phosphatidic acid, because these can interconvert by phosphorylation and dephosphorylation, right? Because the only difference is the phosphate group, right? Diacylglycerol, and the third position, if it is phosphorylated, is phosphatidic acid. Okay. So now the phospholipase D, there are, again, just to show you, there are a number of different isozymes like any other thing. Okay, so in this, it's like the phospholipase D, like activated to G protein, and no, I'm just trying to say that the tyrosine kinase actually activate through ARF mechanism, can also activate protein kinase C, and what happens that the protein kinase, the phospholipase D, actually is activated by it's generate phosphatidic acid, right? so it's inactive, but it is binding with the Rho and RF kinase. These are like co-regulatory unit. So they actually bind the phospholipase D itself is inactive, right? But it binds to this, what we call make a complex with RF and Rho, and then it becomes active. And then it can hydrolyze the phosphorylation of the membrane, generate the phosphatic acid. So it's some kind of mechanism how it is regulated. Okay, you can just get the structure, activation, the function of phospholipase D, and phosphatidic acid, generation of diacylglycerol for PKC activation. So phosphatidic acid is produced, it can actually generate diacylglycerol, right? It can activate protein kinase, generation of lysophosphatidic acid and arachidonic acid. It's actually activate PKA, phospholipase A2, which can release the arachidonic acid and lysophosphatidic acid. Involved with activation of kinases, translocation of RAF1, and activation of NADPH oxidase complex. Actually, this is a well-known mechanism where phosphatidic acid is involved in the oxidative burst. Okay, so therefore I was talking about that on one hand, we are getting activation of phospholipase D, right? We're getting generation of phosphatidic acid. On the other hand, from phospholipase C, we're getting generation of diacylglycerol. Now, these from diacylglycerol kinase can be converted to phosphatidic acid, and then phosphatidic acid can be converted into diacylglycerol from phosphatidic acid phosphatase, which is also known as ligands, right? Now, phosphatidic acid itself is a signaling molecule, which induces a lot of activation of this protein. Diacylglycerol, protein kinase C, and other proteins, can be activated by diacylglycerol, right? And the thing is that because these are interconvertible, so sometimes this pathway can activate this, or this pathway can lead to activation of this, because they can be interconverted. Okay, now the last one is sphingomyelin. I hope you guys are not getting too tired. Sphingomyelin. Now we talk about sphingomyelin. So it has a structure which is very much similar, like excuse me, like phospholipid, right? So sphingomyelin is primarily concentrated in the outer leaflet plasma membrane. It's composed of a long chain sphingosine base, right? Which we call sphingosine, right? And a fatty acid and phosphocholine. Sphingomyelinase causes hydrolysis of sphingomyelin and produces ceramide. And phosphocholine, ceramide is structurally resembled to diacylglycerol, that we talk about, right? Where the ceramide 1-phosphate is structurally resembled to phosphatidic acid. Okay, so that's what happens. So the sphingomyelinase is actually the sphingomyelin is present in the membrane, right? Sphingomyelinase hydrolyzes sphingomyelin, generates the ceramide. A ceramide itself is a second messenger, and it activates all these molecules, which is kind of component of MAP kinase pathway. It also acts on NF-kappa B, I-kappa B, right? And then activate NF-kappa B and induce like a kind of inflammatory response. Okay. Now the thing is that all these things are interconnected. Like so, we have sphingomyelinase coming into ceramide, right? And the ceramide can be converted into sphingomyelin or sphingomyelin synthesis, right? When a ceramide does break down ceramide into sphingosine, right? Sphingosine is actually phosphorylated, like sphingosine 1-phosphate, which has a kind of structure resembled to phosphatidic acid, whereas the sphingosine 1-phosphate lysate is actually releases the ethanolamine phosphate and then basically this is a like aldehyde group, right? So this is the whole pathway. But all these agents, like you talk about ceramide, sphingosine, and sphingosine 1-phosphate, they are signaling molecules. They bind to the other proteins and activate certain kinases or phosphatases. Right now, the interesting thing is that the sphingosine 1-phosphate is actually also a ligand. So once it's produced, it gets out of the cell, and there is specific receptor like sphingosine phosphate, sphingosine phosphate receptor 1, P1, P2, P3, P4, P5, and they actually link to certain G proteins. And these G proteins are then have some kind of response, like in cell migration, proliferation, lymphocyte trafficking, cardiac impulse generation, in conduction, vascular permeability, inflammation, fibrosis, right? So it's frequency 1-phosphate is a very potent signaling molecule. So it's a signaling molecule as well as a ligand, right? It is generated as a signaling molecule, but when it comes out from the cell, it has its own receptor and causes all this kind of signaling. Okay, I think that's about it. So we can stop here and then I hope it's not too much to. Don't have to remember, it's just to give you an idea about the overall big picture of signal transduction mechanism, right? So we talk about all, like, what are, all the second messengers. So you don't have to remember, but at least you have the knowledge. So whenever you're doing research and all that, then you can, we can come back to you, oh, this is a signaling molecule and this is the pathway. And you can always go back and learn more about it. But then it's just give you some kind of introduction about, like a very big picture of signal transduction. So should we stop now? What time is it? Okay, it's almost 1 o'clock, right? No, not 1 o'clock, it's 1:45, 12:45, right? So the only thing remain is the signal transducer, like how we already talked about most of it, but we go over again, right? Okay, so we're gonna take a break now. So we do meet like 2 o'clock or 11:30 or 1:30, depends. What time?
Conductor Ahmad, that there is event.
What is it?
An event.
I think it's a lunch.
Studying
Oh.
distributing the
1 o'clock.
Yes.
Ah. Okay. We can go a little bit on, we can continue till 1 o'clock if you want. Let me share. What is this? Okay. Okay, so that's so we talk about mostly things which are generated through G protein receptors, right? Like adenylyl cyclase. We talk about guanylyl cyclase, calcium, and then talk about single molecules which are derived from activation of phospholipids, right? So what are those? Right? They are handful like diacylglycerol, right? Which are arachidonic acid, which is used to generate the prostaglandin, prostacyclin, leukotriene, and all that, right? And then what else we get? The phospholipase A, or phospholipase A2, phospholipase phospholipase 3 generates what? Diacylglycerol and IP3, right? Diacylglycerol activate protein kinase C, right? And IP3 causes calcium mobilization, right? So that's that pathway, right? And then we have phospholipase D, right? Which generates what? Phosphatidic acid, right? And phosphatidic acid can be interconverted into diacylglycerol, right? And then we do this thing, right? And then the other phospholipid we have is sphingomyelinase, right? Which acted by sphingomyelinase and generated by ceramide, right? And ceramide can be broken down into sphingosine, right? And it's phosphorylated into sphingosine 1-phosphate, right? So it's sphingosine 1-phosphate, sphingosine and ceramides, they are all signaling molecule, right? Second messenger, right? but especially sphingosine 1 phosphate can be a ligand, right? It comes out from the cell, and there is specific receptor for sphingosine 1 phosphate, and then they use G protein in order to do the cellular induction, right? Okay, so these are all like things related to G protein, right? The other signaling molecule we have is basically are utilized by growth factors and trophic factors, right? So these are small peptide or proteins growth factors, right? And so they interact specifically with the receptor on the cell surface, secreted by multiple cell types. Most are secreted by inactive precursor that need to be cleaved or fragmented before they can act. Some are plasma membrane bound, found in the extracellular matrix. And so this is just the introduction. We just go to signaling, right? So what are those growth factors, right? We have a number of growth factors, right? For example, we have epidermal growth factor, EGF, and we have insulin-like growth factor, IGF, platelet drive growth factor like PDGF, hepatocyte growth factor, SGF, fibroblast growth factor, FGF, vascular endothelial growth factor, VEGF. We have tumor necrosis factor, TNF, and we have transforming growth factor, TGF, right? Now, as the growth factors, they're giving the name on their cells, you can easily understand, what their function is. Like for epidermal growth factor, it's acts on the epidermis, right? Or on the epithelial cells. It's also known as epithelial growth factor, right? So it's basically the activation may cause carcinoma, right? Epithelial proliferation, right? Insulin-like growth factor, as the name suggests, it's an insulin-like, right? So most of the function this growth factor has is what insulin also does. It does not really do acts on glucose transport. Like insulin main function is to move the glucose from blood into the tissue, right? Through insulin receptor, right? But the effect of insulin is on growth, right? So it's an anabolic hormone. So IGF-1 is also does the anabolism, right? And the thing is that IGF level is actually associated with the growth. Generally, people who are tall, they have high IGF level because it stimulates their growth. People who are dwarf, actually they have very low level of IGF, right? So IGF level actually determine how tall one person can be, right? But excessive production of IGF-1 is linked to certain cancer, right? Because it also has a growth potential, right? Increases proliferation, right? Hepatocyte growth factor, again, is involved in hepatocytes, in liver cells growth. Fibroblast growth factor, name says like, induces fibroblast growth. Vascular endothelial growth factor, again, is involved in the endothelial cells, right? And the endothelial cells are the cells which make the bloodline, right? So that's why it's called vascular, because what it does is induces involved with angiogenesis. Proliferate endothelial cells, and the endothelial cells make the blood lining, right? Tumor necrosis factor, TNF, and actually is a factor which causes necrosis in tumor, right? So it's actually is causes apoptosis. So all these factors, other factors, are actually causing cell proliferation, and it causes apoptosis, right? And they go into negative direction. And then we have transforming growth factor, right? Now the transforming growth factor is also does not induce cancer, right? Is an anti-cancer agent, right? What it does is induces differentiation, right? So the cell differentiate, it cannot divide, right? So that's how it inhibits, the cancer formation, because differentiate the cell, and they're not going to go big, right? Now, we talk about already this, that we have receptor tyrosine kinase, right? We have tyrosine kinase which are associated, with receptor, and then we also have the tyrosine like receptor like tyrosine phosphatase, and we have receptor with serine threonine kinase, right? So early on we talk about the receptor which has tyrosine kinase activity, right? And the receptor which actually recruit tyrosine kinase, right? But we also have receptor which has phosphatase activity. And then we talk about briefly, that one. And then we have receptor with tyrosine serine activity, right? So the function of these growth factors are basically the induced proliferation, differentiation, chemoattraction, cell death, and migration, right? Okay. they're in vivo, they are involved in early development, tissue differentiation, wound healing, tissue repair, immune response, and stromal mediator of sex and other hormones. Okay, now the receptor tyrosine kinases, right? We already talked about that. What happens that they have a extracellular domain, right? And then the transmembrane domain, which is present in the membrane. And then they have a large cytoplasmic domain, right? Now, this cytoplasmic domain, they have kinase activity. Okay, now, so this is basically a structure of EGF, right? Okay, if it and when if it is an epithelial, growth factor, right? Receptor, right? Now the thing is that the elder, it's become like oncogenic, right? So what happens that there's this is a proton, it's a oncogene, right? Which is coding the same kind of receptor. The only thing is that is the cytoplasmic domain is missing. I mean, not cytoplasmic, the extracellular domain is missing, right? So this receptor actually does not require ligand binding. Like this requires EGF to bind to the EGF receptor, right? So it's an oncoprotein. So ERP2 in a number of cancers it is expressed, right? And what happens is this is constitutively active. It's active all the time because it's basically the extracellular domain is clicked off and the receptor is self-active. So any it's kinase activity active, so it's like involved in oncogenesis, right? Now, so the thing is that there are the number of growth factors, and they use receptors. Like for example, we know that epidermal growth factor uses an EGF receptor, insulin uses insulin receptor, insulin like growth factor, there's IGF receptor, and then we have nerve growth factor, which is use a receptor which is called TRKA, right? Platelet drive growth factor is a PTGF receptor, and MCSF receptor, fibroblast growth factor uses fibroblast growth factor receptor. So there's specific receptor, and then vascular endothelial growth factor uses VGF receptor. Right? Now, all one thing common is that this all receptor has tyrosine kinase activity. Right? Okay. We can talk about that, they are classified into different classes, right? They have like some receptor, the cysteine repeats, right? And then like insulin receptor, insulin IGF receptor, they have similar structure that they have this cysteine regions which are held together by this disulfide bonding, right? So it's like a tetramer. So it's like a two molecule and two here, right? So this is receptor is a tetramer. And then we have receptor which has like immunoglobulin domain, right? And then we have receptors with the all of immunoglobulin domain, but different kind of domains. Like one has 1, 2, 3, 4, 5. Like they have multiple domains. Okay, we talk about we've already gone through that how they get activated. The ligand binds to the receptor. We bind it dimerizes, right? When it dimerizes, then tyrosine kinase activity, it get activated, and they autophosphorylate. So this, kinase is gonna phosphorylate this one, and this gonna phosphorylate this one. So they cross phosphorylate the receptor, right? Once they get phosphorylated, okay, then there are specific proteins which has the binding affinity to phosphotyrosine. So these molecules, like they come and dock there, and then as we mentioned earlier, that depending on the position of phosphorylation, there we get the different kind of set of protein bind, right? For example, it's phosphorylate here, protein 1 come here and bind only. It cannot bind here, right? Protein 2 will bind only when this is phosphorylated in this position, right? Protein 3 will bind only when it's phosphorylated in this position, right? So they have very specific, binding. Some of the examples are like, like phospholipids C, SAR, L3 kinase. They all have different, binding, right? And the binding is actually takes place because they have this SH2 or SH3 domain, right? So SH2 domain, as I explained, is a SAR homology domain, right? And this domain has specific affinity for phosphotyrosine. Whenever it sees a phosphotyrosine, it goes in dock there. So all these protein has this SH2 domain. Right. So again, we have receptor, we have receptor kinase. So adapter protein binds and recruit the enzymes, right? It's just a simple like. Okay. So again, as I said, that this is an example of PDGF receptor, right? So PDGF bind to the receptor, and there is phosphorylate in different position, right? So like tyrosine phosphorylation 740, which is by and tyrosine phosphorylation of 752, right? So this phosphorylation is very important, right? In order to recruit PI3 kinase, right? But if the phosphorylation happens on 771, then PI3 kinase cannot bind, right? The other molecule like GTPase activating protein which comes and bind there. And if the phosphorylation on this position like 1009, 1021, then this has specific affinity for phospholipase C. It all depends on the domains that are present, right? So these are like SH2 domains, right? It bind phosphor. So it's like if there are two domains present, so it's like the need a region which is like path bind for both, right? In this one, probably only one is involved, right? So this all depends on the presence of SH2 domains and presence of the phosphotyrosine side, right? So what happens is that it's just to show that how the binding takes place. So this is SH2 domain, and the SH2 domain actually bind a phosphotyrosine, right? And then there's another domain which is binding site for amino acid site. So they both goes and then they call kind of adapter protein and bind to the receptor, right? And then once yeah, I don't have to repeat this. I have gone through this many times, right? How the G proteins get activated. Okay, and it just shows the RAS signaling that RAS activated and activate a number of signaling pathway. We already has covered there, right? We already gone through this. There's again the RAF, it's like MAP kinase activation, how MAP kinase get activated. So we know that we have selective RAS, which get activated. So RAS actually recruits the RAF protein, right? The RAF protein does what it does is actually gets phosphorylated, activate. RAF is also known as MAP kinase, which activate MAP protein, which is known as MAP kinase, right? We activate MAP kinase. Once MAP kinase is activated, then go and phosphorylate proteins, and we get a response, right? So it's just a signaling cascade how the MAP kinase pathway is activated, and then I'm trying to move these so I can see what it is. Oh, hey. Okay. So MAP kinase activation of transcription. So once the MAP kinase is activated, right, it goes into the nucleus, bind to the response element, and then what happens that the MAP kinase is also involved in phosphorylation of another protein, which is P90RSK, right? And this is also a transcription factor. So basically, the activation of this pathway lead to the generation of two kind of pathways, right? One by MAP kinase itself, which goes into nucleus, bind to this response element and start transcribing the gene. This thing also, the P90 again does the same thing that it's actually activates certain transcription factor. So it's activated, it's phosphorylate, which goes into response element, recruit other proteins, and then induce the transcription. Right? So that's how the MAP kinase pathway goes into the nucleus, and then okay. Sorry. Okay, now the thing is that strategy to prevent crosstalk between MAP kinase signaling pathway, right? So the thing is that there are several ligands activate nerve kinase, right? So there's some kind of mechanism that they prevent like a crosstalk, right? So for example, like here is the mating factor inducing nerve kinase, right? Kinase A, B, C, right? So this is like nerve kinase, and then nerve kinase, right? In this case, we have again the same thing, right? So they actually, they have the scaffold which actually prevent their crosstalk, right? So they don't interact. Like, this node is not going to activate this one. This not going to activate this one. So they activate their own kind of sequence. Okay. Okay, the other important enzyme is PI3 kinase, right? So we all, I think, familiarized with NAP kinase, right? We've gone through NAP kinase so many times, right? We also know about SARC kinase, like SARC activation, RAS activation, right? Okay, so how it does it? So RAS is linked to NAP kinase, right? And NAP kinase activation of the other one is, the important one is PI3 kinase, right? Now, PI3 kinase is like the phosphatidylinositol 3 kinase, right? And what happens? The same thing that with growth factor bind to the receptor, right? Receptor get phosphorylated, right? Once it's phosphorylated, it will put the PI3 kinase, right? The PI3 kinase is like two subunit P85 and P10. So P85 actually binds to this phosphate, right? Once it's bind to the PI3 kinase, what it does is actually, as the name suggests, PI3 kinase, it actually phosphorylates the substrate in the membrane, right? So this is already it's like this PIP2, it become like PIP3, right? So it's put another group here. So it's phosphatidylinositol trisphosphate, right? So this is phosphatidylinositol and 1, 2, 3, right? Before this it was PIP2, now it become like PIP3, right? Once it's PIP3, which is a very strong affinity for which enzyme? AKT. AKT, right? So PIP3 always goes downstream is AKT, right? So it's it's recruit AKT. Okay, so here is shown like structure wise, right? So it's shown, just to show you what happens. That we have inositol, very simple phospholipid, like inositol phosphate, right? So again, this is 3 glycerol, 2 fatty acids, right? Phosphate and then glycerol. So this is phosphatidylinositol, right? Now phosphatidylinositol is phosphorylated on 4th position. So this is like PI4 phosphate, right? Or it's simply PI. Is called PIP, right? Inositol, phosphate, right? And then it can further phosphorylated on this first, this 4th position and then 5th position, right? So it's now PIP2, right? And then PIP2 is a substrate for PLC, right? And then what happens that this is I have to move this, right? So again, anyway, so this is again inositol 1 phosphate, right? And this is 3,4, right? And then the PIP3 kinase actually phosphorylate this position, right? So it's PIP3. Then just to show you that how these structures look like. Okay, so again, that's PIP3 kinase is activated, right? And then it's going to phosphorylate and actually then is at a peak. Just phosphorylate the peak protein kinase B is actually AKT, right? So what it does is recruit the protein kinase B. Once this protein kinase B is actually require another cofactor, right? So this cofactor, once this is produced, right, they have affinity to bind, right? And then this get phosphorylated. Now PDK phosphorylate PKB. Once this is phosphorylated, it's become like active. Then it gets this phosphorylate other protein. So it's like a cascade. Fatty activate AKT then activate a number of proteins, and then what happens? One of the proteins is that bed enzyme, right? So once it's activated, right? So it's activated, it's phosphorylated bed, it actually remove this activated term, and then what it does is actually inhibitive apoptosis, right? So that's why PIP3 kinase is known as survival signal, right? It actually prevent the cell to undergo apoptosis. Okay, so it induces survival. So that's how protein kinase B and PKT they act. Their signaling goes, and AKT is actually is a very key regulator.
We need to stop within that couple few minutes.
Okay, yeah, we
Can
can stop. Yeah, we can stop just after this PKT. So we have this AKT, and you can see a downstream AKT. You know, is actually required is used by a number of other molecules. So the signal is is involved in a number of signals which are involved in cell survival, right? And I just stop here. I think. Okay, I can stop here.
Yeah, yeah, it's okay. So we can just have the lights, please. Yeah. Oh, yeah. Can I close it so that,
Sure. Yeah.
yeah, just we will do that for a moment. It's all right. No, it's better. شغلي انت انا ما تدخلونيش في التكنولوجيا.
You can turn it off.
اي قولي هاي بس.
Yeah, we can turn it off.
Turn it off.
Yes.
You did, okay. Well, oh, there's 20 participants already. Sorry, they were waiting.
Yeah. Okay.
Okay,
Share, and we share screen.
yeah.
Thank you.
So, okay, so people who are on Zoom, I apologize. I think we started without realizing the Zoom connection was not on. So there was small details I think you probably missed, but not really a whole lot of it. I think we almost completed singular transaction topic, and then we are going to work on the next topic, which is tissue culture. So, and tissue culture is something I think you people use very frequently, but most of the time what happens that the information goes from one generation to other generation. Like people who do tissue culture, they teach other people tissue culture, and then the person who learn is they try to shortcut some techniques, right? And then modify it, and then tell it to other person, the third person then modify it, and then again, the actual information, how it is done properly, it gets lost, right? So the idea of this lecture is to go to certain procedures to make sure that you're using the cell line, they're healthy, you're using the right cell line, and you know how to keep them and how to use them in a way that they respond to you, right? Because sometimes you might have noticed that you do experiment and you're not getting any result, right? The reason maybe your just cell lines are not responding anymore. They are, changed or something happened to them, right? So we go to basics of tissue culture. Okay, so what is tissue culture? So cell culture is a process by which prokaryotic or eukaryotic or plant cells are grown under controlled conditions, right? Typically, culturing of cells are from animal and human sources. Just most of the time used, but people also use tissue culture for plants. For plants, tissue culture is not so common because it's easy. You just put the seeds in the ground and you get the plant out, right? So you don't have to really do anything. But specifically, if you're looking for certain cell in plant, just want to study, then you have to go and do the plant tissue culture, right? So it was actually first time introduced in rocks in 1885. First time they maintained the embryonic cells in a cell culture. But typically, the more recently, cell culture was first successfully undertaken by Ross Harrison in 1907. So it's almost like 125 years that we have this technique, right? But then there's some major developments actually happened that actually lead to successful tissue culture. What was that? Is that first it was the development of antibiotics, right? Because one of the biggest problem of tissue culture is the contamination, right? The bacteria is everywhere. They're hard to control bacteria, and you get contamination easily, right? So if you and the problem was how to remove contamination, right? So once they discovered the antibiotics, then the antibiotics are used to control the bacterial growth, right? And second, the formation of trypsin, because the thing is that these cells adhere to the plate, right? And then in order to culture them again, you have to somehow remove them, right? So that you can plate them again. And then there was no other way. Either you scrape them. Once you scrape them, you basically destroy most of this, right? So what you do then it was found that okay, you can use trypsin, and trypsin can be used without destroying these cells, right? If you treat them properly. But if you leave them longer, then of course trypsin is a enzyme which can digest all the protein, right? So these are the major advances. The third was the use of chemically defined culture media, right? The culture media is like they know every cell has a specific requirement, like the food, we eat like different kind of food, we eat like Mediterranean food, we have Western food, burgers and all that, right? Same as like cells, they prefer their own food, right? So there's number of mediums are developed for their optimum growth. Like some uses more glucose, some uses less glucose, some uses pyruvate, some don't use pyruvate. Okay, so it's like what they like, right? What they prefer and what make them happy, right? Okay, What happened? Okay. So what the benefits of tissue culture, or why tissue culture is used, right? Why cells are used for, right? So cells are like the model system for studying basic cell biology, right? Interaction between disease causing agent and cells, effect of drugs on cell processes and triggering of aging, nutrition studies. So we have cells, you add things to the cells and see how the cell respond, right? So basically that's what you can do. You can use a drug and see if the drug is toxic or not, right? Or you can use a chemical and see if the chemical is carcinogenic or not, right? If inducing all this pathway, you can do, test the toxicity, study the effect of new drugs. Cancer research is heavily used in cancer research, right? That functional phase chemicals, viruses, radiation, and all that. Things like virology, cultivation of viruses for vaccine production, because virus. Oh, here you go. Thank you. Okay, so virology, what happens that viruses they grow only in living organisms, right? They are dead if you just leave it on the table, right? They won't multiply, right? So they need host in order to grow. So tissue culture is one way to keep viruses alive, right? Genetic engineering, like you can use cells to produce protein. You can stimulate gene like production of commercial protein, large scale production of viruses for using vaccine, right? So that's how the polio, rabies, chicken pox, hepatitis B, and they were produced. And gene therapy, cell having a functional gene can be replaced by to cell which having non-functional gene. So now this is becoming a tool for changing the genes. Okay, now tissue culture. In vitro cultivation of organ tissue cells at defined temperature using an incubator and supplemented with a medium containing cell nutrients and growth factor is collectively known as tissue culture, right? But different types of cell grown in culture includes connective tissue, elements such as fibroblasts, skeletal tissues, cardiac, epithelial tissue, liver, breast, skin, kidney, and many different types of tumors, right? Okay. Now, so just did I move to or okay? Now there are different kind of cultures, right? What we call is like a primary culture, right? So the primary culture is what you do. Primary culture basically you isolate tissue, right? And then you try to get the cell out from that tissue, right? So that's a primary culture. So most of the time in a primary culture, it's like if you want to have a normal cell, okay, like you want to have a skin cell grow, right? You can take some skin out, right, and chop it into small pieces and just put in the in a sterile condition, put in the media. The cell will migrate out and then say start growing. Okay, but the problem is the primary culture is usually a heterogeneous population, because in skin we don't have only fibroblasts, we have a lot of other keratinocytes and all that. So you won't get a pure culture, right? But there's a way you can, some organs have, or the cells which is only one type, then that can be used, right? The other thing is that the primary cell is finite lifespan. So if they grow 2 or 3 generations after that, they will die. So they cannot be continued growing, right? The heterogeneous, okay, subculture primarily leads to generation of cell line, right? So, if you isolate, a primary cell like pure without any other connected cell, you can actually subculture them, right? When you subculture them, you basically generate a cell line, right? But these cell lines have like a limited lifespan. Like for example, you take a normal normal endothelial cell. People usually often do it because you can get the endothelial cells from blood vessel, and the blood vessel out and grow out from there, right? But they just grow only like 10, 15 generations after that they will die, right? Okay. Now, the other kind we have like finite or continuous cell line, right? So again, the finite cell line which has a limited lifespan and go through a limited number of cell generation, right? Usually about 20 to 80. Okay, doubling and non-finite cell line, right? This cell line exhibit the property of contact inhibition, density, limitation, anchorage dependence. The growth is like slow. The big time is around 24 to 96, right? The finite cell lines is usually from normal cells because they again have the limited lifespan. After that, they die, right? And they have the show in the beginning, like that they have the normal cell. They contact inhibit once. Fibroblast. Yeah, fibroblast. Yeah, same. It's like they don't. You have to basically after a certain passage, you have to stop using them. Because if you continuously use the same culture again and again, then you might have different properties. Okay, and then they will be slowly divided. Okay, so the continuous cell lines, the most cell line grow on a limited number of generations after which this is right. Cell line which either occur spontaneously induced virally or chemically transformed, they usually continuously grow. So basically, when cell is transformed, so when its normal cell is changed into a, is transformed to a cancer cell, right? So those cell lines continuously divide. Yes, they can grow again and again and again. And I give the example yesterday about HeLa cell. Like HeLa, was drive like long time ago. I think it's a ovarian cancer. Patient is long gone, but her cell is still alive. Okay, and it's been distributed all over the world, and they still keep growing. Okay, so that's how it's like a continuous growing. There's no end to those cell lines. So cancer cell lines they can grow, right? Now the type of cells, and then sometimes the based on morphology and shape or their functional characteristics, they are basically like divided into three, right? But there are more than three, but these are like a simplest form, right? They are like fibroblast, right? So fibroblast looks like again like fibers, right? Long things, right? Epithelial cells, and see the epithelial cells how they look like. It's like they are all they have like they are like attached, and then I mean they are adherent and they are in contact with each other, right? So they're making a monolayer, right? And then we have lymphoblastic cells. So these are like in suspension. Okay. HP, THP1. What is this? Yeah, THP1, of course, yeah, T cells, yeah. So yeah, they are like in suspension. Okay. So so these are just but there are other cell line, like endothelial cells, they look a little different, right? And then we have skeletal muscle cell, they look a little different. Okay, now culturing cell. Cell line derived from normal tissue are considered as anchorage dependent growth. Only a suitable substrate, like and suspension cell are anchorage independent, like blood cell. Transform cell lines either grow on as monolayer or in suspension. So most of the cells from organ, like normal cells, they grow on like a solid surface, like in a plastic usually, right? But the suspension cell, like blood, cells, they are in suspension. They don't need any adherence, right? But the transform cells, like most of them, actually, if they are originated from a like organ, they grow as a adherence cells, right? But if they are blood dry, like leukemic cell, then they grow in suspension. Okay. So what we need, so the basic equipment and facilities in animal cell culture, right? So very first important thing is a place, right? It has to be clean, sterile place, right? So sterile work area. How do we get the sterile work area? You cannot make the whole room sterile. So basically they use this laminar flow wood, this tissue culture wood, you probably all seen it, right? So this is basically make it, provide a sterile condition, right? So what it is that, that it has a air coming from filters, right? So it gets filtered, it become like, all pathogen, like, pathogen free, bacteria free, right? It comes and then it circulates in the chamber, right? So then it goes, that you have seen like there's a mesh there, right? Goes from top, goes to the mesh and then go take it to the system, right? And recirculate again and again. So it's kind of providing a very, very clean air all the time. And air is the one who carries bacteria, right? Everything is contaminated bacteria in the air because the air has a lot of bacteria, right? If an airflow cabinet cannot be provided, the cell culture work may be done on a clean bench using a Bunsen burner to create a sterile umbrella under which the work can be done, right? So, I mean, if you don't have facility, you can still do the tissue culture just as a burner, right? So the hot air actually kills the bacteria around it, and you just use everything close to the burner, like, and then you can still do this tissue culture, but this is like not very convenient, right? So basic equipment. If you're establishing a tissue culture lab, what do you need, right? And you probably all seen these things and have these things. First thing is trial work area. It is cell culture hood, like a laminar flow hood or biosafety cabinet. You need an incubator, humidified incubator with carbon dioxide, water bath, centrifuge. You need a refrigerator and freezer to keep your cells, and then media cell counter. When you grow cell, you need to know how many cells, how they're, how many alive, how many dead. So you need some kind of mechanism for counting them. Inverted microscope, of course, you want to see the cell. You cannot just use them without looking at them, right? So you need definitely in the microscope. You need a liquid nitrogen because you have to save your cell, right? You cannot just use the cell. If anything contamination happens, then your cell line is gone. So what you do, you grow the cell and then save some of the cells, right? Keep in liquid nitrogen so that if anything happens to your cell line, then you can always bring them back and grow them, right? You need an autoclave, right? Because all the things you're going to use have to be sterile, right? So you need autoclave, and then you need an aspiration pump or a peristaltic pump or a vacuum pump. Because the thing is that you have cells growing in the media, right? You have to remove the media. So when you pour, then you have chance of contamination because everything. So what you do, you just put a pipette or something connected to the vacuum, and vacuum sucks out every positive, right? So it saves you, prevent the contamination. So these some of the things I'm sure you probably have it and seen it, right? Now, when we do tissue culture, there are like different kind of safety levels, right? So which is kind of designed as like a biosafety level 1, biosafety level 2, bio 3, and bio 4. Most of the tissue culture is done using biosafety level 2, right? Biosafety level 1 is like a very basic safety that you have to have a clean bench and just maintain the conditions, sterile conditions. So BSL1 is the basic level of protection common to most research and clinical laboratories, and is appropriate for agent that is not known to cause disease in normal and healthy humans. BCL2 is appropriate for moderate risk agent known to cause human disease of varying severity by ingestion or through percutaneous or mucous membrane exposure. Most cell culture lab should be at least BCL2, right? Okay, but the exact requirement depends on the cell line, dose, and type of what we do, right? But most of this kind of cell type of what we do is BCL, that's what we do. Further, the safety is BCL3, right? BCL3 is used basically when there's a field that the things is dangerous for human health. They can escape in the air, and then person can inhale it, like in aerosol, and then and probably can have a lethal effect, right? So you have to have an environment with a passive pressure. So nothing gets out at all. Everything stays in. So pressure maintains like a negative pressure. So it's all kind of regulated. And be a safety level 4 is the highest safety level used when you are using viruses and things like, for example, if you want to work on COVID, you cannot use without biosafety level 4, right? So this is like very, very it's appropriate for exotic agent that pose a high individual risk of life-threatening disease by infectious aerosol or for which no treatment is available. So highly risky kind of tissue culture you want to do, then you have to go to that one. Okay. Now, the same as when you use this tissue culture hood, those tissue culture hood can also be for different safety level. Okay. So we have like class 1, class 2, and class 3. So most of the time we use class 2, right? So class 1 cell culture would offer significant level of protection to laboratory personnel into environment when used with good microbial techniques, but they do not provide culture protection from contamination, right? So they provide protection to person, okay, but they do not provide any protection to tissue culture. So you have risk of contamination, right? Whereas in class 2 culture hood, they're designed for work involving like BCL 1, 2, 3 materials, and they also provide an aseptic environment for cell culture. If cell culture is safe, there's no risk of contamination, right? Class 2 bioseptic cabinet should be used for handling potentially hazardous chemicals, like primate drive culture, virally infected culture, radioisotope, carcinogen, and toxic agent. So is that not only tissue culture, but you can also use this hood for other purposes too. Like the main purpose is that nothing gets out from the hood, right? Everything air is actually going to remove it, right? And then filter it out, right? Class 3 bioseptic cabinet are gas tight and they provide highest attainable level of protection to personnel and the environment, right? So a class 3 bioseptic cabinets is required for work involving non-human pathogen and other risky material. Okay, so I'm sure you all have seen a tissue culture hood. If those who have not seen, I just put pictures. So what it is actually is a cabinet, and this is actually glass, right? So this glass actually is you cannot just open to any land. There's a fixed place you can open because it causes a pressure. The air is coming, and there's at the bottom there are some. You can see there's like a lining. There's holes, right? Which actually there's a fan at the back, so fan actually pull the air out, pull the air in actually, not from outside, but the same air which is coming, right? So the filtered air is coming, and then it gets sucked again. So they're making the whole environment using this same filtered air all the time. So this air, no air gets out from room into the cabinet, right? Only because of the pressure or the fan blowing the air goes in and then it gets sucked out, right? Typically, how it is arranged that you need something like 70% ethanol. So you spray every day before you use it. You have to clean the bench, right? Okay, you have to have a container where you can have your waste, right? There's your culture flask, tube rake, your media, right, and the pipetter. And that's how everybody arranged, right? You probably have seen it, right? So you use the pipetter, remove the media, put it there, throw the pipette, use another pipette, put the fresh media, right? So this is very, very common, right? Now, what happens, we have culture media. Now, this culture media, choice of media depends on the type of cell being cultured, of course, right? Different cell, different requirement. The most common media are EMEM and DME, right? So this is very, very basic media, right? And there's not very much difference. It's only small difference in their composition. Media is supplemented with antibiotics like penicillin and streptomycin, right? Okay, prepared media is filtered and incubated at 4 degrees Celsius, right? So what happens that in the old times we used to make our own media, not in a way that you get these packets which have all the powder, right? So all the nutrients are already there. What you have to do is just open it and put in 500 ml water, mix it, right? And then we actually have to sterile filter to make it bacteria free. But these days, you can buy. It comes in a bottle. So this is just shown like an old way. You make the media and then you keep it in the refrigerator, right? These days you get all ready-made media. You just buy it, and then when you're using, once you stop, once you finish, you put it back into the refrigerator and just taking precaution not to contaminate it, right? Okay, so media. So the culture media is the most important component of environment because that's where the cells are growing, right? Because it provides the necessary nutrients, growth factor, and hormones for cell growth, as well as regulating the pH and osmotic pressure in the culture, right? The three basic classes of media are basal media, reduced serum media, and serum film media. Okay, that's what we use, right? We use basal media. Okay, which we actually, add serum in it, the growth factor side, and then we antibiotic. Okay. Sorry. Oh, okay. So these like the serum and growth factors, serum and antibiotics, right? Okay. But what happens that when you want to do some experiment, you don't want to use serum because serum has a lot of stuff, right? It has like a lot of proteins, hormones, and all that. If you're looking for the effect of some agent, then you don't know whether the effect is because of the agent or because it's interacting with something, the serum, and serum is binding protein. You may not get an effect because serum is going to bind with the chemical, right? So you try to use serum-free media, right? But you may get condition that some cells, they cannot grow in serum media at all. They don't like it. They need to have some serum, right? So what you do, you use the reduced serum media. Sorry. Yeah.
Yeah, so I was wondering the media that's used to fix the cells. It's 90% serum.
No, it's not 90% serum. Yeah, you can do that too, but usually it's done in like a 20% DMSO. With 10%, yeah, filler point serum.
Yeah.
Yeah.
So is it considered basic?
Well, it's a basal media, it's a supplemented, yeah. 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 Okay, so the thing is that we use serum. Like the serum is virtually important as a source of growth and addition factor, hormones, lipid, minerals for the culture of cells, right? The thing is, serum is not obtained from a reputable source. Contamination can also pose a serious threat to successful, cell culture experiments. So serum is important. Now these days, this area is so advanced, and you can buy serum specifically for tissue culture, like with Gipco and the other companies. They make Nutrigen, Gipco make this serum, right? And then the thing is that when you use serum, the practice is you buy serum in bulk, right? Because changing serum from one kind of source to other source depends, because it's derived from animals, right? So again, this depends on the animal, depend on the origin, which country, what the animal's eating, and what's in there. So it's usually typically is recommended that you buy serum, you buy in bulk, and then you use over time, right? What's the sorry?
Can I give birth?
Sure, yeah, definitely, yeah. Okay, so basal media, right? So basal media, the majority of cell line grow well in basal media, which contain amino acid, vitamins, inorganic salts, and carbon salts such as glucose, right? But these basal media formulation must be further supplemented with serum, right? Typically 10% serum, and then we use about 5 ml of this antibody comes not prepared. So you just add antibiotic solution, right? Reduce serum media, and the strategy to reduce undesired effect of serum in cell culture is to use reduced serum media, right? Reduced serum media, basal media, enriched with nutrients and animal, dry factor, which reduces the amount of serum that is needed, right? Okay, and there's a serum-free media, right? And then what happens that you can use sometimes.
We usually use it
You use serum-free media,
in
cell culture.
phase.
Yeah, and then we don't add serum at all. So your cell grow okay?
We use the growing serum.
Yeah, they cannot grow without serum. You have to have serum. It's only for this short period of time. They can survive. In the serum-free media, they can survive, but they cannot divide because you need, serum, and serum has growth factors in order to divide, right? So when you did the experiment, in your experiment, you use serum-free media because an experiment is usually you have the effect of like 6 hours, 8 hours, 10 hours, 24 hours, or sometimes 42 hours, right? Cell can survive; they would not die because they have nutrients, right? But they will not multiply. Yeah. So what happens that now growing cancer cell is no problem, right? Because cancer cells are very tough, right? They grow. They need still serum, but they can easily grow, right? But if you're growing normal cell, so normal cells actually require growth factor. Like for example, if you want to grow endothelial cell, right? So endothelial cell has to have the endothelial, the EGF in there, maybe some kind of little bit insulin like growth factor. So now the media comes, like you get a basal medium, and they comes with the different supplements, right? So they just said that, okay, just use, when you get this, just put the whole vial in there, because these are very sensitive. They have certain like life, time. They are not adapted in the media, because otherwise what happens, they lose their activity. So they are come as a frozen, and when are you ready, then you just make the media, and then usually it lasts about a month, or what depends on what kind of supplements you have, month or 2 months, right? So again, this is just an example to show that there are supplements, and it depends on what kind of cells you want to grow, and every they are making media specific for that particular cell line, right? Otherwise, the normal cell will not grow. Okay. Okay. So the serum, what actually serum provides, right? So serum actually is a rich source of albumin, right? Transferrin, alpha, beta, and gamma globulin fraction. They have regulatory protein. They have growth factor, mostly epidermal growth factor, fibroblast growth factor, and they have like hormones like insulin and transferrin, right? And then their function is that albumin is like to provide a buffering capacity, right? Because it's a protein in nature, and it's also it is like antioxidant and also transporter of insoluble materials. So things bind with the protein which are present in albumin, right? And then they are then taken up by cell. Okay, so this will work as like a transport, right? Okay, transferrin is an iron chelator and iron transporter, right? All other proteins, they bind irons and prevent infection, regulate gene expression, and then growth factor required for proliferation, and then hormone insulin for of course the glucose homeostasis metabolism, right? Okay, so they have all these functions. Okay, now I'm not sure if you can read it. Just to give you an example, there are so many different cell lines. So these are all different cell lines, and then these are what are they like? Usually cell line has different numbers, right? Different kind of strange names. But like for example, is 293 is a fibroblast, right? Or you can get A9 cell, which also fibroblast from human, right? And then they can tell you what kind of fibroblasts they are. Like they are from connective tissue, they are from kidneys or whatever. So we have all kind of cell, like we have fibroblasts, epithelial cells, and then and then they are the the source where they are, and here's a list of media that can be used, right? Like this MEM, DMEM, that F12K, all these special media. So they are already the company who makes the cell line, who actually initiate or get the cell line, they already done the experiments to know that what conditions are required in order to have the optimum growth, right? So they formulated the one. Okay, and then again it's just the same. This is just there's so many cell lines, so many media, right? Actually, this I was going to show it before. So what happens that once you make your media, okay, so you have you purchase your media, you added serum, you added antibiotics in there, right? So you are ready to use it, right? So when you made the serum, you have to really be very careful, because everything is sterile, right? If you suspect that you touch something, you touch the bottleneck, or maybe you pipe, the pipette you are using, you touch the floor or touch your hand, right? So it means there's a greater chance of contamination, right? If you suspect anything, what you do, we get this filtration system, right? You probably have seen this, right? Okay, so what you do, there's a membrane here, which is like 0.2 micron membrane, right? So it's basically block all kind of pathogens, right? So you just put the media here, there's a vacuum here, because it's so thin, it's pores, you need to have some kind of vacuum to suck the liquid out, right? So vacuum sucks the liquid out, and then vacuum goes to the filter in this water, right? And there's an extra cap, and you just put the cap on, right? So you always try to make sure that your media is not contaminated, is free, right? Because the thing is that if it's contaminated, then you are
you are in problem, right? Because you can destroy your cell line, because once the bacteria grow, it's really impossible to get rid of it, right? They just grow so quickly, and yeah. Okay. Now things to consider, is like pH and carbon dioxide level, right? And you have probably seen that the media used is like red and pinkish in color, right? And after a while, it becomes yellow, right? Look like everybody's doing this, right? Okay. Or forgot to change the media, right? That's what happens. So why you get this yellow color? Hmm? Consume what? No, yeah, nutrients consumed. No, there's another. Albumin, no. No. Yeah. Yeah, so what happens is this has color. It's just like it's a dye, right? Which tells you that pH is very off, right? So what happens that when you eat something, right, you make waste, right? The same as with this cell, right? Cell consumes glucose, right? And then the rest is lactic acid, because glucose will do the glycolysis, glucose is utilized, okay, coming to pyruvate, pyruvate goes into TCA cycle, and then the carbon dioxide and water, right? But the cancer cell actually they do anaerobic oxidation. They make pyruvate. And pyruvate actually does not go into TCA cycle, but rather it reduces to lactic acid, right? And lactic acid is an acid, right? So you get accumulation of lactic acid, right? So lactic acid, what is the acid? So it decreases the pH. So you get a yellowish color, right? So that's how, and then you have to change the media because it means the pH is changed. Cell is not happy, right? So you have to basically to when you change the media, you basically removing the waste and adding the nutrients, right? Okay. So pH, in most normal mammalian cells, at pH like 7.4, and there is very limited, little variability among different cell lines. So most of it, 7.4, they grow, right? Unless you have like insect cell line, which grow as like an acidic pH, like 6.2, right? So the way pH is controlled, your media actually has carbonate and bicarbonate buffering system, right? So it basically tries to regulate the pH at a shorter range, but if you have too much lactic acid formation, right? Then all the carbonate, bicarbonate consume and you don't get, right? Okay. Now this other thing is the important thing is carbon dioxide. What percentage of carbon dioxide do you use in your 5%? Okay. Okay. 5% carbon dioxide, is there too much carbon dioxide? What will happen? Cell will die, of course. But why? No. It will affect the pH because we have that carbonate or bicarbonate system, right? So the carbon dioxide is actually there to maintain the pH, right? So it provides like a buffering, thing, right? So the thing is that if you have little carbon dioxide, then what happens that it is not going to maintain the pH, right? Too many carbon dioxide, it's again not going to do. Okay, so we now like 5% carbon dioxide, right? Okay, temperature. Why the temperature is important? Yeah, so everybody knows okay, temperature is important, right? Okay. Because our body temperature is 37. So in order to see a physiological response, one is have the same temperature mentioned, right? Okay, so the most human and mammalian cell line are maintained as between 36 to 37, right? Okay, so all this, the incubator we use, they are very, very good, right? They maintain temperature very nicely, right? Okay, but then, the insect cell, they grow on a different, avian cells, they have different, right? And the cell line from cold-blooded animals, like, fish, they use, of course, lower temperature. Okay, now, so that's about basic the tissue culture. But we need the additional supplies, right? In order to, and these are some of the things I just put the picture. I'm sure you have seen it. I just put the picture just in case you have not seen it, right? So the what we need like cell culture vessels, right? So these can be like a variety of things, like these are like a flask, right? And they are like a petri dishes, right? They can be of different size, depending on what experiment you want to do. If you need a lot of cells, then you grow in a big petri dish. If you want a small cell, the reason is why we use it, because the thing is when we want to treat them, and sometimes the agent or chemical you're using, they are very expensive, right? And they are sometimes they're hard to obtain, right? Somebody synthesizes it or somebody did, right? So what happens if you use a big flask, you need a lot of chemicals, right? And you probably don't need that much cells, right? So what we do, you try to grow in a minimum area, right? So we have like these plates, and then we have like all like multi well plates like 48, 12 wells, 6 wells, 96 wells. So again, as you use smaller and smaller, then you use less and less media, less chemicals, less oil. So okay, so you're not spending too much money on tissue culture, so you maintain it, right? These are some of these flasks. They are used, right, for filtration. Again, it depends on volume, how many volume you want to filter. Pipettes you probably have seen, they come on different, like 50 ml, 25, 10, 5, 1, 2 ml, and 1 ml, right? And they are usually comes in bag, style bag, right? So you just open. When you open, make sure that you don't touch it, don't touch anything. Okay. Same as this is pipette, right? You probably have one of these, right? You have multi-channel. When you use like 96 well plate, use multi-channel. Okay, the only thing you have to make sure that all these tight, yeah, they're not loose, because they're loose, they fall down, or they're not, they're not having a vacuum, and they're not, yeah. And then we have pipettes like this, right? And then we have media, right? So these are some of the things we use. Okay, incubator, right? The purpose of incubator is to provide appropriate environment, right? The incubator should be large enough for your lab's need, have forced air circulation. Now all this they have, right? And should have temperature control, right? Usually they are stainless resistive, right? Because they are very easy to clean. Okay, you just put wipe with the ethanol. Although the requirement of aseptic condition, you don't have to have an aseptic condition, because everything is sealed in your flask and all that, right? But you have to make a habit of cleaning the incubator like once a month, or once in 2 months. Take everything out, spray ethanol, and then 70% ethanol. So look like you're already doing this. So you just spray and clean it, right? So it will make your things clean, and you won't get contamination. Because contamination is really a problem. And it's really very frustrating thing, because you're growing this cell, all of a sudden you got contamination, you can't do anything, right? And you lost your cell line, you don't even have cell lines, right? So this can be very dangerous too. So just taking a little bit care. And then this there's a like still just shelving. Now the other important thing is this. What is this? Water, right? You have to make sure there's no water. There's some water, right? Because the thing is that you need some kind of humidified environment, right? Because you have carbon dioxide, you have humidified environment. If you don't, what will happen? That the tubes you have, like 96 plate or whatever, because the thing is that the temperature in incubator is what? 37, right? Okay. You have your tissue culture. So the media is going to evaporate a little bit, right? And then, but when it's humidified, then the evaporation is less, right? Okay. So make sure that, you have water in there to maintain the, it's in a humidified condition, right? Okay. Now storage, right? You need to have some kind of storage for your glassware, plastics, and all that. So you have like clean and nice shelves, right? You have to have a refrigerator, because you have to keep your media in the refrigerator, right? And then you have to take care of your refrigerator too, that not to have contamination. One more thing, actually, I'm sure you don't do it, but I've seen places that people use the same refrigerator to keep their food, and then other chemicals too, which is like not a good habit, right? Because you don't know what is leaking out, what is contaminate your food, and you might get sick, right? So never ever use your food even for a few minutes, right, in the refrigerator. Have a separate refrigerator for food, and then don't use a refrigerator for food for your storing the chemicals, right? Okay. And then you
you need freezer, right? Okay, because some of these things you get in your media and all that, you need to be, frozen, right? Now, one other thing is really you have to have is a -80 freezer, right? For like, frozen, right? And the other thing actually you need to have is, I don't know, I put it here or not, is liquid nitrogen tank. So do you have liquid nitrogen? Well, yeah, because you cannot do without it, right? So this is to, store your cells. Okay. Okay. Now there are some like tips, I'm sure you all doing that, right? What you need to do, always wear appropriate personal protective equipment, right? Because lab coat provide you a lot of protection. The cell line you're using can be a cancer cell line, whatever, you don't want to accidentally drop on yourself, right? Or you always use gloves, right? You don't want to touch something. Usually, when the cancer cannot easily grow, right? Even you touch it, it will not grow. But you don't want to take this. They won't know, because cancer are funny cells. They can have, I don't know what kind of mutation they have. They can escape from your immune system, and I don't know what kind of immune system one has. Maybe weak immune system that could be dangerous, right? Change gloves when contaminated, right? Dispose gloves with other contaminants, right? You can dispose of the contaminants safely, right? You have to collect it, right? Wash your hands after working with potentially hazardous materials and before leaving the lab, right? Okay. Do not eat, drink, smoke, handle contact lenses, apply cosmetic or store food for human consumption in the laboratory, right? None of these, right? I'm sure you will do all these, right? Okay. People, I've seen people that drink coffee in their lab, and which is not a good, idea, because you don't know what's in the lab, all the contaminants. For the institutional policy regarding safe handling of sharps, like needles and all that, that need to be safely disposed, decontaminate or work surfaces before and after experiment. And I'm sure you do it, like wipe with ethanol, before you use it. But it's also important, also wipe it after you use it, right? Because sometimes, maybe somebody's coming and in hurry and want to use it and did not clean it, and you get the contamination, right? But after saying this, don't trust that is somebody already had cleaned it, right? So again, when you use it, clean it again, right? So that you just is kind of safeguard so that you avoid contamination, right? Okay, clean laboratory equipment routinely, even is not contaminated, right? So make sure everything's clean. Decontaminate all potentially infectious material before disposal. Report any incidents that may result in exposure or infection material to appropriate personnel, supervisor, whatever, right? If you suspect anything, right? If you have a lab accident, don't try to hide it, right? That okay, maybe somebody got upset or something, just report it. Because the thing is that if you tell somebody, then you can be treated, right? Or you can inform other people, right? That okay, this is that's what happened. Don't come into this area, right? Maybe you can also get contaminated all there, right? So you have to really exposure to infectious agent. You always tell somebody that okay, this one, even you don't feel any sick or anything, but it's always a good idea to tell them so that you can get a proper care, maybe see a doctor or something, because sometimes something takes time to develop infection. Okay. Now, so you have everything ready in your, right? You start growing this cell, right? When you grow the cell, you take the cell out from liquid nitrogen, right, and grow them, right? And then after that, you have to subculture again and again, right? So why subculture, right? Once the available substrate surface is covered by cell, what we call confluence, right? So then cell is not going to grow. Okay, then you have to remove them, right? And subculture. So basically, if you have one flask, you divide into 2 or 3 or 4 flasks. Okay, so cells to be kept in healthy and growing state, they have to be subculture or pasa, right? The passage of cell is the passage of cell when they reach about 80 to 95, 80 to 90 confluency in the flask, right? Okay, enzymes such as trypsin, lipase, collagenase break the cellular glue that attach the cell to the surface, right? So what happens? So I don't know if you can see it or not. Can you see this, right? Okay, so what it is actually the whole surface is covered, right? This is a monolayer, right? So now there is no more room for cell to grow. Okay, So what you need to subculture, right? Okay, but remember, no, you don't let your cell grow up to that far, right? Because once they we have the contact inhibition, right? Some of the cell change, become like go into senescence, like we explained, like become older, they lose the ability to divide. So you actually do subculture when they're about 80 to 90% conflict. So there is still, you can see rooms in between, right? Okay. And sometimes, it's often like, they say, oh, people get busy working in the lab and, social activity and all that. They don't have time. They see under microscope, they say, oh, maybe I can do it tomorrow, right? But when the tomorrow comes, it's all completely full, right? There's nothing wrong. You can still grow a cell. You still have the cell. But the thing is that, it's like, you have like cell, maybe, few cells become senescence, right? It means they will not divide, right? So once you develop that habit, and gradually what will happen, then more and more cells become all and all. I mean, they're alive, they're not dead, but they lose their ability to multiply, right? So what happens then, you have probably noticed that some cells takes very long time to grow, right? So that's maybe it happens that people not taking care of these cells, and then most of this culture is basically has old cells, right? So just to avoid this, what you do, you just subculture them before they become confluent, right? Okay. Now the subculturing also referred as passaging, right? So what you do is you remove the media, transfer the cell from you remove the cell, right, and transfer into a new basically media. Okay, so that they can further have a more nutrients and they grow, right? Now when this cell grow, right, the growth of cell in culture proceed from like there's a lag period, they grow slow, and then there's an exponential period, right? Then they grow like linear lag. So there's a lag period following the growth phase when the cell proliferates exponentially, right? When cell is adherent, culture occupy all the available substrate and have no room left for expansion. Or when the cells in suspension, culture exceeds the capacity of mediator support for that, right? Cell proliferation is greatly reduced or ceased entirely. Okay, so when they are completely covered the surface, their ability to divide will reduce, right? When suspension cell, there's a lot of room, but what happens? They deplete the nutrients, right? So you have to subculture them, right? So to keep them at optimal density to continue growth and to stimulate further proliferation, the culture has to divide and you have to provide the fresh feed. Okay. Okay. Now, safety aspect of cell culture, right? Possibly keep culture free of antibiotics in order to be able to recognize the contamination, right? Never use same media bottle for different cell lines. Okay. If caps are dropped or bottle touched unconditionally, replace them with a new, right? Okay, switch on the laminar flow cabinet 20 minutes prior to start work. Okay, cell culture which are frequently used should be subculture and stored as duplicate step, right? Okay, so I explain some of these things what happens in the lab, right? Okay, so what happens that often what you try to do is take one of your culture and grow in the absence of antibiotics, right? Just to see if there is this culture is not contaminated with bacteria. What happens that you may have bacterial contamination because of the antibiotics. It may be bacteria growing slowly, right? So occasionally just take your some culture and grow in the absence of antibiotics, and just to see there's no bacteria, right? Or sometimes what you do, if you have suspect your culture media is contaminated, take the culture media and just put in the flowers and just see, see if it is get turbid. If turbid is mean the media is not clean. You have to either start filtering or you have to make new media. Okay. Now, what happens that, for example, you have two cell lines. Okay, two different cell lines, and they both use DMEM, right? Okay, you're in rush, right? It's almost like 4:30, and you have to leave at 5 o'clock. And then what you do, you pull the both cell lines out, right? Because you're using same media, you use the same media, right? So people, what they do is, and I am guilty, I've done this before. like you remove the media, right? And then just add fresh media in both culture, right? Okay, so what happens, this is occasionally you can do sometime, but you need to avoid it, right? What happens that when taking the media out from bottles and putting in the flasks, so sometimes the cells are present at the neck or something, and you accidentally touch the cell, so 1 or 2 cells comes, and then the putting the same pipette again in the bottle, right? And then taking the media out and then putting on the other flasks, right? Then what you do is transfer the cell. So for example, one cell you have this skeletal muscle cell, other one you have endothelial cell. Now without knowing the transfers of the endothelial cell, muscle cell or muscle cell to endothelial cell, right? So the best idea is do one thing at a time, right? And when you make the media, just designate the media for that particular, like TMEM is used for 3 different cell lines. And logic says, well, why you have to make 3 bottles, right? You can send media and just use when you run out, you can make more DMEM. But the good practice is you make DMEM for skeletal muscle, for example. DMEM you use for fibroblast, for example. And DMEM you use it for endothelial cell. So what happens when you take your endothelial cells, you change the media, whatever is always endothelial cell, right? When you do the fibroblast, always it seems like a wastage of media, but then you can avoid. Because sometimes the cells look alike. In the microscope, we cannot distinguish sometimes, our endothelial cells different than the epithelial cells, right? But and you may have accidentally done that, and you may have a culture which has a mix of cells. So maybe when you do experiment, you may not get proper result because you don't know what kind of cells you are doing, right? It's just a picture, right? So as a good practice, separate media for separate cell line, even though this is the same media you use, right? Okay, it happened to me, it's and I'm very, very careful, and I'm very experienced in tissue culture. And then I was growing like endothelial cell and muscle cell. The thing is that the muscle cell totally different than the endothelial cells, right? So opposite direction, and then I can't believe it happened. One day I saw in flask, and then I see the muscle cell and endothelial cell going in the same flask. But the thing was that I was using the same media. Somehow accidentally, I touched the flask or I touched the corner and just transferred 1 or 2 cells. And over time, they multiply slowly, and all of a sudden you see 2 different kind of cells are used, right? So I'm just saying this from my own experience. And okay, so far anything which is not clear? No, we have adherence cells, right? So cell which basically attached, right? So what happens? Cell which are anchorage dependent, cell, how do you subculture them? So what you have to do, you have to actually remove the media first, right? And then you wash with PBS, right? Why do you wash with PBS? Yeah, I mean,
So we wash from the media, so the chipset can work from.
exactly right. What happens that we in the media we have serum, right? And serum has actually trypsin inhibitors. We naturally have in our system trypsin inhibitors, right? Just to prevent blood coagulation, right? Otherwise, anything happens, our blood will quickly coagulate, right? So what trypsin it does is that we have trypsin inhibitors. So you need to wash. Okay, so basically you're washing the cells. So if there is any serum, you remove it, right? And then you add trypsin, right? Then the incubate plate, about like 1 to 2 minutes. Don't let it go more because trypsin is a proteolytic enzyme. It's going to digest the protein, right? So as soon as you see, you start seeing that shell are shrinking and they're becoming rounding like this. Okay, so it means they are all trypsinized, right? So once the trypsinized, what you do, you add, okay. Okay, you shake just you tap it just to lift them, and then you just add the media, right? So what happens when you add the media, it has serum in it, so it's going to inhibit the trypsin, right? So trypsin is no more active. Then you can basically take the media out, right? And it depends, sometimes you have to centrifuge it to remove the media. Sometimes you can just use and divide into 2 flasks
and add more media and then incubate further, right? Okay. So subculturing clear, right? Okay, you probably do on daily basis, right? Now, if you have a cell which are frozen already in liquid nitrogen, right? So you have to also take precaution how you thaw. Okay, because if you do not thaw it properly, you might have all dead cells, right? So protocol for thawing: remove the cryo while containing frozen cell from liquid nitrogen, right? Okay, and then you put in water bath, and then you just don't leave it there, right? Rather, you just quickly shed them and then thaw them quickly, right? Once it's thawed,
On beach fast.
we
Beats.
I'm not quite sure. You have to just basically take the vial and in water, shake it like this. So there's, it's just thawed, really quickly, right? Okay. So your talk is, you should be done in like, in about like, 1 minute, right? And then what happens, take a while, actually I usually spray with ethanol so that, water bath, maybe a combination, water and all that, and take it, immediately put in the, in the food, right? Okay, and then what you do, you just take them out, put in the media, right? So what I usually do, I usually have a tube already filled with the media. So I remove my cell from carbide and put in the media, right? And then you centrifuge. Okay, and then remove the media, because what happens that this media has cryopreservative and you want to remove them, right? Once you remove them, then you get a cell pellet, right? And then you can suspend this cell pellet, you add more media, suspend it, take it out, and you just put in the flask, right? That's, it's pretty easy. Yes.
But it's better to add cells on PBS or media.
Well, I would have usually media. I never done it with PBS. I think it's with media, because media has got the serum and all there, so that provides some kind of protection. Yeah.
Same thing.
Oh, sandbar. Oh, we said bees in it. Oh, bees and bar. Well, we don't have it in our left, but if you have, you can use it. But you have to shake it. You have to do it quickly.
Easier.
Yeah. Okay. Yeah.
So we use another way. When the cells are frozen, we add 1 ml of media and then transfer it to a flask.
Oh, the frozen cell?
Yeah, the frozen cell. And the other day, next day, we change the media.
Oh,
Is it
okay.
right? This
No,
is not
I mean,
for
I
the
mean,
liquid nitrogen.
Yeah, it's coming from liquid nitrogen.
Yeah.
Yeah.
We do not put in liquid nitrogen when we freeze our cell. We use a freezing media, but we do not put the cells in liquid nitrogen. We put in -80. Yeah, but we want to use the cells within weeks or maybe 1 month. So we put it in the -80 freezer. Then we take it out. We put 1 ml of the media in the transfer to the flask. Yes, to the flask, and then we transfer the whole.
Yeah, no problem.
Yeah, no problem.
No problem if you do it, but typically, I think the thing is that, it's recommended not to store cells in -80. We can do short period, like 1 day, 2 day, or maybe about a week, but not for longer period, right? Because the cells will.
For 2 to 3 weeks, even months.
No, you have to have it in liquid nitrogen, because you have to have it in liquid nitrogen, because your cell lose viability, just slowly die. So it can happen. But saying that, cancer cells are really very, very, different, right? So sometimes they can survive, right? Okay, I'll tell you one, and I was really, really, really surprised what happened. Yeah, like about a couple of months ago. So there was this guy, actually he's from I'm in the university, and he asked me to help. So he said he has some kind of ovarian cancer cells. He's working his whole lab and he's liquid nitrogen, right? So, and he's actually not, he's not a, he's basically going into physics, right? He's like a biophysics, so it's mostly like a physics training, right? So he said, well, I'm going to bring cell for you, and then you can culture and help, right? And I knew that probably he knows what to do, right? So he went to his lab, he took the vial home. Yeah, he took the vial home. no ice is, he took the cell out from like nitrogen, cell on hot, right? And then next morning he brings the cell to me. And I said, oh my God, I can tell you 100% there won't be any cell alive. Right? Because it has to be, that it will be there, right? But anyways, to make him happy, what I did, I said, well, okay, let's do culture, right? I put while into class, put the media and let it grow. Next day, see, there's everywhere, right? Afterwards.
They said,
But, but no, they were all there. Yeah. But there was like one thing, maybe I sticking there, one or two steps, right? So I removed and I say I'm just wasting my time. So I just said, if I remove the media, put on a new media in there, and then the better this next day, as long as they are where the cell was, this small island like everyone, right? And I changed the media again, and my God, in 1 month they have a whole lot of cell. So how was this? No, if I said to anybody, you would not believe it. But there was ovarian cancer cell, so this is very aggressive kind of cell. But they survive. They survive. Okay. So. Okay, so when you do subculture, so you know that there's like a lag phase, exponential phase, right? And then then if a normal cell line, then that kind of thing happen, right? If the cancer cell line is just continuously grow, right? So basically, when you do the subculture, you basically try to subculture when they are exponentially grow. I mean, they will slow down initially, but it's going to take like a long time, right? Okay, so there's the subculture, and then okay. Well, we already talked. We use this. There's a way how to remove these cells. There's like you can do cell scraper, trypsin, but now they are like mixture of like trypsin, collagens, or dyes, space, or now everybody wants to make money. So these companies they try to make product, and they want people to use their products. So don't use trypsin because it's cheaper. But if you use, then you probably get a better lifting of cell, or so they are all kind of product, but they do the same thing, right? Okay, so it just different sources, the trypsin, the advantage and disadvantage. Like trypsin is usually obtained from from pig or from wine, and then you have to basically heat in order to activate it, right? But the other one you can basically use as room temperature, right? This requires inactivation. The other one does not require inactivation, right? And then so there are some advantages, disadvantages, but I've been using trypsin for 30-40 years and I don't really have a problem, right? So again, it's just brief summary. So what you do, you rinse monolayer, it trypsin, incubate for a few minutes, stop trypsinization by adding the media, right? Spin cell, add fresh media, count the cell, seal new flask, and incubate, right? Okay. Okay, and this is just I just put down just in case if somebody has no understanding how it is done. So you can explain. So you have media, you remove the media, and then you have trypsin. Sorry, you have PPS, wash it, right? And then these are like suspension cell. So anyway, just you wash the cell. You already explained it, right? You already know all this, right? Okay. Now, so that's why the adherence cell. Now, if you are using suspension cell, it is a lot easier, right? Because you don't have to trypsinize them, right? Okay, I'm just checking if you guys are still awake or. Okay, now so what happens is the suspension confluency, right? So you basically, when you divide, you don't have to remove all the cells, right? Or unless you need all the cells, you just need a small portion, centrifuge it, remove the media, and then resuspend it, and then throw in the flask, right? So it's just like very simple. That you collect all the cells, centrifuge, get the pellet, and then resuspend the pellet and throw in the flask, right? Okay. Now you done all the cell lines and all that. You got a cell line from somebody is in liquid nitrogen. You thaw the cell line. You growing the cell line. You subculturing it, right? Whenever you get your cell line, very first thing you do is you try to preserve some cells, because anything happens, we still have this cell line, right? So, that's what we call cryogenic storage, right? So it is essential to prepare working stock of cell and preserve them in cryogenic storage, right? You probably all have done it, right? Some stage, right? Do not store cells in -20 or -60 pressure, right? That's the recommendation, right? Okay, because their viability quickly decrease when they are stored at this temperature, right? These are two main types of liquid nitrogen storage system: vapor phase and liquid phase, right? So the vapor phase system minimizes the risk of explosion with cryo storage tubes, right? They are required for storing biohazard material, right? Liquid phase system usually have longer static holding time and are therefore more economical. So this is, you probably have seen this, right? They have similar kind of structure, right? Liquid nitrogen tank, which has kind of these things, which has all this section where you can put your, samples, like, in a box, right? And this is actually get filled. So the thing is that when you fill with the liquid nitrogen, the temperature varies, right? The bottom is like 196 and then 178, and the very top is like, I don't know, -150. Okay. So, and then the thing is that what they're saying is that, usually the neck is narrow because it's actually prevent the evaporation of liquid nitrogen. Liquid, I don't know if it's like a bigger. The thing is that I always, think that, when you try to remove the cell, how difficult it is. You have to, pull it and move, jiggle it, and then take it out. And when you put it, you have to really do a few times to get into right place, right? So I was thinking that, why this neck is so small? Why then there's a big one and you just pull it out? But what happens that, with a smaller neck is help, preventing the evaporation, right? So not liquid nitrogen is not evaporating that fast, right? Okay, and yeah, we talked about already this cryopreservation. So, how you preserve this cell, right? So basically, what you do is that you use DMSO, right? And then why do you use DMSO? To prevent crystal formation. So what happens that the cells are in media, right? This is liquid, right? Cytoplasm is a lot of water is liquid, right? When you freeze a cell, what happens to water? It expands, right? So when it expands, it's going to break this cell, right? So what happens that we use DMSO? So what happens is the DMSO is displaces water. So DMSO has a structure very similar to water, right? So, but the thing is that DMSO has less effect on expansion. It does not expand on freezing, right? So all the water is replaced in the cell with DMSO. The cell is not metabolically active, so it doesn't really matter if you have water or no water, because it's going to freeze, sitting very cold, doing nothing, right? And then when you thaw it, then the ice, when you smells, when it freezes, kind of, like you probably have seen, if you put some kind of fruit in the freezer, right? When you take it out, it's all kind of burst, right? The same thing, like, when it freezes, water freezes, expand the volume, right? So there's the purpose. And then, okay, so freezing media is actually, what we use is 10% DMSO, right? But typically what we do, we actually make 20% solution. Okay, because your cells is going to be in suspension, right? Okay, so what you do, you take 20% DMSO media, and then you have like half ml of media, and you have half ml of DMSO media, right? You mix it, right? So it becomes 10%. Okay, and then you can freeze, right? Now,
I was just wondering, we were discussing that they thought that the MSO should not be used because the cells will die or they're toxic to the cells. And many of the assays, we minimize the amount of the MSO because it will affect the cells.
Yeah. What happens is, because these cells are going to be frozen, so they're not going to be metabolically active at all. So they're not doing anything. They're freezing like at -190 degrees. So they are, it just displaces the water, and then when you get, so they're not, on freezing, they're not going to burst. Like,
Yeah, I don't.
yeah. So that's the only purpose.
So, after we take the cells out of the, we add the media and we centrifuge them also to remove the air.
Right.
Then we add another fresh.
Right.
Yeah.
Yeah, so it's like the same thing, you know, when you add them, then you add a lot of media. So media is, you know, as water is going to disperse the TMS out from the cell, right? So you wash it out, right? Yeah. Yeah. Okay. Now, how you freeze this cell, right? Okay, so you just cannot add TMS and put in liquid nitrogen direct, right? You have to slowly freeze them, right? And then you have probably seen this, right? So what it is it's a very simple apparatus. So it has like it says space is in there, right? So and there's like a cryogenic vials which are stable at very low temperature. So you put it in there, make sure you label and make sure you write down on the vial, because if you put the label, when you put the liquid nitrogen, sometimes label comes off, right? Then you don't know what kind of cells it is, right? And people just try to so don't use, but rather directly write on the vial, right? Because and write with the some kind of permanent marker, not the water soluble marker, right? Otherwise, you end up with the same problem, right? But there are some stickers which are very, very sticky, especially designed for cryopreservation. You can use those stickers, right? But it's easy just to write on the vials, right? So you add these, and then what you do is that basically you use outside you fill this with ethanol, probably methanol, right? Okay, and then you put your tube, close it, and then you put in. I usually put in a styrofoam, box and put in -80. So what it does is freezes, but it freezes slowly, right? Not all of a sudden, right? So that's how you do, and then you can transfer this as -80 freezer if you want, for a few days. But for permanent storage, you have to put it in liquid nitrogen. Right, but there's the recommendation. But if you're using their cells are growing fine, there's no problem. You already talk about this. You already know microscope. Okay, there's just some how there's some cells look like. You probably seen this, right? This primary culture, like is the neuronal cells. The neuronal cells, you can see the neurons, and then astrocytes. The carcinoma cell line, myoblasts, we see the fiber, like the scleroderma cells, right? Neuroblastoma cells. It's just an example how different cells look like. Cell counting, you probably all know how to do cell counting, right? MTTSA, right? So you use MTTSA to check the cell viability or cell proliferation, right? Okay, and so I don't have to explain, you already know what it is, right? But then it's briefly what it is that how you do it, you trypsinize the cell, right? You do a cell count, because this is very important, right? So you have to have equal number of cells. You put this cell equal number of cells, usually about 10,000 to 5 to 10,000, depending on what kind of cells you're using, right? And then you treat your cells, whatever agent you're using, right? So it depends, sometimes you incubate for 24 hours, sometimes, depends on the agent you're using for 2 days or 3 days, right? And then once you incubate, then you add MTT, right? And then you incubate further for about 3 or 2 hours, right? So what MTT does? Yeah, we form it, but why? How does it form it? What's the principle? Reduction. Yes. Okay. Anybody else? Yeah. So the thing is that the way this works is that live cells and mitochondria, right? And mitochondria has this lot of enzyme which do reduction, right? Dehydrogenase, right? So if the cell is alive, they have intact mitochondria. Okay, so they will be able to reduce the dye, right? So you get a color formation. Okay, the cells are dead, they won't be dehydrogenase, they are active dehydrogenase. They're not able to reduce the dye, right? So it's more dye get reduced, it means more viable cells you have, right? If you don't see any color change, it means the cells are there, right? Or if you have somewhere halfway, it means You have, right? So what you do, you basically have your control where you have not added anything, right? Okay, so you expect that all the cells are 100% aligned, right? And then you have your agent and you see how, depending on that, what percent cells are alive and what percent cells are dead, right? Okay, look like you are all master in this technique. So, okay. There's another way we do is LDH release. Right? Have you anybody else used this method? Okay, so this works on the same principle, right? So what happens that the cells, right, who are dead, but they release LDH media, right? Okay, so what you do, you take the media out and do this LDH assay. Okay, or you can actually do it the same way. It means, if they get more reduction, it means there are more cells dead or alive. Dead, right? Because this their cells release LDH, right? If the cells are intact, they're not going to release any LDH, right? So that's another way to do it, right? Is do LDH release. Okay. The last one, contamination problem. Anybody has contamination? Yes, okay. Yeah, 4 weeks. Oh my God.
Yeah,
So you got to clean everything.
yeah, change everything.
Yeah, you have to filter and probably use new cells because cells are already
All
contaminated, right? Yeah. So contamination. There is nobody who has never had any contamination. Right? Everybody who's doing agriculture, some stage get contamination, right? Okay, so they just to show you that I don't know how well you can see. So this is cell, and you get bacterial contamination. This is bacterial contamination, and if you see as high magnification, you can even see the bacteria moving. Right? They move, they kind of shake around a little bit, and some you can easily see they are moving, right? So this is very clear is bacterial contamination, right? The other thing is that if you see the media, it would be turbid.
Yes.
Right? Because there are so many bacteria, if you see turbid, and the other thing is that it will be usually turn into yellowish, right? Very quickly, because bacteria also use glucose, and there's so many bacteria growing, and then they make lactic acid too, right? Now, the other problem is yeast. Okay. Yeah, and I don't know, you can probably see the yeast, growing, right? And it's very distinct. You can see, you don't see the turbidity, but you can see the spikes. Yeah, they're growing everywhere, right? Okay, mycoplasma, right? This is the very difficult contamination to check because you cannot check with dengue. What is mycoplasma? Mycoplasma has no membrane. It's very small, particles. Just kind of grows, and so there are like kids. They come and they can actually stand mycoplasma. Like in here, you can see like bluish spores, and you know that we have mycoplasma contamination. And they are, but the thing is that are easy to cure. There are kits available which actually cure the mycoplasma. So there are like different antibiotics which you use, and there's a treatment that how often you use, how many times you use, and then you treat them, and then they get rid of mycoplasma. Okay, so this is all about tissue culture. So if you have any question. All right, I think we're almost done. I don't see. Somebody has 2 questions in chat, but I can't open it. It's not responding. Okay.
Is there a problem that's not working?
No, I was trying to open the chat.